All right, good morning, everybody. We're going to get started with the second data analysis section. Nice to see you all here bright and early. We're going to start off with Tae-Han, who's going to be talking about TESS Gaia Light Curves. And just a reminder, if you have any questions that aren't able to be answered, you can talk about them on the Slack. Just post them there after the session and we'll be able to get to them.
Good morning. My name is Tae-Han. I'm a grad student from UC Irvine. Today, I'd like to talk about TESS Gaia Light Curve, which is a high-precision, dilution-free TESS FFI image light curve. So to start with, I'd like to show an arbitrary light curve of eclipsing binary. This is from another pipeline. So from this light curve, we definitely see the eclipses, but it looks quite noisy. And if we face fold this, it's even more clear that the precision is not very high. The first question that came into my mind is, what is the best precision we can achieve with TESS at each individual magnitude? When we move on to multiple sectors, the problem becomes more complicated. If we put all the sectors of this same EB on the same plot, we can see that the flux of this doesn't agree. And if we just ignore that and do a normalization and detrending, this is what we see. The ellipsis looks different in depth. And the phase fold also shows the same thing. And people refer this sometimes as the staging problem. And these problems are what caused me to start doing TGLC. I thought about, is there a way to improve the TESS FFI image light curve to solve these two problems? And turns out there's one common cause to both of these problems, and it is blending. So we've seen that, we've said many times that TESS have a huge pixel, which results in bad blendings. And if we compare, okay, this image is wrong, but if we compare the same field of view between DTF and TESS, this one should be flipped, but I don't know what's happening. But we can see that TESS pixels is so much larger and blending is so much worse. So these problems cause not only the bad noise here, but as well as the non-alignment between sectors. So before I go into what TGLC does and what we are trying to do, I'd like to first show the results that we achieved. So for the same EB, this is light curve we achieved after TGLC's deblending. So not only the noise reduced by quite a bit, each sector also align well with each other. So let's go into what TGLC did. So TGLC, in short, is a PSF-based FFI image light curve. And the very first step we do is to actually remove the backgrounds so that we are ready to do a PSF fitting. On the left-hand side, you can see this image of a TESS FFI image cutout, where there are two major problems. First of all, we have this leak light from the lower left. It could be street lights. We can model it with a simple gradient. The second thing you might be not seeing very clear on the first image, but it's very clear in the second, are those three vertical stripes. Those are caused by the metal stripes behind the CCDs. So we are able to simulate both and remove them from the image and produce this background removed FFI image. And this is then used for a point spread function fit. And the method we use is called effective point spread function. And this image shows the pixels as white squares and dots, and the EPSF is shown as red dots. And the EPSF is basically a twice oversample grid of points, which the actual PSF is linearly interpolated. Based on the different position of the star, the final PSF may be different by a little bit. So now consider a problem. If I ask you to do a fit on a FFI image cut of 100 by 100 pixels, how many constraints do we have? So 100 by 100, we should have a total of 10,000 constraints. But how many free parameters do we have? This depends on how many stars do we have, right? But an average number that we have is about 1 star per pixel for TESS. And that adds up, if we don't know the magnitude and the position of the star, that adds up to 30,000 unknowns, not to mention the PSF and the backgrounds we have to fit. So this makes the problem under constraint, and it's bad. So we have to solve this. So this is where the Gaia part comes into play. So Gaia measures nearby stars' position and the magnitude. If we use both of those as prior in our fitting problem, the only unknowns we are left with are the point spread function and the backgrounds. And we can use to multiply those two to produce a simulated FFI image. In this process, we can get the point square function for this particular cutout. If we repeat this, we can get it for each individual epochs. So now instead of these 30,000 unknowns, we're left with only the point square function and the background, which adds up to only 500 unknowns, and the problem is now well constrained. So after we know all the point square functions for the stars in the field, what we can do is to simulate the image with all the backgrounds except the target star, and subtract it from the original full-free image. And after that, we can have an image on the right showing a decontaminated image where only the target star is left. And on this image, we can either do an aperture photometry or another layer of point square function fit with a prior of your choice. So this is where we at when we published the paper a year ago. And after that, we have lots of data of TGLC produced, and we want to discuss how well we solve those two problems I mentioned in the beginning in a statistical way. And the first analysis I did is on the photometric precision. So we take all the light curves from sector 56, which is 200-second full-free image light curve, and this will be the standard for a while, so that's why we chose it. A total of 6 million TGLC is compared to 1 million QLP light curves. For TGLC, it goes up to test magnitude of 16. And on this plot is the distribution of both of these light curves. The vertical axis is the photometric precision, the horizontal is the magnitude. Basically, the smaller the value is, the better the light curve looks. So on the bottom is a running median of each distributions normalized to a test noise estimation from Sullivan. And from there, you can see clearly there's a crossing. And to conclude this, TGLC starts to perform better for any star dimmer than 10.5, and QLP would do better for brighter stars. And this makes sense because QLP focuses mostly on brighter stars, while TGLC's deblending power mostly benefit the dimmer stars. And the number 2 takeaway is at 15th test magnitude, TGLC can still perform 1% photometric precision. And I know 15 magnitude is a number that many people cannot reach, and even so is afraid to because how noisy people would think it'd be. But this still can achieve 1% at 15th test magnitude. So another test we want to do is about the second problem. We call it staging, but people can also call it decontamination inconsistency or dilution problem at different sectors. To approach this, we started an exoplanet perspective. So we take all the 500 TESS exoplanets. We took only those that are single planets in the system, because this basically simplifies what we are going to do. We take all the light curves among all the sectors for these exoplanets up to sector 55. And each of these light curve is put into an exoplanet package to fit for their radius ratio. And the reason I'm trying to get the radius ratio fit is radius ratio is a direct measurement of the trended depth. And the trended depth is a direct reflection of how well we remove the contaminations. If the contamination is left, or in other words, not enough contamination is removed, the trended depth would naturally be shallower so that the radius ratio would also be biased. So we have 1,000 of these for TGLC and 1,000 of these for QLP. And we put them into these histograms. So on this plot, we have 2 distributions. On the top is for the brighter stars, on the bottom is for dimmer stars. The division is 12.5 test magnitude. And the distribution is around the fit results I got from the previous step, minus the literature value of the radius of the planet, which is usually got from ground space telescopes. So we treat this as a more precise number than TESS estimation. So the first thing you see is for brighter stars, both TGLC and QLP do a good job of maintaining their median around 0. So that's good because there's no bias. But as we go to dimmer stars, QLP starts to show a bias towards underestimating the radius, or in other words, underestimating the trended depth, meaning there's some kind of decontamination lacking. So in conclusion, TGLC is performing better overall because it shows minimal mass or at all test magnitudes, where QLP shows more bias towards dimmer stars. And I believe if we go dimmer than 13.5, which is the limit of QLP, the difference may be even bigger. So you might notice I've compared in both statistical cases I compare TGLC in both cases to QLP, not because QLP is a bad pipeline, but just because QLP is another good pipeline that focus on some kind of deblending. And we want to compare to it and see how much better TGLC does in some cases. Okay, so the last step is what is TGLC used for, and what will you be able to use, how you can use TGLC for your own science. So since its publication, TGLC has been used for multiple science, including exoplanet research, variable stars, transient events, and also comparison to other missions that's already launched and is going to be launched. And if you want to use TGLC, there's two ways. There are two ways. The first way is to get TGLC directly from us. TGLC is held as a high-level science product. This consists of all the stars up to 16th TESS magnitude. Currently, the bulk download is up to sector 37, and the portal query for singular light curves is up to sector 8. This process is quite slow because there are lots of high-level science products to be uploaded, and TGLC is one of the largest now because how many light curves we are including for each sector. And another way is to download TGLC locally and run it on yourself. The good thing is you can either do the newest sectors that just released, the full frame image is just released, but also you can do arbitrary aperture choice, as well as an arbitrary fit of point square function. More details are shown in the tutorial I held on GitHub, but as well as in the papers. And the last resort, and many people, and actually most of the people in the previous slide, actually reached out to me and asked me to provide a light curve for them. And I'm really happy to do so for anyone in the room and anyone else. And if there is questions about anything, please send me an email. That's all. Thank you. I'll take questions.
All right, thank you for a great talk. Any questions in the room for Taehan? Oh, yeah, I see one in the back there.
Hi, this is Nick Saunders, University of Hawaii. Excellent talk. This is really exciting. I was just curious how well the deblending works if the contaminating source is a variable object or if it has like an eclipsing binary signal.
Okay, thank you for the question. So actually, this is shown in one of the plots in my paper, where after the step we got the decontaminated image, instead of doing a simple aperture, we do another layer of point square function fit, which means we put a PSF on both the star as well as all the stars near it. And the case we showed in the paper is exactly a dim star next to an EB. And we allow both stars to float, and the results shows that we can basically eliminate the EB signal and separate the dim star from that signal almost, I won't say completely, but nicely. Thanks.
Eric?
Eric Feigelson, Penn State. Thank you. You compared TGLC to QLP. Can you also comment on its relation to SPOC, SPOC, which is the official NASA data products?
Are you referring to the 2-minute or the full frame image version?
Any comment you can make.
Okay. So at the time I published, I only focused on comparing to QLP, Eleanor, and the 2-minute SPOC light curve. I didn't have the time to show the SPOC, but for the stars that SPOC produce, TGLC is performing similar to it. And it's performing similarly to those. Yes, it's not better, I would say. It's similarly. And because the way that these things are quite different, these are produced quite differently, there's not too many statistical comparison to them. There are just a couple, I think 10 maybe, comparison between the light curve of EBs and exoplanets to the SPOC 2 minutes. I have plans to compare to the full frame image version of the SPOC pipeline in our next publication. Yeah, thanks.
Maybe one more quick question right over here.
Hi, Domenico Nardello from the University of Padua. So how many time you need for extraction of a single light curve?
Can you repeat?
The time machine you need for the extraction of a single light curve of a sample of 10,000 light curve, for example.
You mean how efficient is the code to run?
Yeah.
Oh, it's actually quite fast. So basically for any field, like after the cutout, the most time-consuming part is for the point spread function to be fitted. And once it's done, producing each individual light curve is very fast. A number I can give you is I run it on two clusters, each have 128 cores of CPUs. That's what we use. To run a single sector up to 16 second magnitude takes about 2 days. And that is a number of about 6 million light curves. You can do the calculation. On a personal laptop, actually the time that takes the most is to download the full image to your local disk. And it's usually done through TESS cut. And after that step, I mean, including those, it's a couple minutes or 10 minutes, depending on how large of a field you're looking at.
Yeah, because I developed a similar pipeline, and I'm using TESS cut now for the extraction of light curve, and it takes a few seconds for a single light curve. So
yes,
I suggest you to use the same.
Yeah, thanks.
All right, let's thank Tehan again. Next up, we have Aviv Ofir, who's going to be talking about systematic errors reduction in both TESS and JWST data.
Hello, my name is Aviv, and I would like to tell you about identifying and correcting systematic effects in TESS and JWST data. But first, I would like to thank the organizing for allowing me to give this talk here. So thank you. Well, let's define the problem. What are systematic effects? Systematic effects in this scatter versus magnitude are just this gap over here, which is the fact that the observed scatter of stars is higher than the predicted ones. This means that we have an additional noise source in the data, which produces this noise floor. Note that this effect, yes, that this also has a typical time scale associated with it. Later, if you ask, I can also tell you what happens over there, where the observed scatter is actually lower than the predicted one, but you can ask me about it later. Anyhow, at the core of our proposal here is a technique called CISRAM. It's a 20-year-old algorithm, widely used, and it assumes a very simple thing that you have lots of light curves, lots of images, lots of stars. And some of these stars are constant, some of them are eclipsing, some of them are transiting or pulsating, whatever. You remove all the variability that you think that exists in the data, and then you are left with residuals. This is supposed to contain only noise and systematics. And the model for these systematics is simple. Suppose you have a given effect, A, and it is constant for all stars. It just has different magnitudes for each one of those stars. Interestingly, if you know what the effect is, then you don't need to think what are these coefficients, what are those magnitudes for the effect, because they are simply given by this simple formula, which minimizes chi-square. And the main insight of the authors of this paper is that it doesn't matter if you read this matrix of numbers column-wise or row-wise, because once you know what the coefficients are, then you can calculate exactly the same way what are the best coefficients, the best effects, so a refined values for the effect. But if you have a refined value for the effect, you can recompute what are the coefficients, and then do that again for the effect, and so on and so forth until convergence, and it does converge pretty quickly. So once you have convergence, you have the best linear effect and the best coefficients for the first effect. You remove that, and then you do that again for the second effect, the third effect, and you have cleaned your data, right? Well, not exactly, because CISRAM is a type of weighted principal component analysis. And as such, it has a problem that you can always remove yet another effect. You don't know when to stop. And if you continue to do it for too long, you will have remained with zero, like identically zero information in your data. So the question of when to stop is still 20 years on, still hotly debated in papers that are still that is still being published to this day. So it has existing topic, and I would like to propose a solution to it. And the solution is simple. Instead of asking when to stop, we should actually ask how to start. Let me explain. I was browsing through the internet and found a popular implementation of SysRAM, and they chose to start to seed this iterative process with a ramp from I'm not good at it. A ramp from 0 to 1. And this is a perfectly good choice. You can start with this ramp and apply it to your data and hopefully get to some structure in your data, in your final analysis. And this is illustrated here just by a sign. The important thing that this ramp is a perfectly valid choice. It was just different from mine because my own choice was not a ramp from 0 to 1. It was random numbers from 0 to 1. And I too had hoped that this will produce some linear effect or some systematic effect in the data if it exists. And this got me thinking a little bit, because if you start with some kind of random noise and you do this again and again and again, and you still get the same structure in the data, it means that the effect is strong in the data. So it's not only that it means the effect is strong, it means you can actually measure the width over there. And if you can measure the width, you can actually quantify how strong the effect is. Because if it is, the width is smaller than the amplitude, it's a significant effect. If the width is smaller than the amplitude, you'd know when to stop. So we have a solution to this stopping criteria. Okay, how to start with many random initializations, when to stop when the result is basically noise. Great, let's apply it to TESS. Here we have one camera, one quarter, one effect, the first effect, and it appears quite strong. There is some structure here with the amplitude of, let's say, 20 in these units. But let's zoom in a little bit further to this corner, and we can see, well, is this structure or noise? I don't know. I'll help you, and let's zoom in a little bit further to this corner over there. And now you can see that this is actually not one effect, but over 100 realizations of the same effect. So this is very, very high ceiling to noise. The scatter is actually tiny. And if you calculate what is the relative of the amplitude relative to the scatter, each one of these points, you get this curve, which is actually in log scale. So most points have a signal to noise of tens, hundreds, or even thousands. So this is a very, very significant effect. This is the first effect. And so are the second, the third, the fifth effect, and even more. So you can clean the data. And what happens? What would you get? You would get this. This is one of my plots for my pipeline. So let's clean it up a little bit. So we have here pre-system residuals and post-system residuals. And obviously, the scatter is slightly lower, but this is not the important part. The important part is over there. If we progressively bin the data to bigger and bigger bins, so longer and longer time scales, then you see that it no longer behaves like the square root of n that we anticipated to be if it were white noise. The raw data levels off quicker, and the system data continues along this trend for a longer period. And I just want to note that this blue shaded region is what happens if you actually inject pure white noise into the same pipeline. So it too does not behave like the square root of n that you expect. But this is you can ask a little bit later then, after the talk. Anyhow, then the system data behaves closer to the way that pure white noise behaves. So it appears to be better than the raw data. But beating the raw data is not a big competition because there are process data, say the PDC pipeline, which is pretty good. And here you can see that the two pipelines produce pretty comparable results by eye. But again, I told you that this is not the real test. The real test is actually comparing to the variable binning test. And here you can see that the ensemble system consistently outperforms the PDC pipeline. Does it help you? Well, this particular target is not a random target. It's actually a TOI, sorry, with a planet in it. It's a very shallow planet, 4.7 days. That's the peak over here. But it's the third peak in this BLS spectrum because it's a shallow planet. So it was not detected, obviously, on the single quarter data, but in multi-quarter data. But if you try to do the same detection analysis on the ensemble system, you do find that this is indeed the highest peak in the data, and significantly so. So it does allow you to detect shallower patterns in the data. Moreover, if you apply the same thing on our newest and brightest analysis technique called TACHLES, which is still in prep, but I'm sure you will soon hear about it for analyzing JWST data. And although it is, I claim, to be the newest and brightest and best analysis for JWST data, it too has systematic effects in the data with many, many images that have significant amplitude in their ensemble system coefficients. So this applies to basically TESS, JWST, everywhere. Let's see. So to conclude, ensemble system is the way to find the stopping criteria, and therefore to find more and better effects in your data and then remove them. Why more? Because most of the time a human would not think that these effects are significant, and therefore would choose to stop earlier. And by you having this data-driven metric, we can continue in removing effects until data tells us it's time to stop. We demonstrated this effect on TESS and JWST from ground-based performance, and basically it is applicable wherever you have a metrics where you suspect that there are still systematic effects in the data. Thank you.
Thank you, Aviv. Any questions in the room? We've got time for a few. All right, while people are thinking, I've got a question. Did you do the comparison over just 2-minute cadence data, or do you see any differences between how it performs on the FFIs versus 2-minute?
Differences over?
Compared to the 2-minute cadence data versus the FFI data, do you see differences in performance?
Not yet.
Okay. Question here.
Hi, Sam Gill, University of Warwick. This is awesome. What goes into choosing the ensemble of stars from which you get your coefficients from? Because you've got to be so careful about not including bad stars there, and especially with TESS, considering how it's got quite a lot of systematics. How do you choose what data to form the coefficients?
You choose the stars that do not have intrinsic variability to use as a training set to learn what the effects are from. And the problem is that the better your data is, basically all stars appear variable. So it takes a little bit of time, a little bit of manual work to actually not mess up this part.
Time for one more question.
Okay, this is BC from Harare University. Now, when you choose the ensemble of your training data, so-called, when using it on all the data, what would be the effect on instructive variable, on instructive variability, even in your data? Will it not remove this signal that are of instructive variability when using it in all the data sets?
As I explained, you first have to look at the data and remove whatever strong variability that you believe already is there, like eclipses, like transits, like pulsations. And when you try to look for faint things that you have not yet modeled, then you should clean the data and then look for these subtler effects. So the initial effects, for example, a very strong transit, should be pre-removed before applying.
All right, let's thank Aviv again. Next up, we have Ryan Ridden-Harper, who's going to be talking about TESS Reduce, which is for extracting TESS PSF photometry light curves.
Cool, thank you. Thanks everyone for coming out this morning. I'm going to be talking about a project I've been working on for pretty much since the start of the TESS or after TESS was launched, which is trying to extract light curves from the TESS dataset. Initially, it was for transients, so things that explode and change quite quickly. And for these objects, removing the background was very, very necessary for it, because we want to look for small changes and wiggles in the light curve. So we needed a very good way of removing the background and leaving more or less nothing there. But the subline that's here, transient focus analysis, isn't strictly true. You can use this for anything. So more or less, it's a flux calibrated difference imaging pipeline for TESS. So this has been built by myself, as well as help of many others, including getting it up to version 2.0, the group at the University of Canterbury that I've been working with. So using TESSJWST is pretty simple. All you need to do is pip install it. And then if you're wanting to look at a supernova, for example, you can just search its name and then tell TESSJWST to go about doing its business. And it will spit out a figure like the one on the right, where you have the light curve, as well as an image of the reduced image. So you can see that it's a pretty blank TESS field in the bottom one. So that's because the difference imaging has worked well. All the stars have more or less disappeared. And the only things that remain are artifacts of brighter stars. But as I say, this isn't only useful for supernova and those types of things. You can also use this for, one more. Supernova is that we can use this for flux calibration. So it calculates from the field that it's observing what the flux calibration should be. So we can see in this example of supernova 2020 CDJ that an independent flux calibration from TESSJWST matches up pretty well with ZTF. So in this case, it's working quite well. And we find actually the 0 point for this field is about 20.36, which is a little bit different from the average value of 20.44 that is often used for TESS. But this can be used for aperture and PSF photometry as well. Sometimes the alignment and things don't work quite well. So we have the aperture photometry of a supernova light curve here. It looks kind of messy. You wouldn't trust this, and you kind of just move on. But if you do use the PSF photometry method, suddenly all the mess just disappears, and you get left with the nice supernova light curve. So generally, PSF photometry is pretty robust in this. We use the TESS PRF module, which has models of what the TESS PRF should look like at every point on the detector, and just apply that as appropriate on the detector. But there are some caveats. So this is something I'm still looking into. There is no preferred method of aperture versus PSF, which was upsetting when I discovered this, because you'd hope that PSF would do better at all cases. But there are some subtleties with how the reduction happens. So if you have a weird light curve in one, it's always good to check the other one. And the other caveat, which is true for all photometry, is that the 0 point calculated for, say, aperture photometry will not be the same as 0 point calculated for PSF photometry. So just keep that in mind if you're using 0 points. So other than supernova, you can use this for anything. So here's just a random star that I came across over the years that is a nice example. So if you want to look at this object, for example, you just give it RA dec and then use this space-time lookup function, which will tell you what sectors the object has been observed in, and you can just feed it into TESSJWST, and it will spit out a light curve for you. So again, this one has a 0 point that's slightly closer to the average value, 20.41, but it is, again, a little bit off. And if just for fun, if you have time to kill like I had last night, you can look at, say, TRAPPIST-1 and find that it's a very flat light curve. But there's like one peak here, which, what's happening there? Quite interesting. You zoom in and you find it is a very symmetric light curve. And as we heard from Deborah Woods yesterday, one should be cautious of very symmetric light curves, very symmetric features in light curves. And if you go and look at the FFIs, this is actually an asteroid that crosses over top of TRAPPIST-1 during TESS's observations. So if you're interested in looking at TRAPPIST-1, be wary, there's an asteroid there. So the way TESS works is over the years, I've added layer upon layer because we get a new supernova that's in a particularly bad spot of TESS. So then I have to add some more wheels on to make the reduction a little bit better. So, but the general way it goes is that a reference image is selected. Then we go and create a source mask for the detector, as well as masking out straps and things like that. Then we mask out all of the things that we don't want to include in the background, and then interpolate over everything that hasn't been masked, and that creates the first pass of the background. We then use the first pass of the background to calculate the effective quantum efficiency enhancement for those strap columns you saw earlier. And then after we've done some initial background subtraction, the images all get aligned to the reference image. So once the alignment movement has been calculated, go back to square one, and we start with the raw test data again. We divide by the quantum efficiency enhancement, so that's pretty much gone. We align frames to the reference, subtract the reference, and subtract it again, apparently. That should be, that we then calculate the background for this subtracted reference. And we subtract the background, leaving with a nice difference image field, with which we can calculate the 0 point and just do our photometry on. So this pipeline works reasonably well for the most part. So I'll just jump through some of the key things that come out of it. So this is an example of a mask where the light blue splodges are the sources in the image that get masked out, and those strap columns are the big columns are the straps that get masked out as well. So this is made using Gaia sources and for every field that you just query for TESS-reduce. The background, as you saw before, can be quite complicated. So this was actually the case that prompted the creation of TESS-reduce. So we had a supernova that's sitting in the galaxy, which is the little blobby thing in the middle of this image. And the supernova was right on top of one of the straps. And we couldn't back away from analyzing the supernova because we had Hubble observations of it. So we just had to go all in. So the process just kind of calculates the smooth background, can use the quantum efficiency enhancement to get rid of the straps. And then what you're left with is an image where the background is gone, and you're left with just your sources remaining. But over the years, it became more apparent that doing things that way, you would still have signal of the background left over. And it took me a while to come up with an idea, in which case, if your light curve of a pixel still has a residual background left in it, it correlates quite well to the background value you've estimated for that pixel. So you can run through a simple procedure where if you find they correlate well, then you run through some additional analysis where you pretty much add more to the background, so multiply it by some factor, and then subtract it from your pixel's light curve until the correlation is minimized. So by doing that way, you can get this kind of last few % of the background that kicks up in some of these pixels. So with alignment, TESS is generally very well aligned, but there are often these small sub-pixel shifts throughout a sector, and they do matter when you're trying to do precise difference imaging. So in this case, this is less than or on order of a % of a pixel shift, but that does matter. If we go and look at, say, our reference without doing alignment, you can see there's the characteristic dipole of sources when you do the subtraction. So over subtracting on the top side, under subtracting on the bottom side. But after you've done alignment, that dipole disappears and you're left with those kind of splodgy patterns, which are just the residuals of a normal difference image. So the last step, which is possibly the more interesting one, is the flux calibration of TESS. So I built a pipeline, another pipeline called Calibrimbor, which if you give it a photometric filter, it'll match either pan-stars in the north or sky mapper in the south and give you a linear flux combination that you can use to predict what the flux values should be in the filter of your input. In this case, we can create those equations you see on the top to convert fluxes from pan-stars to a flux in TESS or fluxes in SkyMapper to a flux in TESS. So these predictions actually turn out to be quite robust to color variations, especially for stars, and they can be used to generate some pretty nice 0 points. Another thing we take into account is line of sight extinction, so we can use catalog stars to work out what the average EB minus V is. And of course, we need to work out which of the stars in a field are isolated stars, so we can just run through and calculate all of those. And then if you take those stars, do the photometry of them, and compare them against the predicted magnitudes that you have from those equations I showed before, or the predicted fluxes, you end up with a histogram like this on the left, which is the cumulative 0 point for every frame, every source in every frame. And on the right-hand side is just how that evolves over time. So generally, the 0 point is very static in the TESS, which is nice and what you'd probably expect. But as I mentioned before, the exact value of the 0 point does seem to bounce around a little from that 20.44 value. So TESS-REDUCE was just built to try and recover these transient signals from the background. So we can start with something that has thousands of counts, whereas this object on the right after the reduction, it's represented in a flux here, but I think its total brightness was around like 40 counts or something like that. So, we're removing things that are about 100 times brighter than it and recovering the signal quite nicely. But anyway, TESS-REDUCE is still in development. I don't think it'll ever be done, unfortunately for me, maybe. But if you use it and you find that there are things that would be helpful to include in TESS-REDUCE, please do talk to me. Happy to see if I can add things in. Also, if you have particularly weird objects with kind of gross reductions and you want to know why this is happening, also feel free to get in contact with me, because I'm always interested in seeing if it can be improved in some way. But yeah, I'll stop now, and if there's any questions.
Thanks, Ryan. We've got time for a few questions. All right, while people are thinking, does TESS-REDUCE take any arbitrary array in DEC, or do you need a tick ID in order to make a light curve?
You can give it any right-ascension declination, and it will just spit out photometry for that patch of sky. So the main thing I've built this for is to do a blind transient survey. So we don't care where something is, just it exists somewhere.
Nice. Any questions? Aviv?
Hello, Aviv from the Weizmann Institute. Can you do this in large scale, produce light curves of basically everything?
Yes, it does get a little tricky though. So by default, TESS-REDUCE uses 90 by 90 cutouts. On larger scales, some aspects of it begin to break down, like the alignment procedure I have at the moment isn't the best it could be. So if you get too big, the alignment doesn't quite work from the corners of, say, a single CCD. But we've been running it on data cubes that are about 500 pixels square, and it's been working fine there. And I've run it on solar system objects as well, where you make a rectangular cutout, which is quite large for the entire path of the object, and it still passes through. So yeah, there are ways in which it can be improved in that sense to work for an entire CCD at a given time. But at the moment, we're finding it's okay to just cut a CCD up into 16 pieces and run them through.
There's one question in the back.
Hello, Kirill Sokolovsky, University of Illinois, Urbana-Champaign. What's the right way to analyze multiple sectors of data with TESS-REDUCE?
Yeah, that's a good question. That's something that I haven't looked into a lot at the moment. As we saw in the first talk of this session, there is quite a displacement between sectors. So last time I looked at this problem was a few years ago, and I've made a lot of changes to the pipeline since then. So I think there will be some combination of 0 point changing between sectors, as well as the position that your target falls on will be slightly different relative to the pixels. So a combination of the 0 point and the PSF photometry might be a good way to try and bring those down to the same level.
Thank you.
All right, let's thank Ryan again. And next up, we've got David Rapetti, who's going to be talking about comparing and automatically optimizing the performance of systematic error correctors for TESS light curves.
All right. Let me first thank the organizers for having my talk here. And I'm just, David Rapetti at the UCRA located at NASA Ames. And this work is in collaboration with John, Joe, and Doug here, participants in this conference as well. And as part of the Spock Pipeline team, we've been working on this project that basically I don't need to motivate this project here as this session and the stays here, but basically it's critical for all the studies that we've been hearing this week here, exoplanets, stellar physics, asteroseismology, and so on, remove the systematics properly. So in addition to a production tool like PDC, right, by a Spock or QLP here in MIT, we have various proposals in the community for removal of systematics as we're in here today, here and during this week, and others can come, right? So I have here some of the examples in the community that we've been considering, but as far as we know, there's been no comprehensive analysis to try to make an attempt to compare these systematic corrections in a large scale with proper, metrics and systematic tools. So basically what we want to do here, so normally these tools have been developed to apply to a particular targets of interest, but again, no comprehensive efforts has been made in that direction. So basically our purpose here is to use different correctors, and you can actually, we use some of them for the moment, but we generated a framework. You can include additional correctors here and basically do this kind of comparison at larger scale. One of our interest as well has been focusing, has been focusing on removing scatter light, which is a key systematic for TESS. But so for all these reasons, we've been developing this tool, this code. Cisco Copy is the name, the current name, and this is associated with a publication in preparation, and the code is going to be released together with a publication. This is in the works. But so the aim here, as I was saying, is to try to do this comparison, to include automatic parameterization. You don't want to do that manually, case by case. You want to do that for larger scales. So we need to include some automatic parameterization, optimization of the process. So we have as well the goal. Let me say as well, this code is based on light curve. So light curve doesn't need introduction in this audience as well. But here is the citation. And basically, what we do is apply this framework, which we can choose which kind of correctors we want to include. We can expand it and so on to a particular sample. The sample of your size, you choose a sample for whatever regions you want. I'll show several examples for the moment, and then basically you apply. So we define a case. By the way, when I'm referring a case, here is a target and a sector. That's what I'm going to be referring when I'm mentioning a case. And then the code produces a series of figures, individual figures and statistical figures, and a series of metrics, right? And this can be also extended as we go on. So we have these are the correctors I'm going to be discussing. I'll explain them in a moment. But RCQ and PLD are the ones that we included in the interest of removing a scatter light. All right. So these are the correctors that I'm going to be discussing at the moment. RCQ, regression corrector with quaternions. So this is based on the regression corrector class of light curve, and basically it has three components. So it has one component which is a spline to account for stellar variability. We have another component which is a PCA eigenmodes to account for background light, for a scatter light, and it has an additional component with a mean, the standard deviation and the skewness of the quaternions to account for Poynting jitter and mechanical effects. The same kind of a structure is the next corrector, which is PLD. It has the same first two components. The third component, instead of using the quaternions, what we use is the PLD technique, the pixel level decorrelation technique, to account for Poynting jitter and mechanical effects. And then finally, we have, and this is also based on the PLD corrector from Light Curve. And the next one is the CVB, which is based on the co-trending basis vectors technique from PDC, from a Spock. But this is an adaptation of the PDC technique into Light Curve. They're not the same. That's why you're all interested also in comparing them. And this is also based on a class E Light Curve CVB corrector. All right. So these are the correctors we're going to explore. And as I said, we need a optimization, which is based on the parameters of each corrector. So we need to select them not manually, but the machine needs to select them. So we need to select a certain number of parameters for each corrector and a certain number of values that we want to explore over, right? And this, we need to select it carefully because this is a trade-off between computational power and the precision that we're going to get for each corrector. So this is our first attempt, this table here, of the parameters for each of the correctors and the values. How we selected that was based on a 24-case sample, initial sample that was selected from Spock results by having pathological effects in the scatter light. Okay, so this sample is the one we use first to calibrate this table. And of course, we can expand that. We can use it to another sample, but the results I'm going to present today is based on this here. And then we need a metric in order to select that. We need to minimize a goodness of fit metric. The metric that we've chosen for the moment, and we can change as well, that is a harmonic mean of various CDDPs at various time scales. And I'll show them in a moment. So basically, this is one of the products of this Cisco COPI pipeline. These kind of plots, the user actually can change different formats. And then you can choose also to show the orange curve or not. The orange curve is the uncorrected curve from Spock. This is the simple aperture photometry curve. And then we have PDC in red. So we get directly from Spock, from MAST. We have PLD in purple, RCQ in blue, and CVB in green. And this is a direct comparison for one of these objects, which is a pathological scatter light in the sample. Okay, so this is the and you can see here that these large effects, scatter light effects in the uncorrected light curve. And the two things I want to point out here of interest. So, first of all, let me say this is the CDP I was mentioned before, the combined differential photometric precision, and we use the proxy from light curve, right, which is a Savitsky-Golay high-pass filter. All right. So, which time scales we use? 30, 60, 160, 120, 160, 200 minutes. So these are these numbers here. We calculate it in parts per million, and then we do the harmonic mean in order to penalize outliers, in order to do the optimization I mentioned before. And here we can see that, for example, in PDC, we have these large gaps due to the scatter light that the system decides to remove. But PLD and RCQ are able to correct at some level these areas here. And I'm presenting, of course, some of the interesting results. Of course, there is also failures at the moment. I'll present the statistical results later. But this is some interesting results where this works. This is another one from the same sample, the same 24-case sample. And we can see these gaps here and how PDC and RCQ are able to recover this data. And of course, if you have a transit in this data, then it becomes very interesting, right? So we can have, for example, this is from another sample, a slightly larger sample. This is a sample of 76 cases, and this was selected with a different criteria. We wanted to use different a range of stereo availabilities, right? So here we can see some stereo availability. So this sample is 76 cases with this criteria, and we can see here large gaps and the beginning of the first and the second orbit, and we can see how well it recovers per PDC and RSQ. So that's interesting. And you can see also here the numbers, right? You want to the CDP to get reduced. So we can see also how it gets reduced in some of these cases. And you can see one of the examples here that you can maybe recover transit, right? And we have some interesting in the community. We've been working in the community. We've been able to recover transits due to this scatter light removal in the case of PDC, and we can do it with PLD or RCQ. So this is two more cases of the same sample. And this is another TOI, and we can see another possible recovery of the transit here. And then what I want to show you now is the statistical results. This is another product from Cisco Copine. When you have your sample, this is another sample, the larger sample that we have at the moment, 826 cases, and we can do some statistical analysis here. And we represent again each of the correctors with the same colors. So PDC is in red. We can see that PDC is the one that, as you would expect, has the larger improvement. So this is what we're showing here is the % improvement in photometric precision. So 0 means no improvement. There's some tails of negative improvement, and then we have large tails of improvement. So we can see that PDC has a bump around 30 to 40% PDC and CVB. CVB you will expect to be similar to PDC in these cases. This is for 30 minutes. This is for 200 minutes, the two extremes. And you can see that for 200 minutes, there's larger improvements here. And then you see that you have these large peaks at 0 improvement, and especially for RCQ for some reason. But actually, when we go to the HM, the harmonic mean metric, then we don't have this big peak for RCQ. RCQ and PLD look more similar between each other. Then CVB looks more similar to the other ones, and we still have a larger improvement by PDC, as you would expect. We optimized this table that I showed before, but only for the scatter light cases. So we can extend that to other cases, and we expect these other methods to improve and get more similar to PDC. There's other reasons why we still can improve them as well. Christina mentioned an effect, for example, for PLD. We can probably have some correlation with a crowding metric, for example. But I want to just briefly also mention this other metric, which is overfitting metric. The larger the value, the better. In this case, we can see here the PDC has the larger peak, but comparable with the other cases. And then we have some a little bit of strange behavior from RCQ, doesn't have the main peak at the beginning, and they have a bump here. All right, so basically just I want to conclude. These are my conclusions here. I'll leave it here, but we have this new code coming up. Cisco Copine has an automatic parameterization. We had a special interest in removing a scatter light. We've seen that PLD and RCQ can do that. This is an interesting case that from the community. This is a Nature paper, TOI 1835, and there was of the 6 resonant sextuplet of the 6 planets, there were 2 planets. They only were able to detect 1 transit, but with our method here, because the PDC discarded some of the cadences, but with PLD technique here, we recover 1 cadence for each of the planet, and we're able to confirm the resonances. So of course, we have evident failures in cases in PLD and RCQ. We know why. We can extend the grid at expense of computational power. And we also need to be careful with the metrics in order to make sure that the metrics represent a failure or not. But and again, and for the moment, PDC as expected has an overall better performance. Thank you.
Thank you, David. We've got time for maybe one question over there.
I'm just wondering if you checked the signal distortion effect that you introduce when you use any systematic correction. If you don't know the signal, then the signal will be distorted a bit, depending on the type of method you use, and that causes a bad signal estimation. All these methods are good when you look for the signal without knowing where it is and how does it look like. But once you found it, then you have to do a complete fit. I'm just wondering if you have a module in your system that performs this.
Okay, yeah, I think I didn't hear the complete word that you said at the end, but I think I heard the idea. The idea is that if we have a way to characterize, how well we do in terms of when you find the signal, if we remove some part of the signal, right?
Yeah. If you don't know the signal and you apply any systematic corrections, they will eat systematics, but they also eat some part of the signal.
Yeah.
And then later on, you have to take care of that. And there are very good examples, all of the methods that you, even PLD has this, which is one of the best, I think.
Yeah. So yes, of course, when you remove systematic, you need to be careful with that. The point here is that, of course, there'll be cases because we're trying to implement these methods again at the production scale. So of course, there will be cases that we have failures, right? So as I was mentioning at the end, we need to be careful that our metrics correctly represent that it's been a success or not. We've seen sometimes that if you inspect by eye, you can see that actually it's a false positive, right? So the metric maybe looks good, but you can see by eye that it's not. So all that is what we need to adjust. But of course, we cannot expect necessarily to be 100% in a production scale, right? If you want to do many metrics, if you want to do it automatically, but we can adjust all these parameters, all these metrics, and so on. We can include other metrics to adjust the method, and then we compare statistically. And the comparison here is against PDC or QP. So these are pipelines that are already working. So we're going to get statistically to that level for any corrector that we introduce. Yeah.
All right, that's all our time for questions. Let's thank David again. And last talk before the coffee break, we've got Tyler Pritchard, who's going to be talking about spacecraft-based detrending of TESS light curves with TESS vectors.
Hi, everyone. I'm Tyler Pritchard. I'm a support scientist in the TESS Science Support Center, and I'm here to talk to you about a new product we've been working on, TESSVectors, which is really designed to help make detrending pipelines that you're working on that use spacecraft engineering data like quaternions or the respective positions of the Earth and Moon easier to interact and deal with. But before we get into that, I just want to briefly remind you about what the TESS Science Support Center is and what we do. And since we're in the data analysis section of the meeting, I really just want to highlight that a big part of what we try to do is create tools and products to help you, the community, interact with TESS and its data. So we have a website here that contains a lot of information on TESS, how to propose and observe, some basic tutorials for accessing and analyzing TESS data. And also we staff the TESS help desk at bigbang.nasa.gov and are super happy to chat with you, the community, and any students that you might have about your experience working with TESS data. I also want to briefly advertise the workshops that we put on. So we've been putting on an interactive data workshop before the AAS winter meeting for the last few years, and we just submitted a proposal for AAS 245, and we're going to talk about the TESS mission, how to propose for the TESS GI call, and how to work with TESS data in the cloud. And a big part of it is a hackathon interactive session. So if you or someone you know is thinking about proposing with TESS for the first time or starting to work with TESS data for the first time, it's a great place to come and get involved and meet other members of the community and start working with TESS. We also have been working and developing a lot of other tools, and I'm going to go through these quickly because this is not the point of the talk, but I'm doing this mostly so it's on Zenodo for y'all later. We've been working on things like LK search, which is sort of a minimalized, repackaged version of the light curve search that maybe you all know and love. Crucially, it adds a few other data products like validation reports and other things that are not sort of visible in the full version, but it's a stripped down, TESS-focused, lightweight interface. We've also been doing things like LKPRF, which is designed to help you interact with the TESS pixel response function in the same sort of methodology. We've been working on tools to help work with TESS data in the cloud. We've been working on tools to help you find where TESS is pointing and target visibility. So we have TESS WCS, which is sort of a new version of a TESS pointing tool, and it also includes things like TESS footprints and position lookups and doing precise things for where a target was on a FFI at a given time. We've also revamped our TESS Point web tool online that you can interact with through our GI website, where there's some improvements under the hood, and also we've added some new like target observability things for upcoming cycles. We've been working on other tools to make proposals easier as well, things like tools to summarize tick information for a list of potential targets, and tools to take potential target lists and get kind of summaries to make sure that you're proposing for the kind of targets that you think you want to. And then finally, there's TESSVectors, what I'm here for. This is a product that really is intended to help you get your feet wet working with TESS engineering data. And I do want to highlight that all of the data that I'm going to be talking about here already exists. There's this bulk download section of engineering data en masse, and it's fantastic. But it can be a little difficult to start working with if you're not familiar with the mission, because there's a lot of different information in different files, and that information can be binned on different time scales. If we talk about things like quaternions, which you've heard a number of times today, like David previously, those are 2-second natively, while Earth-Moon information is binned on, I believe, FFI cadence, and there's other products in between. And so what we're really trying to do is take this information that is already publicly available and members of the community are already using, and just lower the barrier to entry and make it a softer touch to really start working with this kind of data. And so essentially we're combining multiple files worth of information into sort of easy to read CSVs that you can just read with pandas and that are binned to sort of the end user product cadences. So 20 seconds, 120 seconds, and whatever the FFI cadence was for that sector. And then crucially, this is all open source. So, whenever you're doing things like binning, you're making decisions. And if you disagree with the decisions that we've made, it's hopefully fairly easy to go in there and start tweaking knobs and making better decisions than maybe we did. So right now, TESSVectors has 3 large sections of information, let's say. The first is the quaternion information. So this sort of broadly speaking describes the pointing and stability of the satellite. And thankfully, David just gave a great talk about that. And so I'm not gonna chat about that too much. There's also Earth-Moon information. So this information describes the sort of bulk motion of the satellite and the expected scattered light levels across the sector. And Daniel Mitakrishna had a fantastic talk on Tuesday about why that can be so important for modeling scattered light. And then finally, we have some quality of life information that we've been including. This are things like the FFI file name for each cadence of like test cut TPF, so that you can sort of easily cross-match what FFI might have the data that you're looking for if you want to see what like large-scale trends or systematics are doing. As I know, you've probably heard the word quaternions a number of times at this conference. For those of you who maybe aren't familiar with, I apologize for my kindergarten level cartoon here. But essentially, when we're talking about quaternions, we're talking about unit quaternions that are measuring the translation of an ensemble of guide stars across the detectors. And I apologize if anything I'm saying here is not technically correct, Roland. But broadly speaking, there's 4 quaternions. We're mostly worried about 3, which is the translation in X, the translation in Y, and then the rotation angle of the system. And so we measure those from guide stars, and then they translate into movements of the spacecraft proper. Those quaternions are natively binned at the 2-second TESS refresh rate. And that means that if you want to sort of model products on other timescales, it can be a little bit tricky. So what we've been doing is sort of binning them down to end user products and having a variety of summary statistics incorporated there. So this plot here, these sort of dots in here are the binned individual quaternions across a 120-second exposure. This gray background is sort of the standard deviation of those quaternions inside of that bin. And then this bulk motion is sort of not to be concerned about. This is the essentially caused by differential velocity aberration and is dependent on the orientation of TESS's camera throughout that orbit. This is very similar to a lot of plots you'll see if you check out the data release notes. We just haven't removed the differential velocity aberration. We've also been working on creating some like essentially periodograms from the raw quaternions in case you're curious if there's some signal of interest on some timescale and you're wondering if it's systematic or not. And I think the thing I want to highlight with these is two things. So this is sort of a snapshot year by year. And one is that they started out more jittery and have gotten smoother over time. And this is sort of expected. There were things like implementing momentum dumps and other improvements that have really sort of taken this initial occasional spike to behavior and kind of smoothed it out. And then, so this is a kind of a time varying concern. And so these are maybe most interesting in some ways if you're working on early data or data with really long time baselines, or that exist in some of these sections where maybe things got a little bit more tricky. And I'm really not here to tell you how you should detrend with these. There are a lot of people who have written excellent papers on this, and David was just talking about this as well. I really just want to say that you can and that it shouldn't be intimidating. We have a very simple demo describing a linear model where you can basically, take some data, calculate a background, and then look at the statistics from that background, and then show that incorporating some quaternions can really help remove long time scale systematics from this. The other thing we have in these files are what we call Earth-Moon diagnostics. These are from the EMI files on that engineering documents. And so if you think about TESS, it's in this sort of P/2 resonant mission orbit. And the Earth and the Moon positions relative to the spacecraft and the cameras vary significantly during an orbit. And this can significantly affect things like scattered light. Again, Daniel has much better videos of this than anything I'm showing. And TESS actually has videos on YouTube of how the scattered light varies over the course of a sector that I'm not including on this one. And again, we have some sherbet flavored diagrams that are similar to what are already in the data release notes. And I want to take a quick aside just to say that there's two different reference frames that we talk about sometimes. There's spacecraft, which is kind of relative to the midpoint, and there's the camera reference frame, which is relative to the camera bore site. And you might want, particularly for the EMI, different reference frames depending on what you're doing. One big use case for something like the spacecraft Earth-Moon information is selecting really dark frames. And you care about that because when the Earth and the Moon are below the spacecraft sunshade, you'll get rid of most of the scattered light. And so a happy number we've heard is less than about -5 degrees. And so if you apply some simple cuts, you can pick out some timescales that have very low median flux values in your TPFs. On the other hand, if you want to do a more detailed model, you might care about the camera bore site of the camera reference frame, because that's what's going to affect the scattered light reflections when the Earth and the Moon are above the spacecraft frame of reference. And so this is kind of a toy plot showing how you can take the Earth and the Moon information and kind of reconstruct their positions relative to the camera bore site throughout a sector. And I just want to say we kind of have this in what we're calling open beta mode at the moment. The software is all available on GitHub, and the files are all available on the TESS GI website, in what are effectively glorified CSVs that you can read with Panda. We also have a very lightweight API to abstract this and make it a little bit easier. And we just would love if you let us know what you think, if there's any information or functionality that you might like to see that's not included. And I want to give a call out to the fact that the exact location of the files and contents might change. That's part of the reason for this API to abstract the information, but the updated details will always be on GitHub and the TESS Science Support Center website. Thank you very much.
All right, thank you, Tyler. Any questions in the audience? Yep, right over there.
Tara Featheroff, UC Riverside. I was especially interested in those dark frames. That's the first time I've seen those. How long are those typically? And I realize this varies greatly depending on the time of year, but what's like the short end of those that less than -5 degrees, and what's like the longest you can get?
You know, that's a great question. I don't have the summary statistics. Roland might actually have a better idea than I do. I would say that the range that we've heard suggested for these is like between -2 and -5, depending on the details of the orbit and pointing. Yeah.
You can have very dark sectors, especially if you're pointing south. And some of the very early sectors pointing north had very limited, just a few days worth of really, really dark. But it turns out, as you picked up, the really dark frames are really useful. There's a lot of good stuff you can pull out of that.
Thank you, Rolla, for letting me phone a friend.
Any last question? All right, I don't want to hold you from the coffee break, which is imminent. Let's thank Tyler again.
Thank you.
All right, everyone, welcome back from the coffee break. We're going to go ahead and get started with the next session. I'm Nicole Skinke. I'm part of the TESS Science Support Center, and I'll be the chair for this session. Now we're going to move on to some of the synergies that TESS has with other missions, starting with existing missions and kind of moving on through the afternoon with future missions. So we'll start out with Vikash, and he is going to be talking about TESS and CHEOPS.
Thank you. Hi, everyone. I'm Vikash Singh. I'm a research fellow at the INAF Observatory of Catania, and that's in Italy. We have a small research group that is associated with CHEOPS there. That includes Isabella Pagano, Gaetano Scandariato, Giovanni Bruno, and myself. First of all, I would like to thank the organizers for giving me this opportunity to present my work here. That was associated with CHEOPS, where we observe the occultations of Kel-20. It's an ultra-hard Jupiter, Kel-20b, revolving around the giant A star with an effective temperature of, let's say, 8,800 Kelvin. So that's something. Yeah. Okay, here it is. I'll give you a quick look on what CHEOPS is. So CHEOPS is a small-scale ESA Swiss-led space telescope that was launched in December of 2019. Unlike other exoplanet discovery missions that includes like CORO, Kepler, K2, and TESS, CHEOPS is a follow-up telescope where we observe the already known systems to better characterize their, let's say, the system parameters or the atmospheres of the planet. TESS finished its nominal mission last September, and we entered into the extended mission since then. And there is a tentative extended mission 2 that would go until 2029. So brief summary, CHEOPS is a high precision photometer with a 300 millimeter effective aperture size, and it has a single CCD detector with a wavelength coverage of from 330 nanometer to 1100 nanometer. So I would like to publicize this. So every year we have this guest observer program where 20% of CHEOPS time is being dedicated for observers from all around the world. So feel free to apply for it for your exoplanet sciences. It starts in early spring, so March, and the results are announced in April every year. Let's go. Yeah. So quick look on the sky visibility. So CHEOPS is in a polar orbit around the Earth at the day-night around the day-night terminator, and it is pointing away from the sun at a sun exclusion angle of 120 degree. The target should be observed away from the moon at an exclusion angle of 5 degree, and also it's advised to avoid the stray light with an exclusion angle of 35 degree. So the target needs to be above the horizon for at least an altitude of 100 kilometers. At the same time, we also avoid the SA passage. That's the South Atlantic anomaly. Okay, so I'll go through. In the nominal mission, we have an occultation program where we observe the hot Jupiters and ultra-hot Jupiters at their occultations, or that's secondary eclipses. I'll go with occultations henceforward. The key goals of this science mission was to observe the high precision occultations of hot Jupiters and ultra hot Jupiters in order to characterize their atmospheres, search for reflective objects, and in some certain cases, since we have the precision is so profound that we could see temporal variability. So that was one of the science goals. So this is how the data looks like. We observed 7 occultations of Cal20b, 4 in the first 4 in year 1, and followed by 3. You can see the individual fits on the right. And on the left, it's the combined fit. As you can see, we reached to a level of including the 7 occultations, we reached to a level of like 6 ppm in precision. So that's quite good. Come on. So TESS also observed the target in 4 of its sector. That's 14, 40, 41, and 54. So TESS year 1, year 3, year 4, and TESS year 2 when it observed the northern sky, year 4, and year 5. On the right, you see the individual phase curve fits, and on the left, it's the combined fit. One thing to notice is the eclipse depth or the occultation depth is more in TESS. That will come up later. Why? Because it's in the redder part of the spectrum, and I'll discuss it later. So one thing, what TESS and CHEOPS was good in, there is one good application if we observe certain targets simultaneously together with CHEOPS and TESS, and this system was the best example of it. We observed in the first year when we observed Cal20 with CHEOPS, we found this increasing slope in occultation depth, and that was quite weird for us. So we went to look at the TESS data. Coincidentally, fortunately for us, TESS observed the same. TESS was observing the target in that year, and at the same time, it observed 2 of its sector that year in sector 40 and sector 41. And we found a similar upward trend in the TESS data as well. And that led to us to again follow the same target in the following year, where we observed 3 more occultations, and we found, as you can see here, so the visit 6, which is quite, the depth is quite large as compared to the others. So at the end, we presented this result as a tentative signs of variability, which is this is a great testament of such observation where we can do this kind of variability studies with two telescopes with simultaneous observations. This could be later followed with, this could be later used also with TESS and Plato. So I'll move to other synergy case where we could measure planets. We can disentangle planets' brightness when we observe the same target together with the 2 telescopes. So if you observe a single occultation, then the planet's we have one single information, that is the occultation depth, which is the measure of the planet's brightness. But this brightness is a degenerate combination of the reflected light from the star and the stellar reflected light from the planet and the planet's inherent thermal emission. So we can parameterize this reflected light with a parameter called geometric albedo, AG. And we can parameterize the emitted light by the planet's blackbody temperature or brightness temperature. It goes by this formula. I don't know if anyone want to go through it, but it's here. So this is how the parameter space between this AG and T day looks like for a given occultation depth. This was a work done by Lexis and Tern in 2011. This was one of the Kepler targets. So if you observe the same target with two telescopes simultaneously, then we get 2 informations. That's 2 occultation depths. So this could help in breaking this degeneracy, but at the same time, it also adds 2 more parameters, which is AG for the AG and TD for the two telescopes, or the two passbands. This was an idea proposed by Eric Gaidos in 2017, where we could use the color information of the two filter band of CHEOPS and TESS to break this, let's say, reflection emission degeneracy, because the reflected light parameterized by AG and the emitted light parameterized by TD can be have different signatures in the based on the different. They have different signatures based on the color or the passband of the filters. So for 4 parameters, 2 observations. In order to solve this equation, we need 2 more assumptions, and we can assume a gray sky model where the planet is reflecting in a similar way in both the TESS and CHEOPS passband. And the second assumption could be a black body planetary spectral energy distribution in the entire CHEOPS and TESS passband. In doing so, we found this. So the 2 parameter space corresponds to the 2 telescopes, and the overlapping region is the region of interest where the gray sky model holds. And we were able to constrain the geometrical albedo and the brightness temperature of the planet Cal-20b, which in turn help us in disentangling the reflection and emission contributions. In this case, it was 3:1 in CHEOPS and 1:1 TESS, in TESS, like 50% each. So now, after let's say 10 years of such studies, we have a good hold of hot Jupiters and ultra hot Jupiters where such studies have been done, and we have AG and TD measurements of those systems with Kepler, TESS, and now with CHEOPS. This was a plot done by In Wong in 2011, where he presented the phase curves of multiple TESS planets, and we extrapolated that plot with CHEOPS, hot Jupiters and ultra hot Jupiters. As you can see, there is a positive correlation between the AG and TD. As we go hotter, the planet appears to be more reflective, which is not supposed to be, but this is what we get out of such plots. So begs the question, are Jupiters more reflective than hot Jupiters? And if so, then why? That's it. I would leave to the conclusions here. So we were able to characterize the atmosphere of Cal-20b with CHEOPS and TESS alone. I presented the work here with CHEOPS and TESS alone, but in the paper, we also use archival HST and Spitzer data. You can follow the paper with over here. We were able to determine precise occultation depths, more than 13 sigma in CHEOPS and more than 16 sigma in TESS. We obtained precise geometrical albedo based on certain assumptions. We were able to break this reflection emission degeneracy, and also this for hot Jupiters and ultra hot Jupiters, a geometrical albedo of more than 2, it's considered to be quite reflective. They're not supposed to be that much, but it's considered to be reflective. And at last, we found tentative signs of temporal variability. This also illustrates that this temporal variability could be because of atmospheric variability in the planet, where in the paper we presented that it could be since the night side is quite colder, so clouds can form over there and they get advected towards the day side where it gets burned. So the reflection, the planet is being reflected is reflective for certain seasons, and then for certain seasons it's not. I'll just leave to that. Thank you. Thank you for your attention, and I'm open to questions.
All right, thank you. Are there any questions? We have time for 1 or 2 questions here.
Aviv Ofir from the Weizmann Institute. You said that the correlation that you found is unexpected.
Okay.
And you also said that in order to reduce the number of free parameters, you had to assume something about the sky, for example, gray sky. Do you think that by changing the assumption, you can do away with this correlation? Maybe this is correlation is a result of the assumption?
Okay, that's a good question, actually. So as you can see here in the plot, we have presented both all Kepler, CHEOPS-TESS data, even though the colors are different. So, in a way, one of the assumption, which is a gray sky assumption, it holds true here because we have a single AG value. It's not a spectrum. So this value holds true for all the passbands. So certainly, if we change that assumption, we'll have different AG values for Kepler, different for TESS, different for different telescopes. I have a separate slide for that, as you can see. But for that, we need extra information. If I can see the slide. Oops. It's the one at the second last. Sorry, I don't think it's visible. So certainly this is an assumption, but we are coming from the observational side. We have this much information, 2 occultation depth into, so we have to assume something. But if you have extra information from, let's say, from infrared observations, we can certainly constrain let's say, the temperature. Once we do that, then we have information to constrain the AG for the different passbands, which would be a different value. So of course, given how this degenerate situation this is, we can do as best as we can. Yeah.
Okay, I'm afraid we ran out of time for questions, but any other questions that you guys have, we can put on Slack, or we can meet up after the break, and we'll make sure for the speakers to check the Slack channel to see if you have any additional questions. All right, our next speaker is going to be Chris Mann. Oh, yeah. And Chris is going to be telling us about NEOSSat and ORACLE.
Microphone, pants, good. So hi, I'm Chris Mann. I'm a postdoc at the National Research Council Canada up in Victoria, BC. My main postdoc research is actually in a direct imaging instrument, but I hope you don't hold that against me. I still do transit science on the side with the NEOSSat instrument and the ORACLE program, which we'll talk about today. So probably don't need to belabor this, but TESS does a lot of great things. Full sky survey, fantastic. Bright stars, fantastic. There are a few things that are drawbacks of its sort of program. Relatively short baseline makes the longer period stuff a little more challenging. Low spatial resolution requires a fair amount of follow-up. And this follow-up is done by a pretty dedicated group, which I'm a part of, the follow-up observing program, where we observe additional times to constrain parameters, estimates, and clear false positives. But I'm mostly going to talk about this sort of refining and uncovering unknown periods, which is an important part as well. So life is pretty easy when you have a nice string of uninterrupted detected transits. You get a good sense of the periodicity. You can fold them together to get good signal to noise fairly simply. You can get a sense of the TTVs if you can measure the variations between them. It's a little more challenging when, in a more realistic sense, you have gaps in your data, particularly if they are large gaps. So if the duo case we've been hearing about a fair amount, if you catch a transit in one and a transit in the other, you don't know necessarily how much you've missed in the middle. It could be a p/2 alias where you've missed one, or a p/3 where you've missed 2 of them, or any other integer there. The baseline can constrain that a bit, but often these gaps are large and you don't really know what you're dealing with. But you at least have some sort of discrete options, but you do have to check them all. Oh, I went too fast. It's a little worse even when you only have a single transit, because you basically don't even have this discrete system of periods to check. It's a continuous, fairly unconstrained problem. So this is where I think, I spoiled the result there. NEOSSat can really jump in. And what is NEOSSat? I've said it a few times. So this is the Near Earth Object Surveillance Satellite. It's jointly built and run by the Canadian Space Agency and Defence Research Development Canada. made to basically monitor, Earth's local environment. This is artificial satellites as well as, near Earth asteroids and things. But more recently has been sort of converted to general observing, where I'm now pointing it the other way and looking at far away things. It's currently only open to Canadian PIs, but that may change in the future. But I've also been working with a lot of international groups as the sort of Canadian face on the programs to do some really interesting stuff. And probably most importantly, competition has been very low so far. So I've gotten a huge number of hours on the Space Telescope, which is kind of a rarity to have this vantage point for so long. And that's what I'm kind of leaning on. So what is it? Yeah, small telescope. 15-centimeter aperture. There's no filter wheel on it. We just sort of rely on the natural sort of response of the CCD. It's on this polar orbit, and the baffling allows you to point fairly close to bright objects like the sun, moon, and the Earth. It's an aging instrument. It has foibles, it has quirks. It doesn't always work exactly as you expect it to, but with the sort of huge access of time and long baselines we can access, there's some really good stuff. So why would I choose exoplanet science with this instrument? Well, there's challenging targets that we all want to observe and to learn more about. And there's a few reasons a target might be challenging. One might be it's just technically a hard target to follow. Low signal to noise, small planets, grazing planets, faint host stars, stellar variability, these sort of things make it just hard to pull your signal out of the data. A second reason might be programmatic reasons, right? A long duration transit. If your transit lasts 12 hours and you want some baseline beyond that, that's very limiting on which observatories can give you quality data for that. Long periods, if you're waiting 400 days for your next option to come up and the weather turns bad, that's a major issue. These uncertain and unknown periods, you don't know exactly when to point. That's a really hard sell to most telescope tacks. You say, it's gonna happen this week. Can I have all of it? It doesn't usually fly. Or if away from the CVZ, sort of the odds of TESS revisiting and catching something might be quite low. So this is the second category that I think NEOSSat can really help out with. So let's really just jump in. And so this is sort of what I've been doing with it. Long transits where I know the period, but there's sort of 20 to 30 hours to watch. Alias options where you can sort of point, when to look, but you don't know which one will show something, but being able to point at any given time and not worry about weather and daylight and sort of prescribed hours has been helpful. And then window search for when you have a really long period uncertainties, where you just have a large uncertainty region that you want to check. So I'd sort of been doing these observations piecemeal for a while, but now I've sort of since recently wrapped them into what I'm calling the ORACLE program, the Orbit Refinement and Alias Confirmation for Long Period Exoplanets. And in this program, I'm going to sort of set you through a few showcases of some of the things we've done. So the first sort of major success we had with NEOSSat was the TOI 2010, which was a big part of my PhD research. Situation was a single TESS transit, had some RVs to provide a period estimate, but the uncertainty on that period predicted like a transit window of about a week on the 2 sigma level. So we, it's hard to ask for, but NEOSSat gave us a shot, and we, saw it basically exactly where we were expecting pretty much. And with the timing sort of precision here and the photometric precision from the single TESS transit, sort of folding these together, we got really good parameter estimates on the sort of the whole system. Similar system, but a little more ambitious. This is working with, well, we've gone too far. No, I just switched the order. The different system is not a TOI, but it is observed in TESS. This was a system that had a large variability, and it was periodic on sort of 100-something days, but really, really deep as like 80% flux drop. And it had this really jagged structure, but kind of looked like a transit, kind of repeated like a transit, visible in TESS and some ground-based observations. We jumped on the bandwagon and sort of observed it with NEOSSat as well. And again, saw this sort of variability structure changing over time. Some features are disappearing. The depth was shrinking. So what is this object that is sort of stellar in scale, but planetary in mass? There's a few RVs to sort of limit the mass there. Sort of best idea floating around at the moment is maybe this is a disrupted planet, something that experienced like a catastrophic event, a massive collision, and there's some sort of debris field that's evolving in time, and we're basically watching it evolve over sort of a four-year timescale, which has been really, really cool. I'm not the PI, but I've been sort of helping out with this. Similar to our first case, so this is another TOI, a bit more ambitious, working with Diana Dragomir here on TOI 429. Similar initial situation, we have a test transit, we have some RVs, gave us a period, gave us a transit uncertainty. This was much wider, this is like a 20-day window. We did exactly that. It's a little hard to see, there's a red region in the middle where we had an unfortunate scheduling conflict, but we did manage to get a decent amount of data, less smoking gun conclusive at this point, but there was a few hints. And while we were sort of sitting on and thinking about this data, TESS actually reobserved the system and was able to rule out basically all the second half of this sort of period posterior. So we reobserved the first half and lo and behold found another something that lined up exactly with our little hint before. So this is a really good indication that we had sort of found something, and this was again verified from the ground afterwards. So all of a sudden, nicely nailed down ephemeris, and these targets are now available to other observing facilities because you don't have to ask for half a month to observe them. And then finally, I'm going to quickly go over sort of the last showcase of 1861. So this is an example of this alias hunting where we've talked about this a bit, where you have, a transit here and a transit there, and you don't know what you've missed in the middle. There's all these options of periods. TESS was luckily able to limit this a bit with the baseline we had around these two transits, where we knew the period was at least longer than this P over 13 option. So with a bit of a TESS campaign, NEOSSat campaign, we checked up some of these different options where we saw no transits in some and we saw transits in others. But with the 5, 10, 15, we saw nothing. Was able to rule out some. With the 7, 14, and 21, ruled out some more. We did catch a transit on the evens. So we're able to validate the evens and rule out the rest of the odds. We ruled out 8. We ruled out 6 and 9, or 6 and 12. Now we're just left with 2 and 3, and some ground-based observations was actually able to help out and catch the P over 4. So again, a nice nailed down period and a system that has now entered the catalog instead of just sort of languishing in limbo until something can be figured out. So that's pretty much all I want to say on the topic. I'm going to leave this slide here as a bit of a plug for myself. This is a side project of mine. It's sort of extra research time. I don't have a huge amount of sort of time and resources to dig into new planets and new targets. Please come to me if you have an interesting science case. If there's a target you think NEOSSat would be great for you, leaning on this wide baseline coverage is really sort of the strength here. We don't get to quite the precision that CHEOPS was advertising, but on a good day, we sort of get 2 to 3 PPT. And it doesn't have to be this kind of science, right? I'm sure a lot of you will have ideas that I'm woefully ignorant of. Happy to collaborate, happy to help out. Yeah, just send me an email or chat with me for the rest of the conference, and I'll just leave it at that. Thanks.
Thank you. Does anyone have any questions for Chris? We go blue first. They're both blue.
Hi, Chaz Beichman, Nexi. So if you have, say, a very long period, a long transit, and you see be half an hour on, then 90 minutes off or something, how well can you piece together, being down in the bottom of the transit for many hours and get in the end, a full transit piece together?
Yeah. So I have a few examples which I did not show in these slides where, with 3 or 4 different visits of the same transit, and you could probably sort of visualize it from sort of these, right? If we were to sort of piece all these together, if they were all transit detections, you start to fill these gaps. And this is really where having like a long transit is helpful, a long signal, because yeah, we would lose things in certain gaps for the shorter objects. But I've done exactly that, where you fill out a nice transit because we got 3 or 4 visits. It's going to depend on the depth as well, whether you see anything. Yeah.
Thanks, Chris. Eric Itis, University of Hawaii. What's the typical turnaround time from going for proposed object to actually the observations? Is it a yearly cycle or
so
DT?
Some might call it flexible, some might call it disorganized. They do sort of on average a 6-month cycle. but this is a flexible boundary because sometimes they're not ready. It's run by a very small team, sort of, extended missions beyond what it was, planned to do. A lot of the work that I've done with people is they just piggyback on the existing programs I have, and we just sort of slot it into, I have a sort of fairly general program as well as a few specific programs. There's often an opportunity to just slot it in there. And I'm not really, it's a bit weird. They don't just give me a set number of hours, they give me a priority on my proposal. And basically, there's no hard limits on the number of hours. So there's a lot of time available and we can do these large searches. Often, they schedule a week in advance. That's the tightest deadline. But, with a month or so lead time, we could probably figure something out. If you want to do a bigger project and make an actual proposal of it, that's maybe on the sort of 6 months timescale.
Okay, one more question right here.
You basically look outward, so it's midnight for configuration. What's sort of the target availability?
Sorry, could you repeat that?
What's the target availability? Are you basically just looking anti-sun?
For the most part, yeah. So we can point within, I think it's 40 degrees of the sun and 20 degrees of Earth and the moon. And then, yeah, it's a mostly polar orbit beyond that. So the gaps you see, unfortunately, even when you do have a sort of continuous viewing angle, one of the foibles of the instrument is its momentum desaturation and target acquisition are pretty slow due to past hardware failures that have some ingenious fixes. So we do see gaps like this kind of regardless, but yeah, that's kind of the pointing restraints.
All right, let's thank Chris.
Thank you.
All right, up next I'll be hearing from Conny Aerts, who will be telling us a little bit about TESS and Gaia.
All right. Good morning, everybody. My name is Conny Aerts, and I'm bringing you a story today of a very successful marriage between Gaia and TESS. And so this is about massive star asteroseismology. When I say massive star, I mean all stars born with a convective core. That's my definition, right? You see my collaborators here on the screen, and I will happily show them some, well, I will show their faces as we move along. So let's go to episode 1. Most of you may use Gaia to have a good position in the HR diagram, but Gaia also provides light curves, sparse light curves that have a long baseline. Now, this is very different from TESS light curves, but you can do asteroseismology with the combination. So here on your left, you see a graph of the Earth-Sprung-Russell diagram with more than 100,000 points indicated of stars where the Gaia light curves have told us that these are non-radial pulsators. And so you see also the instability strips for one choice of input physics where these stars are supposed to lie. Now, why do we care about all this? Well, because people like astroseismologists care about improving stellar models. And the weakest point of stellar models is that the transport processes, and I mean both angular momentum transport and chemical element transport, also called mixing, are very poorly calibrated still. So on the right, you see the achievements of the Kepler satellites, 4-year long data, and you see core rotation plotted as a function of the evolutionary stage. And there are about 1,800 stars in that diagram, but we really don't know very well how the stars transport and then lose their angular momentum. Now, the key thing in this diagram is all these gray and purple stars on the main sequence, they are only covering a mass range up to 9 solar masses. So we really want to go up to higher masses as much as we can. And that's where Gaia comes in, because these more than 100,000 stars are also observed by TESS, but now we know where they are, okay? And so Dan Hay has already shown this diagram in his review talk. He did a magnificent job in creating light curves, or in analyzing light curves of 60,000 of these stars. And you see plotted here the Gaia frequency on the x-axis and the TESS frequency on the y-axis of the two most dominant frequencies. And you can see that they agree pretty well. TESS has some trouble in aliasing frequencies recognition. Gaia doesn't have that at all, right? And so this is a very important key result because it allows us to go from like a few hundred stars to several tens of thousands of pulsators in the upper HI diagram. Now, as a side remark, aside from science in this slide, I'd like to take you a little bit into the house of asteroseismology. We astroseismologists, we care about people. We are an inclusive community. I'm proud of having created it like that. And we also acknowledge that we need to help each other and celebrating when we have important events. So I am now going to invite you to celebrate with us and together with some of my assistants on a very important event. And Dan, stand up, please, because Dan Hay is turning 30 today. And I want to celebrate. Happy birthday to you. Happy birthday to you. Happy birthday, dear Dan. Happy birthday to you. Hip, 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 hooray! And enjoy the birthday cake at lunch then. So this is how the astroseismology community works in general, okay? Family and human activities first and then science. Right. So another thing that Dan did, and I have it on my badge, which means it's important, is make a stacked periodogram you see on the right of gravity mode pulsators. Now, these are stars that have modes that probe the very, very deep interior of the star, and then has made a stacked periodogram, and you see a beautiful ridge appearing. Now, such a ridge is expected from theory and from Kepler stars to reveal the mode identification. Because for us, in massive star astroseismology, labeling the modes is really a stumbling block. That's very different from low mass stars. And this ridge is telling us that the majority of these stars actually have a prograde dipole gravito-inertial mode. What does that mean? It means that the period of the mode is about the same order of magnitude than the rotation near the core of the star. So it allows us to see straight into the deep heart of these stars. And so in this diagram, as you can see, are more than 5,000 stars. We had up to like 700 from Kepler before. So this is really great that TESS can deliver us after Gaia tells us where they are, right? And in the left diagrams, you see the amplitude distributions of these stars in the four groups they belong to. So pressure modes on the left, delta Scuti stars and beta Cephei stars, and on the right, Gamma Dor and SPB stars, okay? So when you move on to the higher masses, as I want to do, I'm starting with episode 3 now, and there are more than 100 new beta Ceph stars discovered by Gaia. You see them plotted here in a Hertzsprung-Russell diagram where I've indicated the instability strip. This is work led by Dario, who is on the left, and Matthijs, my PhD student both in Leuven, on the right. And what you can see, again, the nice thing about Gaia is that it has a homogeneous data set with lots of parameters treated for all stars equally. So the dominant frequency of these stars clearly connected to the V broad parameter. And the V broad parameter in Gaia is defined as the upper limit of the spectral line broadening. So that's connected to the rotation of the star in a projected way. And you clearly see that there is a strong correlation. It's not tight one-on-one. It should not be. It cannot be. Why? Because rotation shifts the frequency of the mode, but it depends on the azimuthal order of the mode, how much is being shifted. And so you see that reflected in this graph, right? Now, what can you do more with Gaia? And this is something that works better than I had anticipated, even though I'm a very optimistic person. Gaia has multicolor photometry. TESS does not offer that. So when you want to identify modes, there used to be a technique that we used long before space asteroseismology about amplitude ratios, because it gives you a hint on the type of mode. And you see that reflected in this diagram on the left. Orange points have L equal 2 modes. These are quadruple modes. Blue points are stars with dipole modes. And red points, green points are radial pulsators among the beta Ceph stars. So actually, by combining the TESS amplitude with the Gaia amplitude, we can do mode identification. And this has been bothering people like me for more than 25 years in order to do that. So this is really a good way to look ahead. Having all that, we also have rotational splitting in 48 stars so that we can deduce the envelope rotation in these massive stars. And you see that on the lower right. There is differential rotation up to a level between 1 and 4 roughly, but mainly between 1 and 2. Angular momentum transport theory has a problem with this. So we need to tune it better. And while we have 48 stars now, it's going to upgrade a lot. Moving on, what can asteroseismology also do? Give the mass of the convective core. And so here you see that plotted as a function of the evolutionary stage. Is this what we expect? Yes, because the convective core shrinks as the star lives its life. I can tell you why if you don't know, but not right now, to stay within time. And so what we see is whether it's radial pulsators, dipole or quadrupole, they all behave as expected in terms of convective core. And moreover, we have asymmetries in the rotational multiplets. And that allows us to access the internal magnetic field that these stars may have. I have no time to go into that, but my student Vincent, who is in the audience, has a beautiful beta Cephei star, and he can explain you all about that, even having in hand the very first massive supernova progenitor, as I call it, that may have a strong internal magnetic field. Go talk to Vincent, who is sitting over there. In the last coffee break, you still have time if you haven't done that during the poster sessions. Okay, let's move on to these gravity mode pulsators. Here they are in a Hertzsprung-Russell diagram on the left. Every gray dot is a star, and these stars are compared with evolutionary models that have been calibrated by the Kepler Gamma Doradus and SPB stars. And if we then compare that with what we expect from the initial mass function, like a plain Salpeter function, you see that plotted on the right. So this actually tells us how efficient the mode excitation mechanism is. Flux blocking for Gamma Dor stars works really well, according to the number of stars that we find. The heat mechanism, also known as the kappa mechanism, does not successfully excite modes in every star. And now we have more than 10,000 stars to compare it with, instead of just a few hundred that we had from Kepler. So given that we're only working with DR3 right now, DR4 will be coming up, and we will do this type of science for really many, many, many stars. Another thing that is fantastic is that Gaia gives an excellent dominant frequency of a dipole gravito-inertial mode, as we have shown, and that is sufficient to actually derive the rotation frequency in the very deep core of the star. You see that expressed here. The rotation frequency is plotted as a function of the dominant mode, where the Gaia limit is 4 millimag. That's fine. Gaia wasn't created to do asteroseismology at all. And so you see a very nice trend. That means that as soon as you have a dominant mode frequency, and as soon as you have your star confirmed to be a pulsator, you immediately straight into the heart of the star, see how it rotates. I still find that amazing when I think of it. This is work I'm right now doing with Timothy, and since I have to hurry up because I did a little party in between my talk, here is a confirmation that these stars really behave as we expect them to be, and allowing us to do really asteroseismology in the next future. So I will leave up my slides, you can read them, but DR4 TESS is going to be fantastic, and Plato even more so. Thank you for your attention. And congratulations again to them.
Yeah, thank you so much for the overview. Does anyone have a quick question for Connie? So I'll ask a quick question. So you've been talking about DR4 and how that's going to happen. What is the difference with DR5? There's going to be more light curves available. Is that correct? Or what?
It's going to be better light curves.
Yeah.
Above all, DR4 will have all the time series, so the whole community can play with that, and that's going to be a major improvement, and it's going to give rise to millions of stars instead of thousands. DR5 is going to be an upgrade, I think, mainly in the quality of the data, and perhaps some better objects that weren't handled properly in DR4. We have limits on orbital periods that we can have, on pulsation periods, so very long pulsating supergiants, for instance, etc. Okay, we don't have a date yet for DR5, by the way.
Any other quick questions, David?
David Charity, NEOSSat. So first of all, I'm glad I wasn't your student when I was 30. Thank you, Connie. More seriously, can you start to, with these data, can you start to measure the rate at which the core begins to contract as the stars age?
Yes, if we do population studies, that's the whole point. So the plot that I've shown where you saw this decrease of convective core mass, the convective core mass at each stage of the evolution is directly connected to the chemical mixing, which is what we are trying to calibrate. And so that allows us to derive internal profiles of what we call the mu gradient, the mean molecular gradient. And that's what we are after. For now, we haven't analyzed the TESS data in detail. We're just checking are the trends as we expected them to be, so that we can dive into this work into the future. And thanks to the TGLC producers of light curves, by the way, because these are great. I forgot to say that.
All right, let's give one more round of applause for Connie, and a big one for Dan for his birthday. All right, next up we have Mayuka Mori, who's going to tell us a little bit about TESS's work with some ground-based observations.
Maybe it's not. Okay. So hello everyone, thank you so much for giving me this opportunity. I am Mayuka Mori. I am a postdoc at Astrobiology Center in Japan. So today I'm excited to talk about our recent research, which was published early this year. And the title is Multiband Star Spot Characterization by Synergy of TESS and ground-based telescopes. So as all of you already know, this is transit, but what will happen if there are unocculted star spots during the transit? So in this case, the planet passes over a relatively brighter area on the stellar surface compared to what we would expect without star spots. Then it results in deeper transit observed. So this intuitively illustrates how star spots influence to the transit depth measurement. So, so in reality, the effect of star spots is much more complicated because they work differently at different wavelengths. So this is transmission spectroscopy, transmission spectrum of super-Earth GJ486b observed with JWST. And they say the signal can be explained by the water-rich atmosphere on the planet. But at the same time, the signal can also be explained by the unocculted star spots, even if there is no atmosphere on the planet at all. So now with the incredible precision of JWST, it is the era that the effect of star spots is much more important or more problematic than ever before. So this effect of star spot is called transit light source effect, which was first mentioned in Rackham et al. 2018, who gave a talk on the first day. So the effect of star spots is expressed by the epsilon lambda over there. And epsilon lambda is calculated from three important parameters. T-spot, photosphere temperature, and T-spot, spot temperature, and F-spot, spot covering fractions. So these three parameters are important or the fundamental characteristics of star spot. But spot characteristics have not been fully investigated, even observationally or theoretically, especially for M dwarfs. So we don't know typical spot size or typical latitude dependence of spots, or we even don't know typical spot temperature. So sometimes spot temperature is inferred from the relationship between photosphere temperature, according to these kind of empirical relation. But this relation is mainly based on the results from solar type stars or earlier type stars. And there is a lack of data set for the stars below 3,000 or 4,000 Kelvin. So the purpose of our study is to put observational constraint on spot characteristics, especially T-spot and F-spot of M dwarfs. Another option should be is spectroscopic observation, but we wanted to do it with less observational cost. So rotational modulation is important. As in some of previous talks, when the star is brightest, there is less spots, and when the star is faintest, there is more spots visible. And from this rotational modulation, we can put constraint on these three parameters. And for T-spot, we have some reasonable assumption or reasonable prediction from the spectroscopic observations or something. But for T-spot and F-spot, they are completely unknown values for now. So if you only have one light curve, like from Kepler or TESS, then you need to put assumption to each of these values. So multi-band light curves comes into play. So if we have multiple light bands simultaneously, then we can break the degeneracy of these two values to some extent and then retrieve them simultaneously. Our target is K225 system, and it is adolescent mid-M star in higher disk cluster, which has transiting sub-Neptune K225b. And K225 was known to have 1.88 days modulations. So we chose this star as our target. One is because knowing about the star spots on this system should be important or useful for future atmosphere research on K225b. And other reason is that its continuous modulation is useful or made it best candidate or best test case for evaluating our method. So what is important in our research was simultaneous multi-band observations. So we used TESS and ground-based telescopes simultaneously. So when TESS was observing K225 in sector 44, we conducted intensive observation using LCO 1 meter telescopes with Sinistro camera. So having different observatory at different locations on the Earth, we were able to conduct intensive photometric observations. Oh, sorry. So this is what we had. So along with TESS and Sinistro dataset, we also use archival data from ZTF in G and R band. So at last, we were able to get 5 different light curves in 4 different bands simultaneously. So after period search and phase folding, this is our phase folded light curve in 4 different bands. So you see clear rotational modulation and different amplitude in the modulation. And this difference in the amplitude is important to infer spot parameters. So this is what we got, amplitude and their uncertainty. And this amplitude AB at each band is calculated from can be calculated from F-spot and CB, spot contrast. And spot contrast is converted from T-spot and T-spot through some model. So we are able to constrain spot parameters from comparing amplitude and these equations. So this is our posterior distribution of the parameters. In our fit, we use parameters as F-spot and delta T. Delta T is the difference of star spot temperature compared to the photosphere temperature. And we were able to put a 2 sigma upper limit of delta T is 190 Kelvin, and F-spot is under 61%. And it is better constrained than previous research. So from until here, I was just explaining the method obtaining spot characteristics from only solely on amplitude, but we also tried spot mapping to get a general distribution of the stellar spots. So in our method based on Ikta et al. 2020, we actually place the spot on the stellar surface and measure the stellar brightness at each rotational phase. So in this fit, we use parameters as spot latitude, longitude, radius, and temperature for each given number of spots. So the lines in the bottom figure shows our randomly chosen best fit light curves coming from the converged MCMC chain. We tried spot mapping with 2, 3, 4, and 5 spot cases. And from our result, 3 or more spot cases showed better fit compared to the 2-spot model. And 3, 4, 5 models that does not have a specific difference among them. So here, I would like to emphasize that we did not intend to get a unique solution of spot distribution, but rather we tried to graph the general characteristics of spot distribution. So from here, I want to say I'm believing that the spot case 3 or more, 3, 4, 5 spots, this demonstrate the general characteristics of spot distribution, and it seems K225 has spot on the middle latitude, not equatorial, not polar. So this is posterior distribution of spot parameters from spot mapping this time, and what we learn here is result with in spot more than 3 show general trend of spot distribution, and derived parameters posterior distribution of parameters were consistent with results from amplitude, which confirm the robustness of our method. So from here, I would like to discuss what we learned from our study. So first, I would like to emphasize the effectiveness of multi-band monitoring. To demonstrate this, we tried spot mapping with only using TESS light curve and using all 5 light curves, comparing the result. So you clearly see the best fit light curve is different. And incorporating multi-band light curves narrows down the possible model range and results in better constraint on spot characteristics, especially spot temperature. So ground-based observations is ground-based observations have like less photometric precision and less observational cadence compared to TESS, but still they are very useful to constrain spot characteristics. And also, after we get spot parameters, we can of course estimate transit light source effect. So this is the contamination factor epsilon lambda from our reasonable T4 to T-spot and F-spot value. Of course, we are not able to constrain spot covering fractions, which is not contribute to modulation, which means always visible spot. But still, having this kind of photometric precision, photometric constraint on spot parameters allow us more reasonable transit light source effect estimation for future atmosphere research on this target. And finally, this is another implication from our study. It is a relation between photosphere temperature to spot temperature. So this is the figure shows a relation of T4 and T-spot, focusing on the spot temperature, photosphere temperature below 4,600 Kelvin. And the blue line shows a commonly used empirical model to calculate spot temperature. And gray points show the data set which was used to calculate empirical relation, and colored one is more recent result, including ours. So looking at recent result, it seems like delta T value tend to show smaller values compared to the empirical relation, which means the spot temperature of M dwarfs could be more closer to the spot photosphere temperature. So this is still preliminary result. So we would like to add more data points to the around M dwarfs to applying our method to more stars to update this relation, because this relation is very important to infer transit light source effect. So this is summary, and you can find our paper in the QR code, and I will take any questions. Thank you so much.
Awesome. Do we have a question?
Great talk. Thank you. Dom Odo from the University of New Mexico. It seems like these spot models are fairly observationally driven rather than driven by stellar physics. And I'm wondering if there's anything in terms of stellar modeling that can help us constrain these observational models rather than kind of like the other way around, if that makes sense.
Yeah, yes, that's a great point. And I would like to say it's the theoretical understanding of star spots, especially for M dwarf, is still very limited. There is one paper about spot temperature, theoretically calculated spot temperature by Panja et al. 2000 something, sorry. And yeah, the result was consistent, but still, yeah, we need to investigate is this derived spot distribution is physically correct or not. Thank you so much.
Okay, thank you. Yeah, it seems like that's something we should be paying attention to as a community.
Yeah.
Thank you.
All right, we have one more question. We can get way up in the back. You guys can run a mic way up in the top section.
Thank you. Francis Wilkin from Union College. Of course, on the sun, when we look at sunspots, we see the penumbra and the umbra. So I wonder whether it would make sense to model the spots with those two regions with two different temperatures.
So you mean, sorry, if I catch your question correctly, so is it reasonable to put only two temperature model for stellar surface, right?
Or is there evidence for the relative contributions of umbra and penumbra in star spots beyond the sun?
Sorry. Can you repeat that?
So would it make sense to model the sunspots as umbra plus penumbra?
Okay. Yeah. So there again with Panja et al. 2008 something from theoretical model, it is reasonable to think that the spot of M dwarf is more like a sudden change in the temperature. So the penumbra is not very distinct for M dwarfs. So and also adding penumbra for our model is just makes the model complex and maybe result in overfitting. So we didn't use it. Yeah, but maybe if we apply our method to earlier type stars like K or G dwarfs, then maybe we need to consider about penumbra as well. Thank you.
All right, let's give one more round of applause. And just a quick reminder, if you guys do have more questions about this, please go to the Slack and you can post them there and continue the discussion later. Okay, our last speaker of the session is going to be Dan Huber, and he's going to be switching things up and telling us about a future observatory with TESS.
Yes, thank you. Hello, everybody. So in the spirit of this session, I will be talking about synergies, but synergies with a future space-based telescope, namely the Habitable Worlds Observatory. And I'll try to convince you that TESS is an excellent tool that we have to precisely characterize the stars around which the Habitable Worlds Observatory will one day directly image Earth-like planets. So I want to thank all my collaborators. You see Dan Hay up here, but don't worry, Dan, I won't make everybody sing, although I'm very, very tempted. So just as a refresher, what is the Habitable Worlds Observatory? HW was the top recommendation for space from the Astro 2020 Decadal Survey. So it basically will be the next flagship mission from NASA. And the goal is to produce images such as the one that you see on the left, which is our solar system at around 10 parsec with the central star blocked out. And the goal is to directly image Earth-like planets in reflected light and study their atmospheres. There are other space-based efforts towards that road. Roman, for example, will be a technology demonstrator towards that goal. And there's also a European effort, the LIFE mission, that will try to achieve this using interferometric techniques. So one of the things that you might ask is, well, what do we actually want to know about stars around which habitable worlds will try to detect exoplanets? And one really important aspect of this are actually stellar ages. We want to know how old the stars and the planets are that we will detect. And I really like this quote, which is actually just a tweet of a quote from a meeting that is now many years ago, 7 years ago, the Ages of Stars meeting in Elba, Italy, where Dave Soderblom motivated the meeting by speculating that when life is found on another planet, someone will ask how old that life is. We know how old the life is on Earth, and we will want to know how old life is when we find it on another planet. But in addition to this sort of philosophical question, there's also a lot of science reasons why precise ages are important. For example, in this very nice paper from Daniel Apai's group a few years ago, they showed that this might actually be one way to unambiguously show whether things that we detect in the atmospheres of these planets are actual biosignatures. So this is a plot that's showing the fraction of inhabited planets with detected oxygen as a function of age. And if life is common in our universe, in our solar neighborhood, we would expect a positive correlation because we know that on Earth, for example, the oxygen abundance increased with age. And one of the reasons why that happens is because there's life on Earth. And so if we actually measure oxygen abundances on several planets, and we know the ages of these stars precisely, and we see a positive correlation, that might be a smoking gun that life is common in our solar neighborhood. There's another aspect about these stars that we want to know, and those are the orbital inclinations of the planets. This is more sort of a practical thing, actually, because as you can see from these two examples of directly imaged planets that we know of, on the left, Beta Pictoris, and on the right, HR 8799, the orientation actually matters for the detectability. You can clearly see that if you have a face-on system like HR 8799, it's easier to detect the planets because they're always visible than for an edge-on system like Beta Pictoris, where the planet goes behind the star in the inner working angle where you can directly image the planet. So we want to know the orbital inclinations of planets around nearby stars. That may be able to be possible with astrometry over time, but we can also use the spin axis inclination of the stars as a proxy for this. So in a recent paper led by a graduate student, Aloisi A, we actually showed that the host star inclination of the stars that host directly imaged planets correlates quite strongly with the orbital inclinations of the planets themselves. A lot of these measurements, actually, the inclination measurements, were made using TESS data. Now, these planets are very massive and the stars are very young. They're unlike the planets that we want to find with habitable worlds. But if this tracks to lower masses, we may be able to use spin axis inclinations as a prior to the orbital inclinations of planets. So what are the stars that habitable worlds will observe? So there's several target lists out there. This is one example. This is an HR diagram, radius versus temperature, of a selection of stars that were put together by Eric Mamachek and Carl Stapelfeld. And you can see immediately that these are sun-like stars, right? Our sun would be around here. So these are stars with spectral types F, G, K, and a few M stars. And so the question then is, how can we measure ages and inclinations of these stars? Now, if you would ask any stellar astronomer in the room, they would probably agree that the age and the inclination of a star is probably two of the most difficult things that you might want to measure around the star. So how are we going to do this? Now, the good news is that all of these stars are incredibly bright. And of course, that makes sense because they have to be very close in order for us to actually directly image planets in the habitable zones at this close inner working angles. They have to be at distances that are close to us. And because they're so bright, many of them are basically naked eye stars, sun-like naked eye stars in our solar neighborhood, we can bring the full force of stellar astrophysics to bear on them and actually make these measurements. And two of the most powerful tools, this will come to no surprise to some of you who know me, to do this are asteroseismology. We've heard a lot about asteroseismology already this week. The study of stellar oscillations. This is a power spectrum of the sun showing these, the Gaussian power excess that is typical for solar-like oscillators. But also gyrochronology, which is another powerful tool, measuring the rotation periods of stars. And in this case, these are rotation periods as a function of temperature for different clusters of different ages, and using the spin down of stars over time to measure their ages. So both of these techniques can measure ages. They can also measure inclinations, and I'll touch on that a little bit at the very end. Okay, so what's the data that we will use? So TESS 20-second cadence data is really fantastically suited to do this precise characterization of habitable worlds observatory targets. One of the reasons for this is that TESS 20-second cadence data gives us the best photometric precision for the brightest stars. This has already been mentioned earlier in the week. This is a plot from a paper a few years ago now, where we show the scatter of the 20-second cadence data bint the 2-minute cadence divided by the scatter of the corresponding 2-minute cadence light curves. And you can see that the brighter the star is, the better the 20-second cadence photometry performs relative to the slower cadence. And in particular, for the brightest stars, exactly the ones that habitable worlds will observe, we're getting something like 20 to 30% better photometric precision. And you can see this by eye in this phase-folded transit light curve from Pi Men C. So this has enabled a treasure trove of astroseismic detections in nearby sun-like stars. As a reminder, I'm showing you the power spectrum of the sun. This is what the sun looks like. So you're looking for Gaussian power excess with regularly spaced peaks centered at around 3000 microhertz. It's about 5 minutes in period. So here's one example, Beta Virginis, a nearby sun-like star, and you see the power excess and the regularly spaced peaks. And we now have more examples and more examples and more examples. We have a whole gallery. These are all nearby sun-like stars, 5th, 6th magnitude stars, for which TESS 20-second cadence data has yielded fantastic astroseismic detections. Many of these are basically just single sector detections. And for a lot of things that we want to do, we want multiple sectors and longer time series. And just to show this explicitly, here's an example of one of such stars, a multi-sector power spectrum of a nearby sun-like stars. And I just want to pause so we can all look at this power spectrum and how amazing it looks, especially hopefully the astroseismologists in the room will agree. If those of you don't look at power spectra all the time to make you hopefully agree that this is amazing, here's an example of the very best of Kepler. This is 16 Sig A, one of the nicest detections we have from the Kepler mission. We're not quite there yet, but you will hopefully agree that this power spectrum and this one both look very high signal to noise, and we can do a lot of great science, in particular measuring ages with this data. Okay, so one of the things that you might have noticed is that the astroseismic detections from TESS, even with 20-second cadence data, go down to about late G-type stars, but not to the K-dwarfs. And that's because the amplitudes get even smaller, and even with TESS 20-second cadence photometry, it becomes very hard to detect oscillations in photometry. But there's a solution, and that is to use extreme precision radio velocities. Now, luckily for us, there has been, of course, a revolution in terms of developing these instruments. In particular, 2 instruments on large aperture telescopes are now available to do this. This is Espresso on the VLT, which has been up and running for a while, and the Keck Planet Finder, KPF, on Mauna Kea, which has been commissioned last year. And for those of you who missed it, oh, sorry, one slide too early. So we've started fast cadence observations with KPF. Last year, this is the first light observations with KPF of doing astroseismology. KPF has a fast readout mode. You can read out the entire CCD in 15 seconds, which is really well suited for astroseismology. In fact, in this time series, this is a couple of hours of RVs on a sun-like star. You can see by eye the 5-minute P-mode oscillations. So KPF has now been up and running for a year, and as I've mentioned, in case you missed it, yesterday was KPF Day on the archive. About 30% of all exoplanet papers in the exoplanet category were from KPF. We've heard a lot of the results already this week. We had a talk from Nick Saunders and Stephen Giacalone yesterday. There's also a poster by Jingwen Zhang. All of these deal with Rossiter McLaughlin measurements of exoplanets. But there's another poster down here, the last paper here by Mark Hahn, that presents the very first astroseismic results from KPF. And these are on Sigma Draconis, which is a nearby sun-like star, a K0 dwarf. And so in the top here, you see the power spectrum from the KPF observations showing the clear, nice power excess. In fact, TESS has also detected oscillations in this star. This is probably the coolest that TESS will ever be able to get. And we also have a simultaneous detection with TESS. This is the coolest star for which we've detected oscillations with both RVs and photometry. Now, colleagues in Europe, led by Tiago Campante, have used Espresso to actually push this to even cooler stars. This is the detection of oscillations with Espresso on Epsilon Indi, a mid-K dwarf, and we will be pushing to cooler stars also with KPF. So to go back to the HR diagram and wrap it all up, I think there are really good prospects for doing astroseismology and measuring precise ages. And for precise ages, I mean something like 10%. You can ask me afterwards how realistic this is if you'd like. But for about 90% of all Habitable Worlds Observatory targets. The F and G type stars will be done by TESS, perhaps also with CHEOPS, but TESS 20-second cadence data is really exquisitely matched to this. And the K-dwarfs will be done using EPRV instruments such as KPF and Espresso. So I didn't talk much about inclinations. Inclinations are harder, but they're not impossible. So this is some work that I did with Jen Van Feders at UH, where we looked into the feasibility of doing this. You can measure inclinations using mode splittings from astroseismology. You need a long time series to do this. You could do it for a few of the FGK stars, or F and G type stars that rotate fast enough. For those that we can't, we may be able to use rotation periods, V-sin I measurements, and radii to infer their inclinations, and stars that are amenable to this based on predicted rotation periods are shown at the bottom. It's harder, but it's doable, especially if we get really long time series. Okay, with that, I will put up my conclusions, and I will finish with the main message, which is that there are really, really good prospects of precisely characterizing stars for the Habitable Worlds Observatory, but it will require dedicated long-term campaigns. The RV data that's required is not trivial. We need several nights per target to do this. There are many stars, and I can go into detail on this in the Q&A if you'd like. So these need to be designed now, so by the time that Habitable Worlds flies, we have the data to do this. And of course, TESS needs to continue operating. Imagine what we can do with 10 to 20 years of TESS 20-second cadence data on the nearest, brightest sun-like stars around which we will hopefully detect or reflect planets. Okay, with that, I'll stop. Thank you.
All right, any questions? Got one right here. Yep. I think she's coming from the other way. Yeah.
I'm wondering, why do you get smaller scatter for the 2-minute average of the 20-minute integrations compared to the full 2-minute integration?
Yeah, good question. There was a bit of discussion on this early in the week. I can go back all of it. So the reason for it is essentially how the cosmic ray rejection is treated. So for 2-minute cadence data, the cosmic rays are automatically rejected on board, and for 20-second cadence data, the cosmic ray rejection is done on the ground by the Spock pipeline. And essentially, the onboard reduction is a little bit too aggressive when it rejects frames that are actually due to pointing jitter rather than cosmic rays. The members of the TESS team can go into more detail, and the reason why it is more severe for bright stars is because the pointing jitter matters more the brighter the star is.
So it's the method of averaging that is the difference between the 2-minute continuous. It's the method of averaging that makes the difference.
Yeah, I mean, it's a matter of the treatment of the data. So right, if you would assume that they're both the same, then if you average 20 seconds to 2 minutes, then this should be 1, right? So these should all be at 1 because it's the same amount of photons, but that's not the case. So it's a matter of post-processing.
Okay.
And one more quick question we'll do over here.
Daniel Bayless, University of Warwick. I was just wondering, for the ages of these systems, does life get easier for all other things being equal for an older sun-like star than a younger sun-like star in terms of the asteroseismology getting parameters out? So like if it's at 8 gigayears, are you more accurate than if it's at 3 or 2 gigayears?
Yeah, so there are a couple of layers to this question. So one is that for very young stars, asteroseismology struggles just from a detection perspective, because activity actually acts to suppress the convection that drives the oscillations. So the youngest detected solar-like oscillator we have currently is from K2, actually in the Hyades, so it's about 800 million years. So if you go much younger than that, it becomes very hard to detect the signal. But for any sort of old star between 1 to the age of the universe, we can do well, and there the precision basically is related to the main sequence lifetime. So the fractional precision is actually set by roughly about 10% of the main sequence lifetime of a star, because what asteroseismology measures, the reason why we get the age is because we measure how much hydrogen is converted in the core into helium. But roughly sort of saying 10% between 1 and 12 gigayears is not a bad assumption. That's basically as good as we can do. Yeah.
All right, I think that's all the time we have for questions. So I saw a couple more hands, so make sure to go to that Slack channel to ask those questions. All right, let's give Dan one more round of applause. And a quick round of applause for all of the speakers in this session. I think Avi has a couple more announcements before we scatter for lunch.
Okay, so before we go for lunch, I want to announce the winners of the poster competition. But before we do that, I want to say a few things about, we had a competition for a best post on Twitter or X. We looked through it yesterday. We didn't find any specific or single post which clearly blew everything else out of the water. So instead, what we decided to do is to note the most active Twitter or tweeters. There are 2 people who were more active than others on Twitter. And the first is Prisi Karpur, who is a grad student at UC San Diego. This is her handle on Twitter. You can find her there. And here is some of her posts. My favorite is this one from the by Dr. Jonathan Chow from the Mental Health in Academia talk on Tuesday afternoon, which seems so long ago now. The second one I would like to note is Paul Mooney, who is a science writer. Here are some of his posts. I think thanks to him, practically every speaker has a picture on Twitter now, and this is only really some of it. His Twitter handle is Moon, so I really wonder, how did you get that one? I mean, that's oh, okay. So thank you both for Prisi. I hope I'm pronouncing it correctly, and to Paul, who making the conference much more noticeable on Twitter. So thank you for both. Now for the posters, we have two honorable mentions. You can think about them as two runner-ups, and then the winner. And we prepared a nice certificate for them. So the first honorable mention is Owen Mitchum, who is an undergrad at, I forget the university, I apologize for that. He just left about an hour or two ago, so we will figure out a way to send the print of this print to him. This is his poster. He basically led the effort of building an observatory at his campus as an undergrad. So definitely someone to keep an eye on in the next few years and beyond. So though he's not here, let's have a round of applause to Owen. The second honorable mention is Theron Carmichael, who I hope is here, but I don't know that. Yeah, you can come up. This is Theron's poster. This is actually a photo of Theron's poster, so it's not the best quality, but what I like about this one is I don't need to tell you what this is about. You can just see it. And it will make you go talk with him and ask about all the details. So come on up. I want to embarrass you completely. Thank you.
I would have dressed nicer, but
yeah.
Thanks, Avi.
Take pictures. And the winner of the poster competition is Javier Viana. I hope I'm pronouncing it correctly. I do not think he's here, right? Some local MIT people can tell me if I don't think he's here. Anyway, this is his poster. So this is clearly, I mean, right? The science and the design all come together, and this is beautiful. So congratulations to Javier. So we will also find him next week and give him this certificate. And this is it with the poster. You can go see the posters now during the lunch break. I wanted to announce this now so you can still have some time to talk with the poster presenters and go see these posters and the rest of the posters over the lunch break. And we will reconvene here at 1:30.
All right, everyone. Welcome to the second to last session of the conference. Today, we're going to hear about more exoplanets, and we're going to start off with a talk by Mallory Harris from the University of New Mexico. Mallory, take it away.
Okay, we lost some of the nice fonts, but okay. Hi, everyone.
My name is Mallory. I am a fifth-year graduate student at the University of New Mexico. We'll be on the job market in the fall. And today I'm going to talk to you about microlensing with TESS. And I'm going to take a guess on what all of y'all's thoughts were, well, most of y'all's thoughts were when you saw a microlensing talk in this conference, or at least the transiting people. I mean, it's not the microlensing exoplanet survey satellite. That would be a mess. These are the jokes. But TESS actually is presenting a unique opportunity to study microlensing for reasons that I'll go into over the course of my talk. But just to really quick go over what finding a microlensing planet entails. When a lens star, which is the one with the higher proper motion, a foreground star, overlaps with a background star, it causes an increase in the flux of that background star that we can measure with TESS. Now, in this reference frame here, we are showing it from the lens reference frame. So if the source is the one that appears to be moving, and that will be continuous throughout the talk, just fair warning. But when we measure that light curve, we get this kind of bells-like shape called a Pajinski curve. And when there's a planet present, the gravity of the planet will also cause a slight peak in the light curve as well. For all, if this is still how you feel about microlensing and you have no idea what I'm talking about, don't worry, I will tell you when to be excited. So many of us will be familiar with this figure, this projection of the TESS, what TESS has observed over its primary and first two extended missions. And to move this into Cartesian coordinates, we can see that there's a kind of top hat shaped gap here, which includes the galactic bulge. For microlensing, this is a little bit scary that TESS hasn't gotten there yet, because microlensing requires that two stars overlap along our line of sight. And while the crowding in, say, a region along the galactic plane would look like this, when you go more towards the bulge, you can see that there are 2 orders of magnitude more stars in this range. And thus, the expected output of TESS is on the order of none. However, TESS does have some potential to find microlensing planets. We'll start with the cons. The first is TESS is not observing the most crowded field of the sky. I've already said that. But TESS also has huge pixels, 2 orders of magnitude bigger than those that Roman will use to do microlensing. TESS thus has a much higher background flux threshold that we need to overcome with high magnitude events to observe them. And it's also kind of hard to resolve exactly what star is experiencing the microlensing event. However, there are some benefits with TESS. For one, with its very eccentric orbit, it has the potential to measure the parallax just with its own observations of a microlensing event, which allows us to resolve the mass ratio discrepancy and measure the true mass of a planet candidate. I believe that this may be possible for the nearby stars that TESS is most equipped to observe. And most importantly to me, TESS has an observing cadence that is unparalleled. Even Roman will not touch that 200-second cadence. And for me, kind of made me think. So what can we do with TESS? Well, let's break down what kind of microlensing events we can see. Well, microlensing events are like onions, like ogres. Here again is the lens reference frame. You can see here, and over here we'll show the light curve with the source star tracing out its shape. To begin with, when the motion of that source star relative to the lens star perfectly overlaps, we'll see a higher magnification event rather than when it's occurring more along the periphery. This ring here is called the Einstein radius, and it's basically the distance out to which that gravity of that lens star can impact the flux of the source star. So the further into the upper edge, the limbs, as it were, of the Einstein ring, the lower the magnification. However, there is another input that we need to consider where there are finite source effects. The source star is not a point source. Rather, its angular size can be comparable to that of the Einstein ring. And when it is, this can cause either only parts of that star to be magnified at a time, resulting in a curving and less magnification, or it can result in a higher magnification when the star is more along the limb of the Einstein radius. So to begin with my work, I started looking for events like this with no planets, just microlensing. And what I found when I looked into the TESS observations, and you can see TESS sectors marked out here with the big brown cubes, and the OGLE, KMT, and MOA fields, which are the ground-based microlensing surveys, marked in the light green, brown, and dark green fields. What I found is that there is some overlap with TESS. While it's not observing the bulge overall, it does get kind of close. So when I went and looked for high magnification events that occurred when TESS was observing a field of view that were alerted by KMT, MOA, and OGLE, I tried to see, can TESS find any microlensing events? And here's what I found. Several, including my personal favorite. This is when you go ooh and ah, because this is really cool. This is KMT 2021 bulge 0940. That's a mouthful. But what we can see here is real limb darkening effects, where we see a great curving of the peak of the Pangensky curve. We see that there's a slight offset maybe of when the peak of the event occurred. And when we compare that to the KMT observations, which you can see here, we can see that because of TESS's time resolution, we can actually get a lot of information from this light curve. So that answered my question. TESS can do microlensing events. Now, can it find planets? Well, my team started looking for these events after we used the ground-based surveys, by looking at Gaia transient alerts. What we found in the first case was this event that occurred kind of near the galactic plane, slightly off of it, in a not very crowded field where we don't actually expect to find many microlensing events. And when we looked at this event closer with TESS, we saw this beautiful Pangensky curve, this beautiful microlensing event, and a peak that we thought could be a planet. This was really cool. This was really exciting. But unfortunately, our ooh and ah guy has to go away now because this was a flare. But what this told us is that even though this was a flare, if it had been a planet to fit this model, we would have been able to observe it with TESS because it has that time resolution. This occurs on the order of 45 minutes. Roman would get 3 points. So why did I think that this could be a planet? When there are two bodies in the lens system, we get what is called a caustic. These two Einstein rings interact, and there is a certain shape created by their mass ratio and the separation between the two objects that comes out of this, that comes out of the light curve, that tells us that occurs when the source star crosses into this caustic. When it crosses in, the magnitude goes to infinity, or theoretically, and when it stays up high, and then when it crosses out, it immediately drops off and starts falling off again after peaking. So when we measure these weirdly shaped light curves, we can get an idea of the mass ratio and the angular separation between a host star and its planet. And what's great is that these are very characteristic to microlensing. There's no flare that's going to come in and disguise itself as my ogre and tell me that I did not find a planet when I find a caustic crossing event. So we kept on our search. We kept using these Gaia observations. And what we found was this event that again occurred along the galactic plane in sector 64. And when we looked at the TESS observations, boom. Ooh, ah, this is really cool because we're seeing a definitive caustic crossing event. This is beautiful. And what we think the source star is doing here, based on our model, is crossing through this caustic in this way, as you can see here. From this, we are able to extrapolate. And just to show you how great the TESS time resolution is, you can see how we have multiple points in these peaks. These occur along the order of like 2 hours, 2.5 hours, and no one can touch the time resolution. And by having a good idea of these finite source effects, we have a good idea of have a good idea of the angular size of the source relative to the Einstein radius. From using magnitude observations, we can get an idea of what type that source is. And then moving along, we can continue. And eventually, if we find the distance to the source star, resolve the separation between the lens. We can determine the Einstein radius and potentially get some more information about that lensing star and its planet. So having this time resolution is so important to really understanding a planetary microlensing event. So when we expand this model, we can then measure out the properties of this planetary system, namely the planet to host star mass ratio and the angular separation between these two objects. But I wanted to show you as much as I could about this really cool system. So I used the PyLMass software, which is made by the same people who allowed me to do these beautiful modeling. And to use a Gaussian mixture using the magnitudes and the proper motion of the source stars to hopefully determine what exactly this planetary object might be. And these are very preliminary results. I'm going to say that now. Was doing this very excitedly, trying to prep it for y'all. And what we found is that this planetary object is probably about 23 Jovian masses. So maybe a brown dwarf star in this case, but we can do this with TESS. We can find these planets. And when I continued over the, and you can see where the Gaussian mixtures converged from these histogram plots for the Lynn star. But recently, as in 4 days ago, I was also able to incorporate another sector of TESS observations into my model. This is sectors 63 and 64 combined, giving us a larger picture of what's actually going on in this event. And from that, we got a new microlensing cosmic crossing model that kind of tells us that maybe that has very similar shape to our original, but is much more narrow, telling us that this is potentially a much longer event and with a much smaller object. If these results are correct, that 23 Jupiter mass object goes down to 8 and into the planetary regime. So these are very preliminary results. I literally ran the model yesterday, but it's still very exciting. And my next steps will be to include the Gaia observations that we have into this model to see if maybe we can measure the parallax between Gaia and TESS with these events. So whether or not microlensing are the exoplanet ogres is up to you. I hope that I've shown you, though, that you don't need to beware them so much. They are much more approachable ogres. And I will leave this slide up and take your questions. Thank you very much.
Any questions for Mallory? We have mic runners in the back. Oh, never mind. Go ahead, Stephen.
Which one? Me? Thanks, Mallory. So this is really great work. Oh, by the way, Stephen Keen, UC Riverside. So as you know, including the baseline is really important to modeling microlensing events. And it looks like you probably have quite a few events that have characteristic timescales that are comparable to the length of a TESS sector.
Yeah.
And I was curious if your system of detecting and modeling these is advanced enough that you could actually alert on some of these and have ground-based observations catch the end and really nail down that baseline.
So we haven't looked into that yet, but I definitely would be very excited to do that. Right now, we are going back to the archival Gaia alerts. So by the time we actually get to the TESS observation, like incorporating the TESS observations, it's usually been a little while since it actually occurred. But I would be very excited to try that, especially when to try setting up a pipeline that could be alerted to these events. I just haven't gotten there yet.
Yeah, maybe for some of those where the characteristic timescale is significantly longer than a TESS sector, but you still see it, then there'd be enough time. But yeah, great work. Thanks.
Thank you. And if anyone would like to pay me to do that, I will be on the job market in the fall.
Would there be any benefit of combined simultaneous Roman and TESS microlensing, since TESS does have the much better cadence?
I believe so, especially in the current, when such things as those kind of horn shapes come out of the light curve when the cosmic crossing events, because as you saw, TESS gets great time coverage of those, and Roman would only get maybe 6 points. And that allows us to kind of model it out much better. However, it would have to be a high magnification event because, like in the case of this event, we are starting to approach kind of that background light pollution threshold. So it's kind of harder to get the baseline with TESS. But if in a case of a high magnification event, I do think that the better cadence with TESS would be very beneficial, yes.
Questions? Any final questions for Mallory?
Aviv from the Weizmann Institute. Can you look for them independently of other alerts?
Not at this point. I would definitely love to do a demographic survey with this. I'm especially interested in looking towards the large and small Magellanic clouds in the continuous viewing zone where there may be more overlapping objects. But we haven't gotten there yet. I would love to do it as a postdoc, but not just at this point.
All right, let's thank Mallory. So while we're waiting for our next speaker to get her slides up, I forgot to make a couple of announcements in my excitement to start the session. First of all, next poster break or next coffee break is the final time to see posters. At the end of the coffee break, please take down your posters. And the other announcement is that our final talk of the session is canceled. Unfortunately, the speaker is ill and won't be able to present. So we're going to take our time a little bit during the session and hopefully get you to coffee break a few minutes early. With that, our next speaker is Sydney Jenkins from MIT. Go ahead, Sydney.
Hello. So I'm Sydney Jenkins. I am a rising fourth-year graduate student at MIT working with Andrew Vanderberg. And today I'll be talking about JWST follow-up of a TESS planet called WD 1856. And this also happens to be the first planet found transiting a white dwarf. So first, let's start out a bit closer to home. So this in our own solar system. So this is our star, the sun. If we zoom out a little bit, we can see those inner rocky worlds. So in a few billion years, the sun is going to expand, engulfing many of those inner planets. And in the process, it's also going to expel most of its outer material, leaving behind just the core remnant called the white dwarf. So these white dwarfs are the leftover stellar remnants that are no longer undergoing nuclear fusion reactions, and they are extremely dense. So they have a volume comparable to the Earth, but a typical mass of around 0.6 solar masses. They also represent the end state of evolution for around 97% of stars. But despite this, their planetary systems are very poorly understood. So we only know of a handful of white dwarf planets, even though theory suggests that any planets beyond around 1 AU should survive the transition off of the main sequence. So this raises an important question, which is what exactly is the fate of these post-main sequence planetary systems? And one of the ways that we can try to answer this question is with TESS. So a few years ago, there was a program dedicated to searching the TESS data specifically for white dwarf planets. So to learn a bit more about this discovery process, stay tuned for Bob's talk later on. But for now, I'll just say that in 2019, TESS observed a very special white dwarf called WD 1856, and this is what it saw. So this here, you can see this is an 8-minute transit event, and follow-up ground-based observations revealed that the transit depth was around 56%. So what type of system could create such an unusual light curve? Well, it might look a little something like this. So here we have this super small white dwarf and then this large companion orbiting at around 0.02 AU. It's around 25 parsecs away, and from the white dwarf's temperature, we can estimate the age of the system to be around 6 billion years. As for the planet, it's estimated to have a radius of around 10 Earth radii. This makes it around 7 times larger than the white dwarf. And so the mass is where it gets particularly interesting. So here you can see this is just an upper limit on the mass. And this is coming from the original discovery paper, which used a Spitzer data point at 4 to 5 microns to try to constrain the thermal emission from the companion. And because it didn't detect any thermal emission, it was able to constrain the companion to be in the planetary or the low mass brown dwarf regime. But if we want to better characterize this system and we want to actually confirm that this is in fact a planet, then we need additional follow-up. And that's where JWST comes in. So in the first cycle, there was not one, but there were 2 programs that were accepted specifically for following up on the system with MIRSpec. So the first program was using PRISM, and it was led by Ryan McDonald at the University of Michigan. The second one was using the grading G395M, and I'll just refer to that simply as G3 from now on. And this one was led by Andrew Vanderberg, who of course is here today. And there were some similarities between these 2 programs. They're both cycle 1. They shared a common main objective, which is to constrain the mass of the planet and the formation history of the system. Of course, some differences as well in the wavelength coverage, the resolutions, and also the primary methods of the 2 programs. So measuring the transmission features versus detecting thermal emission. So before we take a look at this data, let's think a little bit about what we expect to see. So if the companion is contributing more at longer wavelengths, then we expect to see a corresponding decrease in the transit depth at those wavelengths. So this would look something like this gray dashed line here. And if we also toss in the Spitzer data point that I was mentioning earlier, noting again that this is averaged over 4 to 5 microns. So this makes it a little difficult to tell whether the companion is actually contributing any flux at these wavelengths. So let's now also add in the G3. So this data was taken from 1 hour of out of transit and 1 8-minute transit event, and it was reduced with the Eureka pipeline. You can see that around 4 microns, that we're starting to see a bit of a decrease in the transit depth corresponding to emission from the companion. And we can also model this data with a cloudy, cool planet model at around 260 degrees Kelvin. We can also compare this to the PRISM results. So this is PRISM data reduced with the Firefly reduction pipeline. You can see that in comparison, our G3 data ended up being a bit noisier. We had some unexpected noise and systematics on the red end. And also you can see a difference in the slope at these redder wavelengths. And so this corresponds to a difference in the estimated temperature of the companion. So if we want to investigate what's driving this, one of the things we did was look at the different reduction decisions. So if we instead reduce the data with, for instance, the Juniper pipeline, which was done by Abby Bam at Cornell University, you can see that we're getting another result with the G3 data. So this is something that we're actively investigating now. But from these spectra, we can start to get some takeaways. So they are roughly consistent with the original Spitzer data point. And also we are able to detect the thermal contributions from the companion. And so the facts that we're able to detect this indicates that this companion must be relatively massive. Though of course, we're still working to understand some of these discrepancies. But this still leaves us with the original question that I raised, which is whether it's a planet or a low mass brown dwarf. So one way that we can work to answer this is using a spectral feature at 3.4 microns. So this is a feature we see in our own solar system, specifically in Iron spectrum. We also see it in Titan spectrum. And it's been proposed that it's caused by either unknown hydrocarbons or gaseous ethane. So we can use it here to model our spectrum and estimate a mass. So what we find is a mass estimate of around 9 plus or minus 4 Jupiter masses. And for comparison, when the PRISM team estimated the mass using their retrievals, they estimated it to be around 7.4 plus or minus around 3 Jupiter masses. So these are 2 consistent and independent lines of evidence that this is in fact object is in the planetary regime. So now we can also think about how does this compare to other transiting planets that we know about. This mass actually places it in around the 98th percentile of masses of transiting planets, which raises the question, is this just an anomaly that this first planet found transiting a white dwarf is so massive, or is it perhaps representative of the demographics of white dwarf planets? Of course, can't really answer this question with a sample size of 1, but I'm going to circle back a bit later on. So now that we have the mass of the planet, we can also go back to one of the other driving objectives of the programs, which was understanding the formation history of the system. Specifically, how did the planet get to its current orbit, which is at 0.02 AU? So there are a few proposed mechanisms. There's the cosine mechanism. Specifically, there's actually an M-dwarf binary that's also part of the system. It's at a projected separation of around 1,000 AU. And so this could potentially be responsible for driving the planet to higher eccentricities. There's also potentially planet-planet scattering. So if there's a planet, an additional planetary companion of similar or more mass than WD 1856b, then it could have potentially scattered the planet. So I'll note that both the cosine mechanism and planet-planet scattering would involve high eccentricity migration and tidal circularization to get the planet to its current orbit. And finally, the third option is common envelope evolution. So in this scenario, the planet would have been engulfed by the envelope during the star's expansion as it transitions off of the main sequence, and then it would have rapidly spiraled inwards until the envelope was dispelled. So this would have probably required some additional source of energy in order to dispel the envelope quickly enough before the planet is completely destroyed. So now we can think about a few different lines of evidence for each of these. So for the first two high eccentricity migration scenarios, we generally expect planets to pile up at or beyond 2 times the Roche limit. So now that we have a mass estimate for the planet, we can calculate what that would be for this system. And what we find is that the planet is at around 4 times its Roche limit. So this is consistent with both of these scenarios. And then specifically for the planet-driven scenarios, we can start to probe the presence of any additional companions in the system using transit timing variations, or TTVs. So this was work originally done by Sarah Kubiak, who is a graduate student at Colorado State University. So in 2023, she gathered some of the data from 2019 and 2020, and she made this plot shown here. So this is showing the log probability for an additional companion of a given mass and period. And these purple regions here are the regions that we're starting to rule out. So now that we have additional data from 2023, we can make a new version of this plot. This is what we get. So you can see, for instance, an 8 Jupiter mass planet is constrained to have a period greater than around 3,000 days. So we're really starting to probe the regime where we would expect to find any additional perturbing companions. And hopefully if we get additional data, we can continue to improve these constraints even more. And then finally, for common envelope evolution, there have been a few studies discussing whether this would be feasible for this specific system. And generally what they find is that it would require the planet to be greater than around 5 Jupiter masses. And so circling back to what I was talking about earlier, which is whether it's anomalous that this planet is so massive. Well, if it got to its current orbit via common envelope evolution, then this is exactly what we would expect to find, is a very massive planet. And then I'll also just note that we have recently gotten data from a cycle 3 follow-up program with MIRI. And so this is work that's being led by Mary Ann Limbach at the University of Michigan. So if you're curious about the next steps for the system, then feel free to ask about this. And then I'll just leave up my summary slides and take any questions. Thank you.
Questions for Sydney? I see some over here on the right. let's do Josh.
Hi, Sydney. This is Josh Pepper from NASA headquarters. Really cool work. You mentioned about the anomalous nature of this system, which I think the anomalous nature of this system, which is very interesting in terms of the mass of the companion. But there's another anomaly that still puzzles me, which is that this is a very grazing event. It is only 56% or so eclipsed, which means that the configuration of the planet and the very small white dwarf, it's got to be much less than what 0.1% probability that you would only graze the disk of a white dwarf with a giant planet. So I'm wondering, is there anything that we can infer about this system from just catching it in that very particular configuration as opposed to a complete eclipse?
What we can learn about this system or more generally?
Either way.
I guess, yeah, so it definitely is, this is one of the difficulties, I suppose, with the transiting white dwarf planets that would make it difficult to find any more of them would be the slow transit probability. As for the grazing transit, I think there could be some potential to try to like leverage that to try to like study maybe like specific parts of the atmosphere maybe or something like that. I think some people have raised those points before, so those would be interesting to think about. But
it's about a 1 in 4 probability if it transits that it will be grazing, Josh. So a little bit suggestive, but not super suggestive. Yeah, Dan.
Hi, Sydney. Daniel Bayliss from the University of Warwick. I was just wondering if, because it's such a high mass planet, is there any chance that we can get radial velocities for the white dwarf? I realize it's very difficult and maybe there's no features to lock on for cross correlation, but the higher the mass of the planet, the bigger that signal, right? So is anyone trying that?
Yeah, so generally with white dwarfs, it's hard because they're like generally featureless, except for if they're helium or hydrogen dominated. So I think for this one, we just have a broad H alpha line, right? So yeah, I don't think that would be a real possibility for this system.
Hugh?
Yeah, Hugh Osborne at Bern. So you mentioned the grazing nature and the fact that you look for TTVs, but I would have thought with this grazing system that the real killer might be the depth variation if there's any change in the inclination of the orbit, or even maybe if the planet's changing size, because you can really probe the edge of the planet, right? So have you looked for any depth variation between just the white light curves from James Webb?
Oh, to search for changes in the inclination?
Yeah, either inclination or planet radius, potentially.
So yeah, that's a good question. Yeah, I guess we haven't looked for that, and I guess we haven't seen a difference between the PRISM and the G3 data. That would make us think that there is any changes going on like that, but I guess maybe if we keep looking, we can check it out.
Any final questions for Sydney? Catherine, over there. Yeah.
Hi, I was wondering if Brenham Center for Astrophysics. I was wondering if this is a free-floating white dwarf, or if there are any nearby companion stars also associated with the system.
Yes, so there is, well, the M dwarf binary that I mentioned earlier, that one, yeah. And with the original TESS discovery, the white dwarf was actually blurred with the 2 nearby bright M dwarfs. So that was also one of the challenges with the original discovery.
All right, let's thank Sydney again. And next up in our white dwarf doubleheader, we have Bob Aloisi from the University of Wisconsin.
Hi, thanks for giving me the opportunity to talk today. And I hope Sydney's got you all excited about white dwarf exoplanets, because we're going to look for more. I'm Bob Aloisi. I'm a rising 5th-year graduate student at the University of Wisconsin-Madison. And Andrew is also my advisor. I'm talking today about our search for orbiting exoplanets, orbiting white dwarfs, and on behalf of the team that you see here. As we talked about, white dwarfs are the end product of most stars. So the interesting thing here is, fun fact, almost all of the current exoplanets will end up in systems where the star evolves into a white dwarf. So I'd like to get you motivated. Why should we search for white dwarf exoplanets? Well, as we said, we want to understand how these planetary systems evolve over time. There's also a very interesting case scenario where a planet could move into a habitable zone around a white dwarf and be there for billions of years. So life could develop around planets orbiting white dwarfs. And if you look at the graph here of all of the planets we know, and we've seen this a lot this week, orbiting main sequence stars, we've got this one lonely guy populating a similar plot for white dwarf transiting exoplanets, and we'd like to see more so that we can learn more about the population. If you need more motivation, I'm a non-traditional student. When I decided to go back to school, I went to UW-Milwaukee to get a physics degree, to get ready for graduate school. I put in a space grant proposal to start a TESS follow-up observing program, and we bought a camera for this 14-inch telescope on the rooftop of UW-Milwaukee Physics Hall. The second night after we got that camera, we pointed it towards a known white dwarf transit with a red dwarf transiting it. And I'm going to show you a little bit of a movie about what we saw. Okay, you're looking at the star just above the red plus sign. And for about 15 minutes during that observation, the star disappears. These white dwarf transits are 100% deep at times, if they're not grazing. So the star disappears, and it'll wrap around and do it again here. So where we typically talk about the depth of the transit, indicating the size of the object, you can't really do that with 100% deep transit. So you'll hear me talk about the duration of the transit being how we are estimating the size of the objects. The way our survey is set up to work is we have a catalog of objects that we know are white dwarf, thanks to the Gaia mission. We're going to search light curves from TESS for transiting occurrences around those objects. And then, as you've heard about earlier during the conference, for the TFOP SG1 program, we're able to follow up from the ground using local telescopes at time to confirm that it is a planet. And as we heard in Sydney's presentation, if it is, it's going to be an excellent candidate for James Webb Space Telescope observations. You saw the 1856 system in Sydney's talk. My point here is just to show where the habitable zone is. This planet is close to the habitable zone for a cooling white dwarf star. And so it's not unrealistic to think that if an Earth-sized planet were to scatter into these tight orbits, it could be in the habitable zone of the white dwarf. This graph shows how the habitable zone changes over time as the white dwarf cools, moves closer and closer to the white dwarf. And for the red area with the 0.54 solar mass white dwarf, that habitable zone could last at a given orbital separation for over 5 billion years, which is longer than the Earth has been around. So it is possible that life could develop in this kind of a scenario. For our proposal, what we need is rapid cadence, 20-second and 120-second observations with TESS. And we need that to detect these transits, which are only 1 to 5 minutes in duration for an Earth-sized planet. The graphs that you see here are a simulated injection of a Mars-sized object into a 20-second cadence light curve and a 120-second light curve. And what I want to point out here is even at the 120-second cadence light curve, the signal gets smeared out by the longer exposures and get shallower and lower signal to noise ratio. And remember what this looks like because we've found some very similar objects in our survey. So what did we find? We found about 60 objects with durations less than 30 minutes. So in that regime where they could be exoplanets. And about half of those, when we research the objects, are known eclipsing binaries. And so you see here cataclysmic variables, red dwarf, white dwarf, and brown dwarf transits. And so we found quite a few similar sized objects that we're sensitive to that we know were there. I've also put the vertical dotted line here to indicate for a non-degenerate object what is the smallest period that you could have before the object starts to break up. And that's based on Saul Rappaport's hydrogen body paper from 2021. So in addition to these known objects, here are the candidates that we found. And we've done some vetting of these candidates, just the simple things we could do, looking at the SEDs and looking for infrared excess. If we found that, they're more likely to be a main sequence star or a brown dwarf. And we fit with the two black body models and looked at the temperature of the cooler body to differentiate between those two scenarios. We've also found some objects on very short periods that almost must be white dwarf binaries. But what I want to focus here is on the blue open squares here, which are 7 candidates that could be eclipsing binaries, but these are our best candidates, we think, for exoplanets. And they all have durations between 1 and 5 minutes in various periods up to 2 days. Here's some examples of the pipeline output, one of which is our known planet, 1856. And the top graph here is a periodogram showing a clear detection. Folding on that period in the middle plot, we've got a clear transiting shape. And if we zoom in on that shape in the lower plot, we see a very nice light curve for a transit in 20-second cadences using all TESS data. For an example of one of our candidates, its period is 0.57 days, and it's got a very short duration, meaning it must be pretty small, at 1.5 minutes, but it's a lot shallower transit. And if you notice in the details, this is a 122nd cadence light curve. So that transit is a lot shallower, but it looks a lot like what we might expect out of the smeared out data. To test the sensitivity of our pipeline, we did injection recovery results. And I'm sharing work here that a member of the team, Patrick Sellup, who's a postbac at UW Milwaukee, did. And we're looking at the fraction recovered for various planet sizes, ranging from a half an Earth radius to 15 Earth radii, and periods ranging from 0 to 4 days. And as you might expect, we recovered more of the large bodies on short periods and tapering down to fewer for small bodies on long periods. The range is like 0.3 to 0.85 fraction of the injections. So pretty good sensitivity, though, down to Earth-sized bodies. If we work that into an occurrence calculation based on the geometric probability of a transit plus that fraction, we know we found one planet out of 24,000 plus light curves that we searched. That's a fraction of about 0.4%. And then this is just to put a boundary on it. If we have 7 candidates, 8 detections would give us a 4.6% occurrence rate. And these could be false positives with a signal to noise ratio of 4 to 5, something like that for our detections. They also could be eclipsing binaries. So my bet would be that we're a lot closer to the top graph, but I'd be thrilled if one of the 7 turned out to be another planet. For next steps, our summary is that as we expected, white dwarf planets are rare. We found the WD 1856 fairly quickly, but we haven't found a lot of other candidates since. But now that we have those candidates, we've released them to the TFOP SG1 program for follow-up. And in addition to that, I've got a volunteer group of amateur observers and others that have been working with us for the last 2 years to vet some of the candidates. In addition to that, we're also finding some new eclipsing binaries, 10 main sequence stars, 2 that we think might be brown dwarfs, and a white dwarf. And we do have a TESS Cycle 7 GI program that we're anxious to hear about, hopefully any day now, about ongoing work. With that, I'll take questions, and I want to thank again the TESS team for creating this opportunity for us. Thank you.
Great. Questions for Bob? I see one over in the left behind Catherine. David.
This is Dave Mann, Tufts University. This is amazing. Have you done any follow-up spectroscopy? Is this in the pipeline, search for pollution, maybe some RVs even?
Yes, we just released these to do the photometry to confirm the eclipses at this point. But yeah, SG1 and SG2 for spectroscopy, we hope to do follow-up on over the next few weeks. Thank you.
Astrid, I see right, Mike next to you.
Mike Lund, IPAC. I was curious about the injection recovery that you showed.
Yes.
There's that one dark square. Is that statistically significant? Is there something that's representing that you're aware of?
Not that we know of. Yeah, we think that's just a normal or part of the variability. And in truth, we intended to do 10,000 injection recoveries, and I'll finish that. We just didn't get the whole set done. So hopefully that will smooth out as we get more data. Good question. Thank you.
Yeah, JJ.
Thanks, Bob. This is JJ Hermes from Boston University. So I want to kind of flip things on its head and say that, we only know of a few hundred white dwarfs within 25 parsecs, and one of them has a transiting exoplanet. So, maybe they aren't as rare as we think they are. We just have different selection biases. So you had 24,000 light curves that you searched, but what fraction of those would you actually be sensitive to 1% or a few percent deep transits?
So we actually did the injection recovery with the actual TESS light curves that we're searching.
So that represents all 24,000?
Yeah, randomly selected from those 24,000. So we believe somewhere between 0.3 and 0.85% fraction of those transits would be recovered.
Okay, cool. Thanks.
Any other questions for Bob?
Thank you.
All right, let's thank Bob again. And next up, we have Fintan Seles-Noile. Slides up here. You can take it away whenever you're ready.
Nice. Oh, skip the good part. There we go. All right, well, hello, everyone. I'm Fintan Seles-Noile from the University of Warwick, and I'm here to talk to you about what I've been working on with stellar multiplicity in the Neptunian desert using Gaia. Now, a little bit of a recap. I know a lot of you have probably already seen this, but the hot Neptune desert is this region of low orbital period, high planetary insolation, intermediate planetary size region, where there's traditionally been a dearth of planets despite orbital biases, observational biases favoring this region. Now, we want to know why this region exists, what's the nature of it, and how do we do that? One way we can have a look is by looking at system properties that we find these planets in. Now, a key option is host star metallicity. Now, we know that higher radius planets and lower orbital period planets should have higher host star metallicities, as shown by these plots here. You can see that there's definitely a trend towards that. And hot Jupiters, of course, exist in this corner of this parameter space. And it was also found that hot Neptunes share this property with their host stars. They also will have higher host star metallicities, as shown in this plot here, compared to ultra-short period planets, which are the smaller, lower than 3 Earth radii anomaly planets. Now, if these two planetary types, hot Neptunes and hot Jupiters, share these host star properties, maybe they share other properties as well, and could be a probe of why hot Jupiters are so commonly observed, but hot Neptunes aren't. Now, a key way of doing this is then to find another property of hot Neptune systems, which we can look for that hot Jupiters are known to have. And an obvious example is stellar multiplicity. And by stellar multiplicity, I mean wide companions here, not circumbinary inner double stars, but wider companions. And as we can see here, hot Jupiters, given by that darker line around 1 Jupiter mass, are seen to occur more often than other types of planets in multi-star systems. So if we can search hot Neptunes and find the same thing, it could be a promising result in terms of maybe they do have host stars that are drawn from the same distributions. Now, to do this, we use Gaia DR3 astrometry to perform common proper motion and equidistant searches to look for wide companions to these exoplanet host stars. And the reason is because, I mean, I'm preaching to the choir here, really. Gaia has 1.5 billion 5-parameter astrometric solutions with really good precision on even the faintest of objects, which we can then use to search for a much wider volume of host stars and potentially companions to these systems. Additionally, there are 500 million of these objects which have derived photo spectrographic astrophysical parameters such as TF, log G, and importantly, metallicity, which will be very useful when building a control sample to test against the field population. Now, selecting these exoplanet hosts is going to be a difficult endeavor because there's so many exoplanets. Some of them have well-described host stars, some of them don't. But we start off with the Exoplanet Archive, of course, with about 5,500 planets. And we cut this sample down to a sample that we would like to search because these have much better astrometric observations in Gaia. Now, our first cut is, we're not looking at circumbinary planets, only S-type planets here. And we're interested in transiting planets mainly with a radius and orbital period that aren't limits, they are well described. And we end up with about 4,000, corresponding to about 3,000 hosts. Then we go from DR2, which is where the DR2 RDs are in Exoplanet Archive, of course, to DR3. We lose a few, but that's expected. And then we perform a volume limit on this, as well as a parallax significance cut, which corresponds to about 650 parsecs, which corresponds to about 1,700 exoplanet hosts that we are choosing as our targets. Now, we perform the common proper motion search on these targets, and we are looking for companions around 10,000 AU. That's what this search is going to be sensitive to, but with a standard parallax-dependent radius search at the start, which gives us a lot of neighbors, but of course, these aren't all going to be interesting. So we first cut them based on quality of the data, then run them past a common proper motion metric, which determines whether or not their proper motions agree with potentially bound systems. And then also run them past to check whether they're equidistant, which is that cut there. And we end up with about 300 hosts, which correspond to about 380 planets with wide stellar companions. Here they are on the color magnitude diagram, plotted against a background of all DR3 objects within 650 parsecs, host stars in red, companion stars in cyan. And as you'd probably expect, the host stars are much bluer and brighter, as it's much more likely to find planets around the primaries of multi-star systems. Now, we want to, of course, probe the Neptunian desert for whether or not there are more multiple star systems within this region. But we saw from a few slides ago at the start that ultra short period planets, which unfortunately are included in these older Neptunian desert boundaries, can contaminate the sample. So we can't just use this triangle here. And unfortunately, the Castro Gonzalez et al. Paper arrived a little bit too late for my study, but we performed a bit of a back of the envelope style cut to revise the desert boundaries that we're interested in into this. It mostly is just removing warm Neptunes. We're only interested in the deep desert, as well as the smaller rocky planets that we are known to not follow the trend that we're basing the study on. Now, we also introduce some other planetary boxes just for comparison. The important point is the desert and hot Jupiter boxes. And as you can see, this plot has both the planets that have companions from our search and the planets that have no companions as well. And then we run them past just simply finding the ratio of them within these boxes and find that we do reproduce the expected hot Jupiter result, which is that they have a much higher stellar multiplicity rate than a field sample of similar stars, which is represented by the darker bars. But unfortunately, the desert, I mean, by definition, it's got quite a small sample size. It's very noisy. We can't really reject the null hypothesis from this. It's not clearly following the hot Jupiter trend, which we base this off. So, and these are the sigma values here. You can see it's not 3 sigma for the hot Jupiters, but it is very, very close. So this is where TESS comes in. The TOI planet candidate sample is much better at populating the desert region that we want. So hopefully, by using this sample through the exact same searches that we just did, we can see whether or not there's indications that with better telescopes probing this region, we can test whether or not they are following the trend that we expect them to if they're following the hot Jupiter trend. And we get exactly that. The hot Jupiter result is once again reproduced, and this time the desert is much stronger result. It seems to once again be have a much higher multiplicity rate than the field sample of stars. And just to conclude, we've performed a DR3 astrometry search to search for wide companions at around 10,000 AU or less, around exoplanet host stars, as well as the TOI planet candidate stars. And hot Jupiter hosts reproduce the known result for both confirmed exoplanets and test planet candidates of being found more often in multi-star systems than other planets. However, for planets in the hot Neptune desert, we've got 2 different results. For the confirmed planets, we can't reject the null hypothesis. There's no clear evidence that they do follow the hot Jupiter trend. However, when we consider planetary candidates from TESS, we see that they strongly do. So it's either a case of a lot of them are false positives, or we are seeing, thanks to a much bigger sample size from TESS, a new similarity between the hot Neptune desert and the hot Jupiter sample. Thank you very much.
Questions for Fintan? I see one over here.
Hi, very nice talk. I'm Jinwen Zhang from University of Hawaii. I'm wondering whether in your sample, the stellar companion could dilute the light curve test, and have you considered to revise the planet radius?
No, I agree. That's a good point, and that's what I wanted to say about sort of completeness of the sample as well, because even if it's a very wide companion, so let's say a good couple of thousand AU away, TESS is still going to struggle. There's always been a bias against detecting planets like this, because you could have two stars within the same pixel. So it's in fact probably even worse than just a radius problem, in the point that you traditionally, with the confirmed exoplanet sample, would have a bias against multi-star planets. So I think in terms of actually finding the radius, yes, you're right, there would be a problem with that. But then also even just detecting the planet in the first place and having it go through all the pipelines would probably be another main thing.
Astra, I see one down here with Mike.
Mike Lund, Caltech, IPAC. I was curious with the confirmed planet samples, since those are more studied host stars in general.
Yeah.
What can you say in terms either of how many of the companions you found with your approach were already identified as companions for those hosts, or to what extent those host stars have closer in companions that may not show up out of Gaia data, but are still there? So they're still stars with companions, but not with companions that your approach finds.
Yes, no, and that is part of, again, the completeness study, because for the confirmed planets, I get a general across all planets that we search, about a multiplicity rate of about 16 to 20%, which is much lower than what you'd expect normally, which leads to, of course, the fact that this search, I'm not introducing or adding any known companions into the search. These are purely companions that came back from this common problem motion search. So of course, there will be closer in stars that Gaia wasn't able to resolve, or companions that didn't appear to pass the common problem motion tests that I've run, which you would of course be able to introduce them in with just simply a literature search, basically. But I wanted to keep this consistent by only including the stars from one type of search, so that it's known sort of what the biases are and what separations I'm probing.
All right, thank you.
Any other questions? If not, oh, Sam, right behind you, Astrid.
Hi, Sam Grunblatt, Johns Hopkins University. I was just wondering if the difference in masses of, hot Jupiters versus hot Neptunes would affect sort of their evolution over time, and then if that would affect, sort of the occurrence rates that you're getting for these populations. Would you expect to see a smaller number, or like a smaller occurrence of hot Neptunes just because they're less massive and therefore less likely to interact or something like that?
Yes, and I think that is probably a question for an evolutionary astrophysicist rather than someone like me. I think when it comes to trying to work out whether or not, or what effect, so are you saying that the multi-star system would affect the hot Neptunes, or is it just we're seeing less hot Neptunes because they're smaller?
Right. So I'm assuming that the higher occurrence rate of hot Jupiters in systems with companions has to do with some sort of dynamical interaction that has produced these hot Jupiter systems. And so presumably if you have similar dynamical interactions that are resulting in hot Neptunes, do you get just as many hot Neptunes, or do you get like a smaller number because maybe they interact differently because Neptunes are different than Jupiters?
No, I see. When it comes to what effect these Y companions actually have on systems, it's not immediately clear from either a formation or orbital evolutionary standpoint whether or not there's any effect at all. It's been shown that in sort of sub 100 AU separations, you would definitely see some I suppose what's the word? You know, lack of planets in those systems because of dynamical interactions. Maybe they never formed in the first place, that sort of thing. But with Y companions, the dynamical effects are basically negligible beyond a couple of hundred AU. So this shouldn't really affect, in that sense, any planet on any size, at any size, really. So I think it's definitely not to do with the differences between those masses.
All right, let's thank our speaker again. And our final speaker of the session is Tyler Fairington from the University of Southern Queensland. So whenever your slides are ready, take it away, Tyler.
Cool. So hi, everyone. I'm Tyler Fairington. I'm a final year undergraduate student at the University of Southern Queensland. And today I'm going to be presenting my findings revealing a formation dichotomy in the eccentricity distribution of warm single subsaturns in TESS. So here's the confirmed exoplanet population on the mass radius diagram for planets with mass and radius uncertainties of less than 30%. Highlighted in red are the sub-Saturn population, which I'm defining here as planets between 4 and 8 Earth radii. And despite their similar sizes, sub-Saturns span order and over a magnitude in mass. Now this is puzzling because according to traditional core accretion, when a planet accretes enough mass, it should undergo runaway accretion, becoming a Jovian-sized planet. But for whatever reason, these sub-Saturns decided to not agree with this. Now, this could hint at potential alternative formation mechanisms that are shaping this population. A lot of human and telescope time has been spent confirming and characterizing these planets in order to understand if there are alternative mechanisms creating this population. And today, I'm providing evidence that sub-Saturns are formed through multiple origin channels. And this was done through investigating the eccentricity distribution of warm single sub-Saturns. So Sydney gave a great overview of some of the dynamical mechanisms. So I'll briefly mention each mechanism's effect on the eccentricity of a planet. For in situ and disk migration, we expect the planet to either form in or migrate inwards, so their eccentricities are consistent with 0. If a planet has an external companion, this could cause excitations, resulting in planet-planet scattering, and the upper limit on eccentricities is more prolific at longer orbits. And then from either planet-planet scattering or other mechanisms, such as the Kozai mechanism, high eccentricity tidal migration can cause a planet to migrate inwards tidally. And you can see here that each formation mechanism has their own unique imprint on the semi-major axis eccentricity parameter space. I'll also note here that I'm showing the eccentricity in terms of E squared. This emphasizes the effects of higher eccentricities. So there are some problems if you just grab a whole bunch of planets and look at their eccentricities. For planets shorter than 8 days, they can undergo tidal circularization, and so they can have their eccentricities damped to near circular orbits. So I'm specifically interested in those that I'm classifying as warm, which are between 8 to 200 days. Also, Kepler found that most multi-transiting systems are circular, So to look for hints of alternative mechanisms, I want to look specifically for sub-Saturns and singles. But when you apply this criteria of a warm and single planet to the current population, I'm not left with a population. And 4 planets isn't enough to do anything efficient with regards to eccentricity distribution. This is where TESS has come to the rescue. Here I'm showing period instead of mass, again with the confirmed warm single Saturns in red. And this is the new additions of warm single candidates that TESS has discovered. So I derived the eccentricities of TESS candidates and found the population eccentricity distribution for the warm single sub-Saturns. And this is what I found. Here I'm showing the probability density as a function of eccentricity, with the best fitting median line of the population hyperparameters being shown in red, and then 500 draws from the population posteriors in the background. And what's most evident here is this bimodality, where we've got a large fraction of these sub-Saturns consistent with a circular orbit, and then we have a small subset of the population with much higher eccentricities than what we would expect. But before I dive into statistics of this density function, I'll talk to you a little bit about how I actually derive the eccentricities from TESS. So I made use of the photoeccentric effect, which was touched on briefly by previous talks over the past few days. But essentially, this leverages the fact that while for a planet on a circular orbit, it will have a constant orbital velocity, resulting in the gray observed light curve, a planet on an eccentric orbit will have a varying orbital velocity and thus have a different transit duration depending on where you observe it on its orbit. So depending on its argument of periastron, its transit duration could either be shorter, seen in red, or longer in blue than if it was circular at the same orbital period. By comparing the ratio of this observed transit duration to its circular counterpart, we can directly constrain the eccentricity and argument of periastron. An example of this is on Kepler 1656b, which is the first confirmed high eccentricity sub-Saturn in our sample. I'm showing a corner plot of eccentricity and argument of periastron. With purely the TESS light curve and Gaia, we can get this TESS photometric solution in blue and compare it to the accepted radial velocity solution in red. And we can find a within 1 sigma agreement to the high eccentricity of around 0.8. And for some more statistics, our final sample consists of 70 candidate or planets. 29 of these are planet candidates that have yet to receive intensive follow-up. 24 have been verified by the TESS follow-up groups, and 17 are confirmed. And on the right, I'm showing my hierarchical model, which I've found out does not ever look good on a presentation, but the point to take is that we are introducing a beta mixture model. So we feed all of our eccentricities, they are derived from a beta mixture distribution. So going back to our result, we can look a bit more in depth into what actually is occurring in this population. 83% of planets have a mean eccentricity of 0.07, but these planets are also relatively consistent with 0 to within 1 sigma. And then the intriguing part is 17% of these warm single sub-Saturns have a mean eccentricity of about 0.7, indicating some mechanism is shaping a non-zero fraction of this population. In order to make sure that this result was intrinsic to the population, we conducted bootstrap sampling analysis in which we assigned false positive rates to all of our candidates and also assigned a probability of being drawn based on their likelihood of being in the 4 to 8 Earth radii sub-Saturn range. Our false positive rates came from the TESS follow-up working groups, with planet candidates having a conservative 40%, those verified through photometry at 5%, and confirmed planets having no false positive rate. So now that we've confirmed this population is accurate, we can plot it back against our illustrative model of the formation mechanisms. Again, to remind you, this eccentricity is in E squared, So the actual values of all these points are relatively higher, and their uncertainties are smaller. And we can see clearly that both modes coincide with one mechanism, disk migration, and then high eccentricity tidal migration. What's also interesting is for planet-planet scattering, we would expect subsatins on the longer end of the orbit scale to be found with moderate eccentricities. But this has to be taken with a grain of salt because there is a whole lot of selection effects and completeness where TESS may have just not observed many eccentric 200-day period subsatins. We can also plot our subsaturn result against the warm Jupiters by Dong et al. 2021. And we can see two key findings. The first is that, as expected, the low eccentricity mode of subsatins is higher, as we would expect smaller planets to be more circular on average. But the interesting result out of all of this is the fact that subsatins have a higher mean eccentricity for their small high eccentricity subset than the Jupiters. And so to summarize, we identified a bimodality in the eccentricity distribution of TESS warm single subsatins and find that our results are consistent with a population formed through disk migration and high eccentricity tidal migration. If we want to understand more about the mechanisms of high eccentricity tidal migration, this parameter space requires further modeling in order to understand what the mechanisms causing the initial excitement are. Thank you.
Questions for Tyler? See Diana over there behind you, Catherine.
Diana Dragomir, University of New Mexico. I use the implication that the population of subsaturns is analogous to the population of warm Jupiters?
Yeah, that's a great question.
Okay.
I don't want to be the one to speculate that. So the Jupiter population, as we're finding out with recent discoveries, do have a number of planets that are consistent with high eccentricity tidal migration. So this doesn't refute or approve that the Jupiters and the subsaturns are analogous. But it'll be very interesting to find that out.
Great talk, Tyler. Brandon Radzim, Indiana University. I have two questions. One is just basic. I'm sure you kind of played with your sample in deriving this result. Did you ever, I mean, of course, this is numerically prohibitive in terms of number statistics, but did you ever just look at subsaturns with confirmed masses and change your cut to a mass cut? Because we know like there can be all sorts of, lots of these planets tend to be poofy, and a 4 to 8 Earth radius cut might be excluding some fraction of the population.
Yeah, so the problem is we wanted to keep this study homogeneous. So we wanted to use TESS rather than combining different studies as they all have their own biases. Unfortunately, TESS doesn't give you a mass, so we can't make a cut to look at the population.
Okay, great, thank you. And then my other question is maybe a little bit more open-ended, but just what's your general feeling? So this is like a super interesting result, and as we've discussed, might have implications tying subsaturns to close-in giants, Jovian planets. But as you said, subsaturns might kind of represent a bridge between these lower mass super-Earths and Jovians, and their companion rate might also be intermediate between those two populations. So what's your feeling for how prevalent these types of violent dynamical mechanisms might be within the subsaturn, close-in subsaturn population, considering that they might have a higher companion rate and therefore maybe a larger fraction of them might form quiescently?
Yeah, I think I wouldn't be able to tell if subsaturns originate from the same mechanism as the Jupiters, if I'm getting your question correctly. I know previous studies have talked about like planet-planet collisions being possible route for sub-Saturns, which could differentiate them from the Jupiter high eccentricity tidal migration. But I think this whole sort of area just requires a lot more theoretical work and simulations in order to understand what actually makes these high eccentricity planets. And I think just identifying that they exist is the first step.
Thank you.
Thanks, Brandon.
One right behind you, Catherine.
Hi, again, great talk and really interesting result. I'm Vikash from Columbia University. I was curious about, you used a mixture of two beta distributions here. And I was curious about your motivation for both those things. Why 2 instead of n, and why beta instead of something else?
Sure. Previous work has used a normal mixture model, so 2 Gaussians. The problem that we encountered with this is normal mixtures require symmetrical uncertainties. So you actually get you get symmetry in the uncertainties when you're deriving the population distribution, which can actually result in a positive bias. So an example of this is my re-derivation of the 2021 Jupiter result. The yellow is with a normal mixture, and you can see it's slightly positively biased towards a non-zero eccentricity. The point of using a beta mixture is that you can essentially get really close to 0, or in the very unlikely event, get very close to 1, and you can have these asymmetric uncertainties.
Cool, thanks. Did you play with more than 2 components?
Yes, sorry. So the point of 2 components is that beyond 2, the uncertainties start to get way too clustered, and you start to get unifying basically down to 2. So I did try to model 3, but you basically get a result of 2 within 1 sigma.
Cool, thanks.
Thank you.
2 behind you, Astrid.
Hi, Ben Sheppey, University of Hawaii. Did you look at what it looks like if you just sum the probability distributions?
Could you repeat the question, sorry?
Did you look at what it looks like if you just sum the individual probability distributions?
Between the Jupiters and the sub-Saturns?
No, in the previous plot. Like here, my understanding, correct me if I'm wrong. Let's keep going.
I did like
slide you showed, yeah. Yeah, on the the left-hand side, what I'm understanding what you're doing is you're basically fitting a 2-component model to the probability distributions of all the different planets. But you just sum the probability distributions on the left-hand side.
As in, like, did we just take all the eccentricities of the individuals and plot a distribution? No, so we used the hierarchical Bayesian model that I showed you. Basically, you fit all the individual planets' eccentricities simultaneously to a population shape, which in this case is the beta mixture model. And then the population shape serves as a prior on all the individuals. And that way you get a shrinkage effect where you get more informative eccentricities of all the individuals and the population at the same time. So we infer this population without any bias of all the individuals.
Let's do one quick one from Sam.
I promise it's quick. Sam Grunblatt, Johns Hopkins University. Did you determine the ages of these systems, and did you see any trends?
Yeah, that's a really good question. So the confirmed high eccentricity sub-Saturn, Kepler 1656, is roughly on the order of 5 gig a year. We did look for lithium in the spectra of the other high eccentricity candidates and didn't find anything. But myself and collaborators were also awarded a program for NEWID to confirm the high eccentricity candidates in this sample. So hopefully for those who haven't had spectra yet, we can have a look at their spectra. We haven't done any gyrochronology or anything yet, but that's for a bit further on. These results are all preliminary.
All right, let's thank Tyler again. And let's also give one big round of applause to all of our great speakers in this session.
Welcome to the final session of the day and of the week. Happy Friday. This session is focused on what we call synergies between TESS and other missions or surveys, and specifically this session will also be focused on future missions. As we come to an end of the conference, we nod to the future. And we will start with Billy Edwards, who will talk about population studies of exoplanets atmosphere with the ESA aerial mission. Take it away. You already have that.
Thank you. Good afternoon, everyone. My name is Billy. I'm a staff scientist at ESRON, the Netherlands Institute for Space Research. And it's really great to get to kick off this final session to talk to you about aerial. My plan is to give you kind of a brief overview of the mission, to then give some insights about the target selection methodology that we're using, and then to focus on the impact that TESS has had already on the aerial mission and the impact it could have over the next few years. So to start with the kind of basics of aerial, what is it? It's an ESA-led mission, but there are contributions from the US, from Canada, and from Japan as well. It's now been adopted formally by ESA, is fully funded for launch. The launch date is scheduled for the second half of 2029 on board an Ariane 6, which I think successfully launched for the first time a few weeks ago. Maybe you saw that news. The plan will be to operate aerial from L2, a very popular orbit for astronomical satellites. And the instrumentation on board aerial is essentially 3 photometers and 3 spectrometers. So these operate from 0.5 to 7.8 microns. This data is taken simultaneously. So unlike HST or JWST, where you have different instruments that you can only operate one of them at a time, all of aerial's instrumentation is always operating. The data is always the same. You get this coverage simultaneously. The only thing that ever changes essentially is the cadence of the exposures. So aerial data is kind of always homogeneous in that way. And the plan in terms of the science is to, of course, study transiting exoplanets and to look at their atmospheres and do a population survey of exoplanetary atmospheres. So what's the current status of aerial? So this is a computer-generated model, a CAD model, supplied by Airbus, who are the prime contractor for supplying the spacecraft bus. And then here is kind of what aerial looks like in reality. So these are some actual hardware components. So you've got the mirrors down the bottom left, M1 through M4. You have the V-grooves and the baffle, which are there to keep the telescope cool. You have in the sort of top right, there's the panel which will hold all the instruments. In the bottom right is the AIRS instrument, the aerial infrared spectrometer. And the top part is NIRSpec and the FGS, the fine guidance sensor. And this is what NASA is contributing to aerial. So these are all, most of these are not flight hardware. These are all either structural models, thermal models, or structural thermal models. I think the one exception is potentially the V-grooves. So these are down here that are going into the thermal vac chamber there, which are a potential flight spare for aerial. But everything else is just sort of representative of what parts of aerial will look like. And they're being tested and made at the moment. There's also, on top of this testing of these, there's been testing of actually the instrumentation itself. So this is a picture of the lab setup in France for the AIRS instrument. So the instrument is operating from 3.9 to 7.8 microns. You can see a detector image there of after the source spectrum has gone through the instrument. And if you can see, maybe on this plot on the left, you can see the sort of blue or the darker line is the spectrum that we got out. And the other two are models from Hytran for water and for carbon dioxide. So the first big result from aerial is that we've detected water and carbon dioxide in the Earth's atmosphere in a lab in France. Which is obviously, a massive result. So yeah, look out for that paper. So just a good indication that we can kind of detect the species that we want to in this environment. So hopefully now we can go on to do this on exoplanetary atmospheres. In terms of the science, what are we going to do? Well, I put sort of how I would word the aim of aerial here in the bottom right. That's to perform a meticulous chemical survey of exoplanetary atmospheres. And the key idea is to be able to do demographic studies with this data set. So we're going to study, our requirement is to study 500 exoplanetary atmospheres. We may do up to 1,000, so it's somewhere in that range of planets. We're going to be doing transmission spectroscopy, emission spectroscopy, and also taking phase curves as well. So what will the aerial survey actually look like? How are we doing the target selection? How are we prioritizing targets and so on? I think I could spend the whole session trying to answer this question and still couldn't fully do it. So I've tried to do it at a very kind of informal and basic level here. But essentially, in my mind, there are two different types of kind of population studies that you can do. The first is to say, okay, I have a big broad parameter space, and I want to say, how does a bulk parameter affect the atmosphere? So as I increase with planetary mass, how does the atmosphere change? As we change the temperature of the planet, what different species emerge? How does the star affect the atmosphere, and so on? So you can view this, or I'm starting to view this a little bit like playing exoplanetary bingo. So you're trying to cover this big parameter space. You might have sort of mass versus temperature. You want to find things that are all the same temperature and say, how does mass affect the chemistry that we're seeing? And the same for like all the different axes that you could do this on. In reality, we're kind of doing this, I guess, over sort of 4 or 5 dimensions. But this is kind of the basic idea. The second kind of population study you can do in terms of the atmospheres is to say, take a selection of planets and say, on paper, these are all the same. So these have the same bulk characteristics, they're the same mass, the same radius, same temperature, same star. They look exactly the same on paper, but are their atmospheres actually the same? And then try and find in each of these classes of planets, what's the kind of normal for that particular type of planet. And so I've started viewing this as a bit like playing the game Among Us. Maybe some of you remember that from the COVID lockdowns. And so it's trying to find the kind of the imposters, the weirdos, the things that are different from their kind of companions. And so when you put these two together, what you get is this kind of bingo card, but instead of having a single planet in each of these spaces, what you want to have is many, many different planets. So you can find kind of the normal, the archetype in that class. And then when you do your population study, you're not biased by having kind of one oddball that's kind of leading your trend into some, into the incorrect trend. So this is where TESS really comes in and was been really, really useful, because what we want is to have many, many planets to choose from. So we can do this study that's both kind of diverse in terms of the parameter space we're looking at, but is also kind of deep in terms of how many planets we're observing in each part of that space. So based on some simulations I ran sort of a month or so ago, of the 540 or so TESS confirmed planets, around 44% of those are potentially good targets for aerial based on SNR. And if you actually then went to sort of applying this strategy of doing this, exoplanet bingo and making this survey that aerial could actually study in the prime mission life, you get that around 30% of the targets that we would study in this example would be from targets confirmed from TESS. So these are all the ones labeled by a star in this diagram of planetary radius versus planetary temperature. But of course, this is if aerial launched today, and we're not launching today. We've still got many years until aerial launches, something like 5 years. So there's still many more things that can be confirmed in that time. So then the question becomes, how many TESS planet candidates could be good targets for aerial if they're actually true planets? And if I look at the current TESS planet candidates, there are about 2,000 that we would consider as potential targets for aerial based on just on SNR. And if we then, some of these, of course, will be false positives. Some of them won't have, I've assumed a mass for these. They won't have the exact properties. And so there may be some, obviously, this is highly caveated in terms of the number. But even if only half of those were potential targets for aerial, there's still an awful lot there that could be great targets for us. And so now going for a sample of 500 planets, trying to, again, cover this wide parameter space, I found that, about 213 of those in this example were planetary candidates. So there's still many, many good targets for atmospheric spectroscopy that have not yet been confirmed. So if you add this to the confirmed number, you get to something like 60% of aerial targets could be coming from TESS, which is a huge, huge number. So the key question, I guess, is kind of which targets aerial is actually going to observe. If you'd like to know this information, you can use the QR code there. There's a publicly available repository. It lists kind of the currently known planets that we're considering, as well as the TESS planet candidates. It's updated every couple of months, and all the old lists are kept there as well. And if you are interested in the kind of the detail, then you can go and see the paper that we wrote a few years ago. There's a number of different things on there. One of them is some plots like this, and don't worry, I have a zoom-in version in a second, but it's essentially the planet radius versus planet temperature, and it's saying this is just for G-type stars, and it's saying what are the best unconfirmed candidates for spectroscopy with aerial if they were truly planets. And so if you zoom in on one of these squares, I think this is just like the sort of hot Jupiter section of that diagram. There's a list of 10 TOIs, and these are the best 10 TOIs in transit and in eclipse for study with aerial. So TOI 65, 64, if it's a real planet, would be the best in that part of the parameter space for aerial. And then the brackets show like how that compares to all of the kind of currently known planets as well. So it would be the third best target in terms of like how quickly we reach a higher SNR. TOI 65, 64 would be the third best target. So there are two better ones out there, but this is still a great target. So if you're looking at these and you see some that are on this list, that's great. And you can say that Ariel might study this in the future. And also if you're wondering which ones to follow up, then from a point of view of Ariel, these are the really high priority ones that we would like you to go and confirm or refute in each case. I want to use my last bit of time just to say Ariel is always said as being a dedicated mission to doing exoplanetary atmospheres. That's mostly true. 90% of the science time will be spent doing a structured survey of atmospheres, and this will be kind of constructed by the consortium. But there is some extra time for complementary science programs. So this is open time available to anyone in the community from any country. This is going to be run by ESA, using like standard proposals like you would have for HST, JWST, for the TESS and so on. And so that equates to about 2,000, 2,500 hours. Currently, it's for targets which don't have a fixed sort of time. So things that could be very flexible and fit in the schedule between different transits that we're observing with Ariel. But I'm hoping to change that we can make that so that there are some time critical observations allowed in this time as well. But obviously that will have to be not affecting essentially the prime mission science. And so there's a graphic there of some ideas that are already being pursued to see how Ariel can contribute. So for example, studying free floating brown dwarfs, studying asteroids and comets, or looking at protoplanetary disks. So if you're thinking like having some spectroscopy from 0.5 to 7.8 micron would be really useful for your science, please let me know. I'd be happy to do some simulations and see how Ariel can contribute to your science case. And in summary, so Ariel is going to launch in 2029. We're going to do a survey of exoplanetary atmospheres. The idea of Ariel is to be a demographics mission. But we're really already thankful for what TESS and the TESS community has done. We've already provided something like 30% of the targets, but there are many, many more out there. So if you go and confirm those, we'd be even happier. So with that, I will thank you for your attention and happily take any questions. Thank you.
Questions?
Aviv from the Weizmann Institute. Can you give me a short brief on what is better or worse in real versus JWST?
What's better or worse for JWST? That's a complex question. I would say it depends what you're trying to do. So I guess the benefit of Ariel for a single target is always that we get this kind of wide wavelength coverage, whereas with JWST, normally you have to use multiple instruments to cover that same wavelength region. But obviously JWST has a bigger aperture. So if you're going for very small signals, so, rocky planets, for example, with very tenuous atmospheres, then JWST is perhaps a little bit better there. And I think the key part of Ariel that we really struggle with JWST is because JWST is based on proposals, it's very hard to do population studies because you end up almost with sort of a random lottery of what planets are picked. And then it's very hard to do sort of structured population survey where you're not doing low number statistics. And so that's the idea behind Ariel, is to do a kind of structured survey so we make sure we kind of cover the whole parameter space. And also that we have homogeneous data sets, because if you study, they've already found like if you study the same planet with different JWST instruments, you get different answers in terms of like the atmospheric chemistry. So if you now study different planets with different instruments, you don't know whether the differences are based on the sensitivity of the data in each case, or because the planets are truly different. And so that's kind of also one of the ideas of Ariel, is to have that homogeneous data to allow you to do those comparisons and say, okay, this difference is because the planets are different, not because my data sets have different sensitivities. So I'd say that was a brief, overview of that. A good question.
Yeah, good question. Let's thank Billy again. Next, we are moving from aerial to Roman. We have a voyage in future and current missions. We have Mark Pinsonelt. I hope I didn't butcher it.
Pinsonel's close.
Thank you. We'll talk about red giants, asteroseismology in TESS and Roman. Take it away.
Yes, thanks very much for the opportunity to come and talk about this. And I thank you all, the few, the brave, the proud, the final session attendees for all being here with us to learn about this exciting science. I wanted to also note that the work we're doing with Roman is part of a good team where we're actually trying to do careful simulations of what we can do with seismology and Roman, and also trying to lobby the Roman team hard to actually make sure we can actually do seismology with it. Now, I'd like to begin by kind of looking a little bit at what the physics of seismology is, because I think it's actually quite elegant and quite beautiful. The basis of seismology and why it's such a powerful tool for studying cool stars is that cool stars have turbulence in their envelopes. This turbulence excites waves. Stars have enormous gradients in density and pressure in their interior, and so these waves are refracted as they go in. If you come back up to the surface and you have an integer number of nodes, you can get constructive interference, and this constructive interference gives you frequencies that tell you something. The difference in spacing between frequencies tells you about basically the speed of sound, which is related to the mean density. So you have one entry, which is mean density. That's one thing you can measure. And the ability to reflect the waves at the surface. Let's see, is this actually a, oh, we have a pointer, awesome. Okay, the ability to reflect waves at the surface also requires you to have a wavelength that is longer than the density scale height. And so in effect, you only trap modes that are long enough in frequency, just like you have microwave ovens that have holes that are smaller than the wavelength of the microwaves. And so as a result, you have one thing you can measure that tells you about gravity, one thing you can measure that tells you about density. You can get mass and radius, and with stellar models, age. I'd be glad to go in more if interested. And so why red giants is the next question. And the short answer is that it turns out, serendipitously, that red giants are high amplitude oscillators, and their frequencies of oscillations are almost perfectly matched to planet transit missions. In fact, all planet transit missions are stealth asteroseismology missions. Your observing cadences and your strategies almost perfectly match what we need to see giants. Giants have spectra, which are remarkably rich in information about abundances. They're luminous, and you can also get great kinematics in them. And so that means that by studying red giant seismology, you can learn about motions, you can learn about chemical evolution, you can learn about ages, you can get a fantastic array of things, and that's why red giant seismology is so remarkably rich. Now, I wanted to put this in context because it's important to think about where different missions kind of fit into the scheme of things. The Kepler and K2 and Corot data that we have is samples of order 10,000 for both Kepler and K2. These are sort of spread out in distance, but in practice, the Kepler data is largely in the solar circle because of its viewing angle. TESS is an enormous sample, but bright stars, very local. And I'm going to try and convince you that Roman is beautifully complementary by giving us a potentially enormous sample of objects in the center of the galaxy. Now, one of the things I like to do here is to kind of show what this does to a community that's broader than seismologists. After all, there are dozens of us, but there's more than dozens of you. And so it'd be kind of good to be able to show what you can do with this. On the right-hand side, I'm showing you a kind of classic chemical diagram, the alpha to iron, which measures basically the degree of elements that come from core collapse or rapid enrichment events, versus iron to hydrogen. This basically measures how important prompt sources of elements are relative to delayed ones. You see that there's two groups. That's actually a really significant problem in the galaxy to understand why there's two groups instead of one giant blob. But if you just had the chemistry, you wouldn't see anything else. If you then go to the seismology, you can see that these green stars here are almost all locked in one spike with a really, really narrow domain. They also turn out to be kinematically related to the thick disk. So this is the thick disk population. And if you look carefully, you can see that the thin disk population is delayed a little bit more, has a much richer, wider range of ages. But you can also see there are things you wouldn't have predicted just from a simple picture. Like there's a bunch of these young stars that are alpha rich whose origin is actually quite controversial. We discovered those with seismology. That's actually an important point. If you actually wanted to look at something else you might get, on the upper side here, we've heard a bunch of talks here about looking at young planets, and you might wonder why all young open clusters are near solar metallicity. It turns out that if you look in the giants, you see that virtually all of the young core helium burning stars are also solar metallicity because there's a finite time to mix stars into the solar circle in the galaxy. You can learn about things like that from studying seismology. And my final pitch here is this is more than 600 stars which are rapidly rotating or rotating rapidly enough that they're almost certainly merger products, planet engulfment candidates in the red giant branch, and we're learning about engulfment of planets and all sorts of exciting side populations here. So there's a lot of information encoded in this, quite beyond things like just age maps. Now, we could say that we don't need us anymore. We have our robot overlords. They can look at the Kepler data. They can just solve for everything, correlate everything with everything else, and we're done. It turns out that the robot overlords aren't here quite yet because we actually find out that we can't recover some things from our Kepler data. We can't recover old ages, and you can never find things that aren't in your training set to begin with. So we really need to be able to sample populations across the galaxy in order to be able to faithfully understand and recover the information that we're interested in. Now, the other piece here is I just showed you that alpha to iron versus Fe on H plane. This is an iconic image from the Hayden et al. 2015 paper, kind of showing you how these trends change as you go across the galaxy. The pattern that we see in the solar circle is very particular. The alpha pore population shifts in metallicity, the strength changes as you go up and down in the plane and radially. We have no data in the bulge. It's a really interesting open question what these populations look like and what their ages actually are. Now, what TESS is going to give us in this domain is an order of magnitude larger sample. We already have 158,000 measurements published. That's more than 10 times the Kepler sample. We heard this meeting from Rafa Garcia that sample's perhaps doubled. We probably have more than 300,000 stars. And so what TESS is going to give us is a really, really large local sample, a very, very big sample of measurements. It's a clean selection function. The data is just getting better and better. We have lots of overlap with Gaia, and this will also be an absolutely essential training step for interpreting the data in the center of the galaxy, where we will have far less information about the stars. Now let's switch to Roman. Roman is a completely different beast. And I think it's actually worth noting that, first of all, it's launching in 2 years. It does have a huge weak lensing cosmology component, but it's a stealth asteroseismology mission as well, because in the center of the galaxy, the microlensing people are studying at fields in the galactic bulge. And they're studying at these fields for a very long dwell time, and it's a really, really exciting opportunity. Whenever you have a mission where you want to take movies of stars, I love it. I support you. Whatever you're doing, just take movies of stars, and we're just all in on it. It's fantastic for us. And so you're looking at the center of the galaxy. And one of the things to note about here is that this is a very different domain than TESS. We are talking about basically pixels that are HST resolution, 1/10 of an arcsecond pixels, giant cameras, huge images. These things are going to be in the infrared, so you can see right into the center of the galaxy. The Galactic Bulge Time Domain Survey is tiling a series of fields with about a 15-minute cadence. Okay, so there's a 15-minute cadence there. And in addition, one note here is this is all public data. We're in NASA land, okay? So that means this is all public data. There's a commitment by the mission to produce light curves for the stars because the microlensing people want light curves. So that's kind of a core science tool for the microlensing people. And there's deep multiband photometry. There's some things that are really different also. Infrared detectors are continuous read. That means that although there is a 1 minute exposure, you can actually subsample that 1 minute exposure for interesting science. In fact, our stars are a little bit too bright. The giants turn out to be saturated at the center of the galaxy, and we're relying on the first 3-second read in order to be able to actually get interesting data from the giants. Now, in addition to this, this is the kind of data you're going to be looking at. This is a simulation of 1 part in 1,000 of the Roman galactic bulge field from Robbie Wilson. And you can just see the fantastic depths that you can see in this image. All these light curves, all this variability. There's just a ton of stuff in there. In addition, we can zoom in. This is a closer image. This also shows you what a TESS pixel might look like. If you're wondering if you're thinking about TESS, it's going to be kind of like that size. So there could be some things you can do in here, but it could be kind of rough with crowding. And all of those annoying yellow things that are saturated are the giants in the asteroseismic field. They're the saturated star images that you're actually looking at in the giants. And it's resolved down to fantastically small scales. And so we've done some simulations. These are different models representing different more and less pessimistic assumptions about the noise properties. Most pessimistic on the left. This is the same noise properties, but observed at a higher cadence. We've been lobbying the Roman mission to come back and observe at a little bit higher cadence to get better noise performance. And this is kind of a measure of how well we could do in the brightest saturated stars. Green is good, red is bad. This is frequency of maximum power, which is a gravity proxy, red clump on the top, red giant branch on the bottom. And you can see that we actually really do think that we're going to be able to do seismology in the bulge, and we're going to be able to do it credibly and well. Now, one note here is we're going to be put right back to where we were at the start of the Kepler mission. When Kepler was released, we had a gigantic time domain database and a really modest library of information about the stars. We had to build that up. There was a Kepler input catalog was fantastic. We had to build it up over time. It took a lot of effort. And in this case, we could have 500,000 asteroseismic detections, and we will have colors and a little bit of other information about the stars in the center of the galaxy. So leveraging that information is going to be absolutely crucial. And so we really, again, will be relying really heavily on TESS to basically teach us what a red giant looks like so we can interpret the red giants we see in the center of the galaxy. I will put up, in closing, a kind of bit of a technical information about Roman and the Galactic Bulge Time Domain Survey for those who are interested. Thank you very much for your attention on a Friday afternoon, and I will take questions.
The energy and the passion, it's contagious. I want to start working on Roman now. Did I say this out loud? Questions?
Tara Featheroff, UC Riverside. I love these crowded fields. They also are very intimidating. Can you give any comments about dealing with blending, because you're going to have to?
Yeah, it's an interesting question. It turns out that blending is going to be an issue for the faintest sources in the field. And it's certainly going to be something the microlensing people are going to have to think about given their typical target magnitudes. For the seismology, our stars are by their definition just incredibly bright. And so blending is not a factor for the astroseismology. But that is going to be a real challenge for the light curve team in particular to be able to work on the famous sources.
Luke Bauma from Caltech in the back. Earlier this week, you said a few words briefly about the high latitude survey.
Yeah.
Could you maybe gesture toward aspects of that that you're excited about?
Yes, there are 3 big pillars to the Roman mission, 3 dedicated teams, one of which is looking at weak lensing, looking at galaxies, one of which is the Galactic Bulge Time Domain Survey, and one of which is the High Latitude Time Domain Survey, which is aimed at finding supernovae. That is interesting because it's going to be sampling things over longer timescales of days, and if you're interested in that, that's important. Another thing to note is recently approved is a galactic plane survey, which is going to be not a necessarily a time domain image, but a deep infrared image of all the sources in the galactic plane, which is going to be amazingly useful for a lot of galactic science.
One last question.
just like TESS, oh, sorry, Ben Shappy, University of Hawaii, just like TESS, hopefully Roman lasts past the main mission and we'll do a lot of science going forward. So my question to you is, if you could point Roman anywhere after the main mission for a time domain survey, where would you like to point next?
I would really love it if we could look at a globular cluster. The field of view of Roman is very close to a globular cluster. That would be awesome. And to be honest, I think Andromeda. Andromeda would be just a great field to look at for a long time.
Okay, let's thank Mark again.
Okay.
So from Roman, we are going to CHEOPS. CHEOPS is, of course, not a future mission, but a strongly ongoing mission. And we have Hugh Osborne, who will tell us about the tales of investigating a very complex multi-planet system, HD 110067.
Yeah, thanks, Avi. Yeah, so I was stepping back a little bit from the future of exoplanets to a project that I'm currently leading through the CHEOPS GTO. I'm Hugh Osborne, by the way. I'm at Bern and ETH Zurich. And so, yeah, I'll tell you a little bit about this population of longer periods sub-Neptunes we've been finding, and then I'll concentrate on this very exciting system, HD 110067. So we tend to concentrate on long period sub-Neptunes, and I hope to convince you that those are an interesting bunch of planets to look at. So these are planets that aren't really dominated by their host stars in the way that hot planets are. So they don't have, they haven't potentially lost their atmospheres through photoevaporation, which means maybe they're more primordial. These are often in multi-planet systems, which enables us to do interplanetary comparison if we can characterize these planets. We also, as we've heard earlier in this conference, don't really know how they're formed. Maybe they're water pore formation, kind of gas dwarfs that are formed inside the ice line, or maybe they're water-rich formation beyond the ice line and they've migrated in. So that's an open question that these planets can help us answer. And the way that we can answer that is because these are low-density planets. They have extended atmospheres, which means that they are characterizable with the current generation of space telescopes, specifically with James Webb. And so we can observe lower temperature molecules in those atmospheres, CO2, methane, ammonia potentially. And there's also a potential trend that at cooler temperatures beyond 600 Kelvin, these atmospheres become clearer. So the really key detections that JWST has made in the last couple of years have been for planets with equilibrium temperatures of below 600 Kelvin, TOI 270, and which we heard about from Pierre-Alexis on Tuesday. So the problem is if you look at the planets that TESS has found, so this plot you've seen a lot this conference, period versus radius, there is the clear hint of the 27-day orbits in the yellow dots here, which are the TESS TOIs. And that's because the majority of the sky is only covered continuously for 27 days. And so for most of the stars in the sky, we don't find many planets beyond that. And that's a shame because there's a missing population of sub-Neptunes, and that's actually occurrence rates. That's where there's more sub-Neptunes. The peak in occurrence rates, if you look at Kepler, is between 30 and 50 days. So there are planets out there that TESS hasn't seen. But don't worry, because, well, this is another way to look at that. So if you look at the two ecliptic poles, you can see my favorite part of the sky, not really, the continuous viewing zones here in yellow. And care to guess where all of the confirmed sub-Neptunes beyond 25 days are? They're in the continuous viewing zones. And that's a real shame because these are only about a couple of % of the sky. So we should be finding these planets across the sky. But for the moment, we are unable to, unfortunately. But yeah, so the long period and cooler sub-Neptunes are hiding from TESS at the moment. But through this program we have on CHEOPS, we are able to start filling in this region of longer period sub-Neptunes. So this is kind of zoomed into the Neptune regime. And these are all of the planets that we've been able to detect through this program. So how have we been able to do that? Well, they're not really hiding from TESS. They're hiding in plain sight, these planets, because if you look at this TESS sector from sector 12, there's clearly a transiting planet here, or at least a candidate. This is a 25 sigma transit. It's about 500 ppm, so I think this one's about 3 or 4 Earth radii. But this is quite easy to find if you're looking at the light curve as a human, but also if you're not running a periodic search. And then what tends to happen with TESS is you wait 2 years, and then 2 years later you get another light curve. And in this case, you see another beautiful transit, 500 ppm once again. So these are we call Duro transits, and these are surprisingly hard for the current generation of the planet search techniques to find. So we've been able to find hundreds of these candidates, but only about 25% of those have been through the TOI pipeline. So one of the ways we've been finding them is with a custom detection pipeline that, okay, I say see poster 118 by Amy Toussaint. You can go and see the hole where that poster was, if you like, after the conference, but you might be able to find it online. But yeah, the majority of these candidates are around bright stars, and the majority of them are actually relatively small in radius as well. So we've heard a little bit from Chris Mann this morning about how you can follow up the giants. So typically this is done from the ground and maybe with NEOSSat as well. But in terms of the smaller planets, CHEOPS is the perfect machine to go after these. And Vikash Singh introduced CHEOPS this morning, so I won't introduce it that much. But suffice to say that it's well suited to go after small planets. Yes. So what do we get when we have these 2 transits? We get usually a minimum period based on where we don't see a transit in the light curve. So this might be 20 days. And then we have some maximum period set by the distance between the 2 transits that we found. And then there's usually an array of aliases between those maximum and the minimum. And this can be as many as 40, depending on what your minimum period is from the TESS light curve. So the first thing that we do is we run a model based on the transits that we have in order to predict which are the most likely aliases. I have some code which is able to do this and means we can focus on only certain aliases to hunt with CHEOPS. So this is an example of how we do this with HIP 9618C. So we first looked with CHEOPS at the 40-day alias, and we saw a flat line. So this is real data from CHEOPS, and obviously the transit here is missing. We went after the 46-day alias, again a flat line, unfortunately. Then the 49-day alias, once again a flat line. It's quite addictive when you get these data in an email, because you don't know what you're going to see, whether you'll find the planet or not. It's kind of akin to gambling in that sense. And when you find a transit like this, it's very nice to kind of moment where you realize that you have the orbital period of the planet and you can confirm it and you can start doing characterization of that planet. So yeah, in this case, it was the 52.6-day alias for this sub-Neptune. So now looking at the planets that we found in kind of population. So I showed you already, they span periods of about 20 to 80 days. In terms of the magnitude, they tend to be pretty bright, median magnitude in Gaia of 9.1, which is helpful when you want to get mass characterization or atmospheric characterization for these planets. I won't talk about it, but there's a naked eye star with a Neptune, which we found. You can ask me afterwards about that one if you're interested. Also, these planets tend to be cool. So if you look at, in terms of equilibrium temperature, they tend to be between about 800 and 400 Kelvin. So beyond this 600 Kelvin line where maybe there's a trend in terms of clear atmospheres to observe. And they are also characterizable. So this is the JWST expected signal to noise and the transmission spectroscopy metric. And you can see that all of our planets cluster quite high in the TSM. And actually, we kind of double the number of characterizable planets beyond 20 days through this sample. And if you look at them in terms of their multiplicity, we often find them in multi-planet systems. But I won't say that this is a trend. This is also completely biased by the fact that they're easier to find when they're exterior to a known planet. Although in some cases, we have found interior small planets to these sub-Neptunes. So these are all the systems that we've published so far. 8 papers from this project. So at the moment, I'm working on the 9th paper, which will introduce the full sample 20 planets here. But now I'd like to concentrate on the most interesting one of these systems, at least the one with the most planets, and that is HD 110067, which Rafa Luque published last year. And so this is a bright K0 star. It was observed with 2 sectors in TESS, so this is what the data looks like. And you can see a kind of forest of transits in these light curves, which is really beautiful transits, all visible to the eye. So there were 15 transits in these 2 sectors of data, only 9 of them from periodic planets. So I think there's 4 transits of planet B, 5 transits of planet C, and then there are 6 other transits, which we couldn't associate to periodic planets. So this actually, in this case, TESS stops at 13.5 days. It can't find planets beyond this for this system because we only had two transits of planet D, which we were able to link up, 2 transits of planet E, and then 2 single transits of the outer 2 planets. So we knew that there were probably 6 planets in this system, but we didn't know what the orbits of the outer 4 planets were at this point. So we went hunting with CHEOPS. So we started hunting aliases. Each one of these observations is a different possible alias for planets D and E. A couple of them are actually observations of planet B, just to improve the ephemeris of that one. And you can see that there is a transit lurking here. That's planet D. So we got lucky for planet D, and we found a 20.5-day orbit for that planet. And the interesting thing was that I looked at the periods at this point, and I realized that actually these are almost identical to 3/2 ratios. So they are within 1% of a period commensurability. And because we had 24 aliases, although we'd ruled out quite a few of these already for planet E, there were only a few possibilities for the next planet in the chain. And one of them was exactly 1.5007 times the orbit that we'd found for planet D. So we had a pretty good guess at this point for planet E. It must be at 30.8 days. But we still didn't know about these outer 2 planets. Oh yeah, and I should say that these are consistent with 3-body resonances, if you look at the Laplace angles. So for the outer 2 planets, how can we get the periods when we only have 1 transit? So one thing we could do is we could extend potentially this resonance chain and ask, okay, what could the period be? So we did this. We looked at the 5 lowest first-order resonances, and we tested them all and looked at whether the data maybe ruled out some of these periods. Maybe we should have expected a transit. We didn't see one. And that was exactly the case. 4 of these periods, actually, we would have seen transits. So the only possibility was for it to be a 4-3 orbits with planet E. So that was our prediction for planet F at 41-ish days. And then we did the same for planet G. And once again, 2 of these cases were ruled out by the photometry, but that left 3 potential orbits. But if you look at the actual Laplace equilibrium angle for these, only one of them is stable. So 2 of them have extremely unstable equilibrium angles, and then one of them is only 6 degrees away from the kind of the perfect resonance chain. So that was our prediction for the system. And this was all the data we had. And it's a shame, actually, if you look here at the first sector of TESS data, there's a hole where it would have been nice to have 2 transits. And well, we had a little bit of a spoiler. There are actually 2 transits there. So TESS was just masked here, and there were 2 transits exactly where we predicted them, thanks to the PLD decorrelation that we heard this morning. And so I will skip through this, but these are low-density planets. We have TTVs now from CHEOPS, so we have more than 4 transits of all of them showing large amplitude TTVs, as you'd expect. It's an extremely characterizable system, the brightest with more than 3 planets, the brightest resonant chain, and one of the best systems for interplanetary comparisons. So with that, I think I'll leave up my conclusions, and I would just say that if we want to find more of these systems, we want to make sure that we cover the mid-latitudes at longer than 27 days. I think that's an important step for the next, in the future with TESS. Okay, so with that, I'll thank you, and I'll take questions.
Thank you. We have time for maybe 1, maybe 2 questions. Yes, Dan.
Okay, it's somewhat provocative. If you can solve these from duos with the help of CHEOPS, then we don't need to go to the mid-latitudes because you get your duos and then CHEOPS go and find it. So isn't that going to give you what you need in terms of finding these at the mid-latitudes? TESS just visiting twice or three times?
I mean, our sample tends to be those cases where we have one transit per sector, but anything at 50 days is unlikely to transit twice. So the more time you can put onto these mid-latitudes, the more transits you're going to find, and the longer you're going to be able to push the planets that you can detect. So even if you could continue ad infinitum the current TESS strategy, we're still going to be limited by the amount of time that we spend on low latitudes. I mean, I've profited very well from the current TESS strategy in terms of this project, but I think there are more things out there that we're missing that we haven't looked at with CHEOPS, and we won't have the opportunity to potentially.
That's all the time we have. Thank you, Hugh. So from CHEOPS, we move to Plato. Plato was mentioned a few times during the week. If you were wondering what is Plato, then you are in the right place at the right time. Gianpaolo Piotto will tell us all about Plato and give us an update of what's going on.
Okay, thank you. So in this talk, I will try to give a brief overview of the mission, of the Plato mission, and an update on the status of the satellite. Plato stands for Planetary Transit and Oscillations of Stars. It's a complex medium-sized mission by ESA. It allocates 26 telescopes, 12-centimeter aperture. 24 of them, like we call normal camera, will operate in white light, and we cover about 49 by 49 square degrees on the sky. The remaining two cameras are dedicated to brighter stars and will provide light curves in two colors. The launch is scheduled by the end of 2020 with an Ariane 6, and it will be L2. As you see in the rightmost part of this slide, the more than 2,100 square degrees of the field will be covered by 4 groups of 6 normal cameras that are pointing regions in the sky offset by 9.2 degrees to have a larger field. This means that the field is not covered by all the field is not covered by 24 cameras, only the central part of the field. Then going to the outer part, the number of cameras that will be observing our targets will be less and less. In the outermost part, only 6 cameras. Each telescope is equipped with 4 4,900 square pixels for a total of about 2 billion pixels, which is twice Gaia. And by itself, you understand that with this huge number of pixels, it's impossible to download the full frame images, if not from time to time. But I will talk about this later on. Each pixel covers 15 arc seconds on sky. The status of the building of the telescope is quite advanced. 18 cameras have been already delivered to the prime. 3 of them are already mounted on the optical bench. The plan is to deliver all 26 cameras by the end of 2024. And at the moment, the mission is completely on schedule for the launch, as I said, at the end of 2026. Curiosity, each of the cameras is named after some late prominent European astronomer. So Plato basically will search for and characterize exoplanets and their host stars. with particular attention for Earth-like planets in the habitable zone of bright solar-type stars. Planets are identified with classic transit methods. Stellar hosts are characterized. Their radius, mass, and stellar age are estimated through asteroseismology for the brightest part of the sample. And quite unique for a space mission, the mission includes also the ground-based follow-up. For a selected, pre-selected sample, we will going to select it in the next few months of the entire target list of Plato. The consortium is committed to perform the ground-based follow-up for mass determination. So the final delivery of the mission will be planet density and, most importantly, planet age. Planet age is extremely important, as we know, to follow the evolution of the planets with time. And in particular, for planets in habitable zone, it will be interesting to follow the evolution of their atmosphere with time. Here you have a more detailed list of science objectives. We don't have time to go into details, of course. I want you just to focus on this lower, sorry. Don't know what's happening. Okay, this lower part of the slide. So at the end, the core program of Plato is to provide the bulk properties of thousands of exoplanets, including terrestrial planets orbiting solar-like stars in habitable zone. And as from requirements of the mission, for Earth-sized planet orbiting G0 dwarfs with magnitude less than 10, the parameters that will be measured should have an error of 3%, down to 3% for radius, and an error of 10% for mass and for age. Here you see a more detailed estimate of what we expect in terms of radius precisions as a function of the magnitude, and with the expected performances of the satellite. As you see, we expect to be able to reach 3% error in the radius down to magnitude for stars brighter than magnitude 10. So mean density for thousands of planets to help constraining the planet formation and the evolution. This is what is known, I mean, it was known till February 23, but not changed much, density against mass. But for the way the mission is planned and the observing strategy, the Plato will focus on planets with longer periods. That is extremely important, also because we don't know much for long period planets in terms of their density, the basic parameters. And even more, Plato will concentrate on small planets around solar-type stars in habitable zone. So far, we don't know much about these planets, even less for if we want to have a small error in mass and radius. And Plato will indeed fill this part of the parameter space. So impossible to download the full frame images. That means that we need to have the target list ready for the observations. We already prepared what is called the target Plato input catalog. We are already at the second version. It includes the targets and the targets parameters, main parameters, radius, mass, and luminosity, and so on. We have almost already a third version of the target input catalog that will include all candidate and confirmed exoplanet hosts and binary information on the targets. The list of the TPK is done with four subsample of stars. The most important one is the P1 subsample, dwarfs and subgiants spectral type F5 and later down to K7, limited to magnitude 11 and limited also in random noise in terms of the random noise of these targets should be less than 50 for 1 hour of exposure. A P2 sample, which is similar to the P1, but for brighter stars, to magnitude 8.4. And then a P4 sample that includes M dwarfs, and a P5 sample that extend the P1 sample to magnitude 13 for mainly for statistical reasons. In the first row, you see the number of stars that by requirement should be observing in the selected fields of observations. Below here, you see what will be downloaded. So images for the brightest stars, 25-second cadence for P1, 2.5-second cadence for P2, and mostly for the faintest stars, we will just have the photometer calculated on board, and we will have the light curves with a cadence of 600 seconds. All data will be public every 3 months after the initial calibration period. So everyone can have access to the data. The peak is even more complex than this because it will include also other 3 sub-peaks, one with the stars of high guidance, one for the stars for calibration, and last one, very important, will include more than 30,000 stars that will be used for the calibration of the models for both stellar and exoplanet science. The fields have already been selected. At the beginning of last year, we selected the 2 long pointing fields, as pointed out by George many times in the last days. Both of them includes the continuing viewing zone of TESS. How do we observe them? Mainly, okay, first of all, we have to take into account that the baseline duration of the mission is 4 years, but they are consumable for at least 8 years or more. So we, of course, plan or expect or hope for an extension. At this point, for sure, the first field that will be pointed by Plato will be observed for at least 2 years. They can be for 3 years, can be for 4 years, leaving the second field for the extension of the mission. The decision for how long we will stay on the first field will be taken after the launch of the satellite. Last but not least, the first pointing field has been selected in June last year. The science team has decided that the first field pointed by Plato will be the southern fields. You may understand for what reasons, because it's easier to have a follow-up. There are many more facilities for follow-up. Here you have the coordinates, equatorial, galactic, and ecliptic coordinates. And in the lower part here, you have the number of targets in the 4 different samples that will be covered by this first field. As I say, for at least 2 years, and then how we will continue will be decided in the next after the launch of the satellite. Thank you.
Questions?
Thanks for that great overview, Gijs Mulders, Adolfo Ibáñez. I was wondering, the precision of 3% for an Earth-like planet around a Sun-like star. It sounds amazing, but how would you confirm this is actually a real planet and not some false positive?
Well, of course, there will be the vetting procedure first. And then, as I say, we will have follow-up observations that are part of the mission. The first part of the follow-up will be for the confirmation of the planets, of course. And then for the confirmed planet, we will go with the high resolution spectroscopy for the mass measurement.
But follow with radial velocity, for example, can you get masses for such a planet?
Sorry?
Can you get radial velocity follow-up for the mass of the planet?
Yes, yes. The consortium is committed to have the masses from the radial velocity. For what we call the prime sample, it will be a sample of 20,000 stars, more or less, that will be selected in the next year. These, of course, sorry, in the next month. These are, of course, bright stars. Mostly will be P1 stars, so stars brighter than magnitude 11. And for confirming the planets, there will be the follow-up, the radial velocity follow-up for the mass measurement.
Okay, let's thank the speaker again. Okay, we are staying with Plato. We will hear from Yoshi Eshen about her work on looking at the Plato field with the lens or the eyes of TESS.
Okay, I hope the slides are coming at some point. Do I have to do anything? Oh, there we go. Okay. Okay, hi. I'm Yoshi. I'm a master's student at the University of Warwick, working with Dan Bayliss and Tom Wilson. And basically, we're looking at the Plato field and analyzing all the data we already have from TESS to just see what actually is in that field. And so I think we are all very familiar with TESS. And if we aren't, we've heard a lot about it during this conference. And also we've heard a bit about Plato. So this is just, again, an overview to just like point out the major differences. The two things that are really different is one's the orbit. Plato will be in L2, and the number of cameras, where Plato will have 26, which is fairly different to TESS. And this is also something we'll circle back to. If you are more interested in the Plato technical details, there's this great paper from Heike Rauer, which is like 100 pages in case you're ever bored. Feel free to read through it. As also already mentioned by Gianpaolo, Plato will be launched by the end of 2026. And we're observing around 5% of the sky for at least 2 years, maybe even more after. And this field is now confirmed. It's called LOPS2, and it is in the southern hemisphere. And the plot is on the right side on here. And so we can see how there's different number of cameras. So at the edges, we only have 6 cameras, while in the center, we go up to 24, and in between, we have like 12 or 18 cameras. This Plato field, again, as already pointed out, overlaps with the TESS continuous viewing zone. So on the left-hand side here, we have like the all-sky plots, which we know from TESS, where we have the sectors color-coded, and we can see in dark purple the TESS continuous viewing zone, and in white, we have the Plato field on top. On the right-hand side, I just like circle back to the normal Plato presentation of the field, which is in galactic coordinates. And here we can also see the TESS continuous viewing zone in this dark purple, which takes up around 20% of the field. So on these stars, we actually do have a lot of data. Also, just like looking at how much TESS data we actually have, this is a histogram of the stars that will be observed by Plato in the LOPS2 field over the years of the TESS mission. So this just shows the primary mission. And we can see this one peak at around 300 days, which is the stars in the TESS continuous viewing zone, while the other stars only get like a few sectors. And if we just like go through the years, we can see, oh, sorry, that was too quick. But we can basically see how it changes. And this is now up to 2025, which is how far TESS point currently goes. And by then, like by the launch of Plato, we'll hopefully even have more data, but even up to 2025, we'll have like a few stars, around 20%, that already have like 1,000 days of TESS data. So there is a lot to look at. On average, each star in the LOPS2 pick has around 10 sectors by TESS to date. And we can just use this data to actually gather information on the planet host stars, eclipsing binaries, and stellar variability that is already in the field. So during the conference, I think we've actually heard a lot about exoplanets, eclipsing binaries, and stellar variability, and we're all very aware that TESS can detect them. So I'm not just like going to show you these plots of what we have in the Plato field, because we do have all of that in the Plato field, obviously. Instead, I want to focus a bit on the precision and hence sensitivity differences between the two telescopes. Just to circle back, which is also another difference, is the types of stars that will be observed by Plato. While TESS is just like producing full frame images, Plato will focus on F, G, K, and M dwarfs and subgiants, and hence is also limited to stars. And for this project, we're mainly just going to focus on the P1 sample, which also includes the P2 sample, which are some bright stars around 10,000 around like of F, G, and K dwarfs and subgiants. So for all of these, because they're fairly bright, we have Spock FFI light curves and target pixel files. So we could just like get the CDPP value for the 2 hours for all of these targets that are in the P1 sample, which is plotted here as a precision. In gray, we can see the actual TESS photometric precision we have. The black line is the 50th percentile fitted by Michel Kunimoto. And then in the colors, we can see the predicted Plato precisions. And we were looking a bit closer at the stars that actually have a high CDPP value and found that around 35% of them just like have some kind of TESS systematic noise because like it's close to the orbits and scattered light, while 65% of them seem astrophysical, like actually being eclipsing binaries or stellar variability. So these are fairly interesting, just like go through them again and see if they should be in the low noise sample, which has a cutoff at 50 ppm an hour, also be removed. So that is something where TESS plays a very significant role. We also, as I mentioned, have some transiting planets. It's 76 confirmed transiting planet host stars in LOBS-2. Some of them are multi, so overall we have 96 confirmed transiting planets in the LOBS-2 field and 499 planet candidates. On the left-hand side, we can see all the confirmed transiting planets. In red are the TESS discoveries, in yellow are the discoveries that were already discovered by ground-based surveys such as WASP, HATS, CALD, and NGTS. And in this diamond shape, we can see the multiplanetary systems, which are 13. On the right-hand side, I'm just showing the TESS planet candidates we have in that field so far, and we can see some kind of gradient towards the continuous viewing zone and the galactic plane, which shouldn't be too surprising. I just like also noted down all the multiplanetary systems with at least one transiting planets. There's also multiplanetary systems that only have radial velocity planets, but for the sakes of TESS, we're just going to look closer at the transiting ones. And so in color code, we can see the stars, which represents the effective temperature. The circles represent the transiting planets, and the distance to their star is their orbital period, and the size of the circle is the planet radius. And we also have some systems that have some planets that are only discovered by radial velocity, but have a transiting planet as well, or TTV, which are respectively shown by a triangle or a square. Looking a bit more at the planets, we have some radius period diagrams here of our 96 transiting planets in LOBS-2. And we can kind of see how there's a cutoff at around 100 days for TESS. So there's only one system so far in the LOBS-2 field that has an orbital period of 225 days. The other one's kind of cut off as 100. And we can also see how longer period planets, as in like the ones closer to 100 days, are actually around the brightest stars, which is shown on the left-hand side, where the color represents the magnitude. And on the right-hand side, we see how many days they have to be monitored by TESS. And we can there also see we actually need a lot of TESS data to actually get the longer period systems. Hence, we actually need them to be in the continuous viewing zone, which is only 20% of the Plato field. So there's a lot of discovery potential still for Plato to find longer period planets. To show now this discovery potential Plato has, we use Tiara, which is a tool to estimate sensitivities. It was introduced on Wednesday by Toby Rodel, and he also has a poster, which is unfortunately not up anymore, but you'll probably find it online. And for TESS, we could use the real data, which is just the number of sectors, the proper timestamps, and the 2-hour CDPP we have. And for Plato, we simulated data, assuming it will observe for 2 years at its cadence of 25 seconds, and we used the noise that is noted down in the PIC. And we applied this now to only the P1 sample, which includes the P2 sample. So we only applied it to F, G, K dwarfs and subgiants. And so we differentiated between the different spectral types. So first, I'm going to just go to the F-type stars. So here we have our sensitivity plots On the left-hand side, we can see stars that are in the TESS non-continuous viewing zone, where we basically just draw a cutoff at 20 sectors, which is, because we have this bimodal distribution, it could have also been 30 sectors. We just went for 20 here. In the center, we have the TESS continuous viewing zone, and on the right, we have Plato. And basically, that's just in radius and period space again. If we have something that's color-coded by yellow or light green, that means that the sensitivity there is very, very good. Like, it should be very easy to detect planets there. As soon as we go darker, especially in the very dark blue region, it is very challenging. And we can already see how from the non-CVZ to the CVZ in TESS, we can very much expand in period space. And then for Plato, we even go further and for longer periods and also push further down because there are more cameras observing. We just plotted the confirmed planets we have for the respective stars in the lobster field in red and the planet candidates there on top, and see that they do kind of match up with what we have, which was very reassuring. We then just did the same thing for G-type stars. It's going a bit down just because, well, we're going from F to G. Again, planets on top. Then finally the same for K-type stars. Again, planets on top. For one K-type system, we actually, which is down here, we have a few planets that are in the dark blue area. And this is kind of a good example to show that this is just like averaging our sensitivities. There's obviously some stars that have better sensitivities for either TESS or Plato. And so this system, if you just look at the star, actually that is still in the green region. We then try to actually show the differences between TESS and Plato by subtracting the Plato sensitivity from the TESS sensitivity. Again, comparing non-continuous viewing zone to continuous viewing zone and the different spectral types. And basically the blue areas here are the areas where Plato is more sensitive than TESS is. And the white areas, if you go to the top left, are the areas where basically everything is already covered by TESS. Plato will also find gas giants, but TESS has already found them, so there's nothing new for Plato. If you look at the right bottom in each of the plots and the right top, we also have some white area, which basically means both telescopes in this area have a very big challenge of detecting planets just because they're either too small or too long period. I mentioned we do have a few radial velocity planets, which I just wanted to put up here just to show they are there. And on the mass period plot, which we have on the right, we can just see again, they're all around fairly bright stars. And some of them by Plato can potentially be ruled out because the long periods one probably haven't actually been observed yet. So Plato might be able to rule out that they're transiting or find the transits. Same for the low mass ones if they are of small radius. So I'm just going to leave you with my conclusions, and I'm very happy to take questions.
Thank you. Questions?
Hi, Yoshi. Great talk. Tara Feather up UC Riverside. I love that you put this figure on the right because that's exactly the one I wanted to refer to, where there's a couple of little segments that are only covered by 1 or 2 sectors. And we've heard from previously in the week that TESS could potentially do longer term observing away from the continuous viewing zone. Would that be beneficial to Plato as opposed to going to the continuous viewing zone again, or let Plato do it?
That is a very good question. And I think it depends on what the goal is. So for example, if you want to look at TTVs, it's obviously very good when we have very continuous data. But then right now, in advance, there might still be benefits from TESS. If Plato is launched, I don't think there's a big benefit because Plato will just cover everything and we'll just find the planets in this field. And I think one of the big things that TESS could help Plato with is also just flag things like stellar variability, eclipsing binaries, etc. But for this, the continuous viewing zone is not too highly relevant unless we're talking about long period variability. So I think having this already is quite a significant contribution, and then to actually find the long period planets can also just be left to Plato. And TESS could just observe other areas of the skies. I know there's a lot of points going into this, which can be discussed in more detail.
Jazz.
Very nice talk. one of the things that was the biggest challenge for Kepler for the long period planets was not the photon noise, but the stellar noise. So to what extent do the sensitivity numbers you show here include the actual properties of the stars as opposed to just counting the photons?
Again, another very good question. So the sensitivity plots are based on the noise that is noted down in the PIC. And that is a simulated noise, which I want to say is a bit too nice. As in, if we were just like looking at the precision plots I showed before, if we would just scale down the CDPP to the respective Plato curves, they don't really 100% match, as in there's still a few stars which are above. So some stars, also according to TESS, will actually have that good a sensitivity, but stellar variability is not taken into account too well yet, and some stars should be taken a closer look at. It's not all of them. I think it's like maybe around 20%.
Okay, one last question. JJ.
Thanks. Just very quickly, you showed some of these sensitivity plots as a function of radius. How much of that is driven by cadence for Plato?
Again?
How much of it is driven by cadence? So if you go back a slide or two, where you showed Plato doing a little bit better.
Yes.
Yeah, for especially the smaller radii planets. Is that some proportion due to cadence and some proportion due to the duration of the observations?
So we didn't really look at where it is coming from. So the cadence is definitely helping, but the major difference we have here is just the number of cameras. If we just like have 24 cameras, obviously it is like we have a lot higher precision and we'll be able to go further down in detecting like the smaller planets.
Great, thanks.
Great, thank you.
Thank you.
So from Plato, we are moving to yet another future mission, the NASA Pandora mission, and Ben Hord will tell us all about it.
Yeah, great. Thank you so much. Last talk. Thank you for making it here at the very end. My name is Ben Hord. I'm a postdoc at NASA Goddard Space Flight Center. I'm going to talk to you about the Pandora SmallSat mission on behalf of the Pandora team. It's a big mission, it's pretty small actually, but it's a big effort from a lot of different people. And so as a reward for making it this far in the conference, I think that you're all eligible for a prize. So we're going to play a quick game. It's called What Atmospheric Compound is Present in this JWST Transmission Spectrum? So we actually have seen this transmission spectrum today. So this is now going to be a test of were you paying attention? It could be a few different things. It could be water, CO2, methane, SO2. So think hard. The prize is an automatic selection for your next TESS GI proposal. So this is high stakes. Lock in your answers. If you went with E, we actually don't know right now because there's stellar contamination maybe, then congratulations, you just won. So this is kind of the problem that we're running into with a lot of transmission spectra with JWST now. We are having some trouble determining whether a water feature or other really, really interesting features are actually just due to stellar contamination. So this planet GJ486 is a super Earth and could have a water-dominated atmosphere. That would be very cool, but we can't rule out stellar contamination. And so we've already heard from both Ben Rackham and Mayuka Mori, so I won't belabor this point, but the transit light source effect is to blame here. So we have our star, and the traditional thought about what a star is kind of like a light bulb, a uniform source, some limb darkening, we can figure that out. But it's really more of a disco ball. It's inhomogeneous, you've got star spots, you've got faculae, you have not only star spots and faculae in the transit cord, but maybe more nasty are the activity spots outside of the transit. Because if you transit across some activity region, maybe you see that in the transit, it shows up as a blip in the light curve, you can kind of deal with that. But as you see from this figure on the right, depending on the spot covering fraction and the temperature and the spectrum of these different active regions, it's really tough to know if the transit you're seeing is actually the correct depth. And this is all wavelength dependent. So this is kind of a scary problem that we're now facing with the sensitivity of JWST. But have no fear, this problem is solvable. There's kind of two prongs that you can tackle it with. The first is to obtain photometric observations of the star, both across the rotation period of the star and long term. And this way you can kind of constrain the spot covering fraction of the stellar surface and see how they evolve over time. The other prong that you kind of need to account for is the spectral side. So if you get near infrared spectra, you can see how the spectrum of these spots and faculae evolve over time. And so putting these together, you can break the degeneracy of what is the rest of the star doing when my planet is transiting. And it's really important to do this simultaneously. You can do it from two different instruments, but then you deal with instrument systematics not lining up. And then if you don't do it at the same time, then you might get two different answers because the spots and faculae evolve. So it's important to do it simultaneously because we really want to understand what the surface of the star is doing, selfishly so we can understand the planets. I know there's plenty of stellar people here that would argue otherwise, but it's my talk, so I want to understand the planets. And that's where Pandora comes in. Pandora is an upcoming NASA small-sat mission that's going to do exactly that. It has two onboard band passes, a visible photometer that's going to observe in roughly 380 nanometers to 780 nanometers, and an infrared spectrometer, which is going to look from around 870 nanometers to 1700 nanometers, give or take. And so what this will do is it will constrain the star and spot faculae coverage in order to disentangle the star and planet spectra, ultimately to enable robust planetary atmospheric composition measurements. And that's kind of that's the goal here. We've done some simulations. So this is a simulated spectrum of planet GJ357 using what we think Pandora will be capable of at this point in time. And we expect an average decrease in contribution of the stellar spectrum to the overall observed transmission spectrum of about 15 parts per million. So it will be able to help us really tamp down on that contamination aspect and disentangle the stars and the planets spectra. So just a kind of quick fact sheet here. TESS's observing strategy, it's going to observe 20 transiting planets, 10 times each for 24 hours per visit across its 1-year prime mission duration. It's going to focus on K and M dwarf stars because not only are these a lot of times the stars that we're finding planets around, they're also some of the most active. And so if we can kind of get at the most cost-effective way of tamping down on stellar contamination for the most planets, we're going to do that. Like I said, it has simultaneous visible and near IR. It's on about a 0.45 meter diameter mirror on a CODA telescope developed by Lawrence Livermore National Laboratory. If you're interested in any of what I just said there, come talk to me afterwards. There's a lot of technical details about that. And it's going to be in a sun-synchronous orbit. So we have mission requirements. At top level, the two main mission requirements are determine the spot and faculae coverage of low mass stars that host exoplanets and see what impact they have on the spectrum, and then identify exoplanets with hydrogen or water-dominated atmospheres and determine which planets are covered by clouds and hazes. So it's really a two-part mission. 1, stars, 2, exoplanets because of stars. Hello? Oh, that's the wrong button. This is a TESS conference. This is not a Pandora science conference, as much as I would love that. So how can TESS help? And I can think of 3 ways off the top of my head that TESS can help prepare for Pandora to launch. The first is obtain stellar rotation periods. We've seen some of that at this conference too. TESS is great at measuring the rotation periods of the stars. It's important to know what their rotation period is to better constrain how the spots move around into our field of view and just get a better idea of what we can expect as we plan our observation strategy. We also want updated planet ephemerides. So this is a schematic of what the orbit is going to be. There will be Earth occultations of on the order of an hour sometimes for some targets. And so we don't want to miss a transit of a planet. So updated ephemerides from TESS and the ground are going to be super useful in that regard. And targets. I think that might be maybe the most obvious, but also possibly the most important. We've long known that TESS is good at finding targets for atmospheric spectroscopy. I shamelessly stole this from some pre-launch press. This was indeed said many times by many people in this room. So if you see yourself, thank you, I guess. But I'm going to give you a pass because I do think you misspoke. TESS is actually going to be a finder scope for Pandora because it turns out that most of the JWST targets are actually really great Pandora targets as well. We do have target selection criteria. We can't just take any TESS target. So like I said, we're looking at primarily low mass, cool stars. So we have a stellar effective temperature cut. We're also looking at planets that have an orbital period of less than about 18 days, just so we can get enough transits in that 1-year prime mission. And then we have some magnitude cuts so we can get some good signal to noise. And so that leaves a lot of planets still viable for Pandora to look at. So we developed a signal detection metric. It's just kind of a prioritization ranking. It's roughly based on the transmission spectroscopy metric developed by Kempton et al. In 2018, but we added in a couple other things because if we just went by the TSM, we would only look at hot Jupiters and that would be that. But we want to get a good coverage of period space and planetary radius space, as well as a good sample of stellar activity. So we also included some weighting in there to make sure we get good coverage, as well as some parameter about the amplitude of the variability seen in the visible photometric light curve of the star. So when you plot that up in a effective temperature and radius plot, you get something like this, where the circle's size and color is based off of their SDM. And you can see there's quite a few pretty big ones. They're kind of the biggest ones, which is not a surprise. And so we filtered kind of every planet that has been confirmed on the Exoplanet Archive in through this framework. And what we get is this notional target list. I will stress that it is notional. It's subject to change. Pandora's not going to launch until at least the end of next year. But as you can already see, there's a lot of TESS discoveries on here. 11 out of these 20 prime mission targets are TESS discoveries. And so I think the power of TESS in finding these planets is not to be overstated. Oh, sorry, if I can go back. If you want to see this list or download more parameters, I put the website link at the bottom. Pandora has a website, so take a look at that. The Pandora mission schedule is very flexible though, so this is kind of like a mock schedule from an old target list. All of these little tick marks are observations of transits across the 1-year prime mission. So the science calendar for the mission is going to just be generated at the beginning of every week. So as new things are discovered, as new JWST data is taken, as other missions are observing things, we can be very flexible in what we want to observe when. I will also note that about a third of the 1-year prime mission is unscheduled. It's not necessary for accomplishing the prime mission goals. So we're expecting to have some sort of DDT call. So if you're interested in simultaneous visible and near infrared data, we want to know about it because we need to fill the time, and we need to point somewhere when we're Earth occulted. So come talk to us. Wrapping up quick here, just where are we at? This is a timeline. You are here, we're in the assembly, integration, and testing phase. Pandora did pass its critical design review late last year. We're on schedule for our September 2025 launch readiness date. So stay tuned for that. And hopefully that will give us a lot of time to be concurrent with other missions and have really good synergy. So this is one of the last slides I'll leave you with. In brief, we have a robust suite of simulation tools that we've been using to already see what the data could be like. The GitHub link is down at the bottom there. If you are interested in using these tools, it is pip installable, it is stable. See if your favorite target can be observed, and then let us know, because we want to observe as much as we can with this observatory. Also, the last thing, This data will be public as soon as we can process it. So if you're interested in just looking at any of these targets, stay tuned. So I'll leave up this as my summary slide. If you have questions, email me. I also put the PI and project scientist emails up there because they're not here and I can throw them under the bus on this, or go to our website. I'm happy to take any questions and thank you so much.
Questions?
Hello, Aviv from the Weizmann Institute. Very interesting mission. How do you intend to achieve this lofty goal of precision when you're in low Earth orbits, scattered light from the Earth and so on?
So if I heard correctly, the question is how are we going to deal with scattered light in low Earth orbit? Yeah, more or less. Someone has an answer. I don't know if I'm the person who has that answer, but we're working hard with Lawrence Livermore National Laboratory using this telescope platform. We do have a baffle on the telescope to try and mitigate some of this stray light. Their engineers are hard at work. This is a telescope platform that they've been wanting to use for astronomy for a very long time, but it's been used for Earth observation. Interpret that as you will. So this telescope platform has been tested for low Earth orbit, and the details are classified. I don't know. So I know that's not really an answer to your question, but I don't think I have a good answer to your question. But I'm happy to chat with you afterwards and point you in the direction of someone who would.
Okay, that's all the time we have. Thank you, Ben. And thank you for all the speakers of this session for giving us this voyage in synergies with TESS, and especially looking at the future missions, and the future is obviously bright. Before I wrap up, I'd like to invite George for a short note. You can use this. On the podium.
I'll just go to the podium because I'm okay.
Okay, well, it's a real pleasure. I just have to use this. It's a real pleasure to be here for the week, and I think that everyone will agree that this has been a really wonderful meeting. The SOC did a marvelous job of selecting and organizing the talks and the posters, and Avi and his team really worked tirelessly to orchestrate this entire effort, and I think it's been a really enjoyable occasion for all of us. And when I think back over the 18 years that we've been working to make TESS happen, one of the things that really stands out is how many of the topics that we have seen very mature presentations made during this last week were not even hinted at or in our original proposals for TESS at all. Exoplanets were certainly there, but there was no mention of solar system objects, no mention of flare stars, galactic, extragalactic transients were very briefly mentioned. Supernova and no tidal disruption events were part of the science focus. There was a little bit about asteroseismology, but those were the things that we really were mostly silent on, and look at what's actually happened. The slide that I've got, I'd just like to show a little bit again. If we look at where we are in this, now I hope this works. I don't really want to change the slide. There we go. Okay, so the part that I've blocked out in the light blue is the left. We're in 2024. What I'd like to focus on is that panel at the very end, in terms of what will be happening if we have what will have happened, I guess I should say, if we gather again 3 years from now. We would be in the extended mission 1 year from the end of that period. CHEOPS will have continued to work. JWST will continue as it has. Hopefully LIGO will be in 05, and we're going to have a lot more transients to talk about from that are associated with gravitational wave events. Rubin will be just producing enormous amounts of information. Ultrasats will hopefully be about to launch or have launched already. Plato will be up in orbit. and the extremely large telescopes will be operating, at least the EELT, and Roman will be flying. So it's hard to imagine what we'll be able to talk about at that time, and I think that we're all excited about the fact that TESS will continue to be part of the story, and we're looking forward to seeing everyone again in 3 years' time. Thank you.
Remind everyone, for some of us, maybe most of us, the work is just about to start on preparing for the Extended Mission 3 proposal after this week-long of brainstorming of science on the huge range. Let's start. I want to remind you, if you haven't taken your, if you see your name here and you haven't yet taken the certificate, it's waiting for you right here. And please take it, or if you have a colleague from your local institution on this list, you can take the certificate for them. It will make for less room in my office, or more room in my office, actually. Okay, I want to emphasize, while I'm talking to you here, this has been a very large group effort, the SOC and also the LOC, who have been working behind the scenes, and you may have not seen them, but they have been working very hard. And there is MIT Conference Services. You've seen them in the Kresge lobby. They've also been working very hard, but also behind the scene. You don't see them, but they are a critical part of making any conference at MIT a success. And also MIT audio video people, again, backstage, behind the scene, and up there in the booth, also working very hard all day long. So let's give all of them a round of applause. We have, while your memory is still fresh, that's the time to give us some feedback. And we have it's a very short form, I promise you, just any feedback you may or may not have. Positive feedback, things that you like and you want, oh, you need to keep this for the next conference. This was awesome. Like the M&Ms or whatever. The next conference, I want espresso and cappuccino, which I really do. But or something you didn't like and we should improve or change. That will help us do better for next time. And this is anonymous, so write whatever you want, anything that can help us. You can use this QR code. You can use this tiny URL, TSC III feedback, or as of 10 minutes ago, this link should be in your inbox. A few other logistics. As you go out at the registration desk, there is a small card box where you can put your name tag, so we can use it for future conferences. If you want to keep it in some collection, you can keep it. But if you have no use for it, we can use the plastic and the lanyard for future conferences. Everything here was recorded. The recordings, minus the few talks where the speakers asked that we don't make it public, will be made public. It will take some time, sometime in the next few weeks. We will send a message about that. The Slack workspace, if you have some private one-on-one messages or group messages, it will probably never go away. It will always be there. For example, the Slack workspace for the second TESS Science Conference from 2021, it's still there. This is under the MIT license, so we have no, they are not limiting us for anything. They never told me you have a limit, so we don't. Okay, so with that, this is a group photo from Monday. and we will see you in TESS Science Conference 4, which will be tentatively, like Joel said, in 2027, as we are syncing these conference with the NASA senior review process. So thank you.